Hello everyone, this is Aditya and today we are going to do ordinary differential equation and we'll cover everything from basics to the advanced level. And of course it is for your engineering mathematics too. So get ready for diving into the ordinary differential equations, and now let's start with the lecture. But before that, please do like and subscribe my channel, and now let's dive into the topic. Okay. So before starting with the ordinary differential equations, you all must know that what is a differential equation? Well, a equation which consists of differential terms. What does it mean? For example, dy by dx plus x is equal to 0. It is a differential equation. d2y by dx square. Don't worry about this. We will discuss. Plus y dx by, dy by dx is equal to suppose 0. This is also a differential equation, right? So all such expressions which involve differentials or derivatives along with the independent or the dependent variables and somewhat like that is said to be a differential equation, right? And of course there can be n number of independent variables, right? So now let's see further. Okay, let me raise this. Okay, so what is ODE, this ordinary differential equation? Well, let's see. Okay, so basically ODE, it consists of only one different, one independent variable, right? Independent variable, right? What does it mean? For example, we can take simple d3y by dx cube plus dy by dx to the power 5 is equal to a some arbitrary constant to the power x. This is our ordinary differential equation, right? Okay. And if we see, suppose d2v by dt square is equal to k, where k is a constant, del v by del x whole square. Of course, here should also be del, right? Partial derivative. Because here there are three variables, right? There are two independent variables in this case, right? So it is called a partial differential equation, right? I we are understanding this, okay? And we will be working upon the ordinary differential equations, right? And that too the linear differential equations of degree 1 and higher, right? Now, having said the word degree, what does it mean? Let's see. So basically, if I use the word degree, what does it mean? But before that, we should know the order, right? Suppose I wrote d2y by dx square plus dy by dx plus x is equal to suppose 0, right? I have written this. So what is the degree? Well, we won't discuss first of all degree, we will discuss the order. So order is the highest order derivative, right? For example, d2. So here 2 is the order, right? Okay. And degree is defined as the power to which that order is raised. d2y by dx square, it is raised to the power of 1. So hence it has a degree of 1. Degree is equal to 1, right? And in this case, suppose if it was del 2v by del t square is equal to, it is del time is equal to k times del v by del x whole square, right? Okay. So what is its order? Its order is 2, right? Okay. And what is its degree? It's, of course, it's 1, right? If it were 2 over here, it would be 2. If it was n, it would have been n, right? Okay. And suppose I say over here it's square, then its degree will be 2, right? Remember this thing, okay? So having discussed all this, we will move further, right? Okay. Now we are going to see linear differential equation. What is a linear differential equation? Well, a differential equation consisting of the degree 1 only, right? Okay. Suppose d2y by dx square plus dy by dx plus x is equal to 0. This is a linear differential equation, right? But there's a catch. There's one more condition, that if I use a variable, a dependent variable with any of the derivative term, or if I multiply suppose d2y by dx square dot dy by dx plus y is equal to 0, then this is not, due to this term, this will not be a linear differential equation. Why? Because you can't multiply derivative terms, right? In that, and in this case also you can't multiply by a dependent variable with this. Okay, we will see later that why is it the case, but for now this is the condition, that the first condition is that the every dependent and every derivative has a degree 1, right? And second condition is that no products of dependent variable and derivative occur, right? Derivative occur. This is the condition, right? Of course, here there was product, so it is not a linear differential equation. But d2y by dx square plus y dy by dx plus y plus x is equal to 0 is a linear differential equation, right? So you need to understand this, okay? Let me raise this and then we are going to move further, right? Okay, now what is meant by the solution of differential equation? So let's assume a very simple differential equation that y is equal to d2y by dx square or dx2, whatever you want to say. Okay. So what does it mean first of all? If suppose y is equal to fx is a function, right? Okay. You take the first derivative, it will be f dash of x, right? Okay. And if you take the second time derivative d2y by dx square, it is nothing but d by dx of dy by dx, right? Which is equal to f double prime x, right? You can say this, right? And of course that suppose y is equal to e to the power not e. Let's take a simple example, x square, right? So what is dy by dx? It's equal to 2x, right? Okay. And what is d2y by x? It is equal to 2. What is d3y by x square x cube is equal to 0, since the derivative of 2 is equal to 0 and derivative of x is equal to 1, right? Okay. So having said all this, let's see that what do we mean by the solution of a differential equation. Well, let's see. So in this case, that y is equal to d2y by dx square, we can see that y is equal to e to the power x is working in this case. Why? Because dy by dx is e to the power x, and if you again take the derivative is equal to e to the power x, which is equal to y. So e to the power x is indeed a solution of this equation, right? So this is how we solve the differential equation. I mean, how we check that what is meant by solution. There are many ways to check to find the solution of the differential equation, which we are going to see in the later part of the video. So kindly bear with that. And of course, if you are liking this video, then please do like, subscribe my channel, and please do subscribe my channel, and please share it to everyone as much as you can. And now we will see that yeah, there's one more thing which I need to tell, that when we will solve the differential equation, let's see first of all, let's see with the question. Suppose xy is equal to a e to the power x plus b e to the negative x plus x square. So we need to solve, we need to form a differential equation of this out of this equation. So here a and b are arbitrary constant which we can choose, right? Okay. So the thing you have to note that the order of differential equation is equal to the number of arbitrary constants present, right? Which means in this case there are two arbitrary constants, so at max you can take d2y by dx square, not more than this. Okay, so you have to remember this. You can't take d3y by dx cube, right? You can't take this. You can just take the maximum power, I mean the maximum order as 2, right? Okay, so we can solve this very easily, that xy is equal to a e to the power x plus b e to the power negative x plus x square. So we can simply take the derivative. We get y plus x dy by dx is equal to a e to the power x minus b e to the power negative x plus 2x. We can take another times the derivative and we get dy by dx plus dy by dx plus x d2y by dx square is equal to a e to the negative a e to the power x, sorry, plus b e to the power negative x plus 2, right? So we have this equation. Of course we can further simplify it also. We will get 2 dy by dx plus x d2y by dx square is equal to a e x plus b e negative x plus 2, right? We get this thing, okay? And of course if you see that this can be said as, if you can see from here, that this is equal to, if you simplify you get xy minus x square plus 2, right? From this, okay, you get this value, the value of this expression as xy minus x square, and to add a 2, you added a 2. So this is your differential equation, 2 dy by dx plus x d2y by dx square is equal to xy minus x square plus 2, right? Okay, this is how you manipulate the things and you understand and solve the problems, right? And now let's see that how does a general differential equation look, okay? And of course you need to remember this thing also, right? Okay, and now let's see, okay? So any linear differential equation can be written as the function of the variable, independent variable, then the dependent variable, then the derivative, the first derivative, then the second derivative, until the nth derivative, right? Okay, of course, for example, x plus dy by dx is equal to y. This is also the of its form, right? So basically if you solve this, I mean if you, when you solve this, you get two kinds of solution. One is the general solution, and the one is the particular solution, right? Let me change the chalk. So what do I mean by the general solution? It means it will consist of, n variables, right? Okay. And in the case of particular solution, you assign values to the variables, right? To the arbitrary variables, right? I mean arbitrary constants, right? And of course the values you can't just do like that. It is like you have to solve for them, right? And this is how we distinguish between a particular solution and a general solution, right? And we will see it in the later part, okay? So don't worry about anything, okay? So what next we have to do? And okay, so we can take an example also. For example, that dy by dx whole square is equal to 4y. So you can take square root both sides. You get dy by dx is equal to plus minus 2 root y. So you get 1 upon 2 root y, 1 upon root y dx is equal to plus minus 2 dx. You simply take the integral. You get root 2 root y is equal to plus minus 2 x plus an arbitrary constant, right? Okay. So you get basically root y is equal to plus minus x plus c by 2. C by 2 you can write another constant, suppose c dash, right? So you get y is equal to c dash minus plus minus x whole square, right? Okay, so this can be one of the equations. So if you take one, so this is a family of curves actually which you are getting. And if you substitute, suppose we take y is equal to 1 plus x whole square, I mean c plus x, and you put c is equal to 1, right? If you are given at a point, suppose it satisfies a point, okay, and you get the value as c is equal to 1, so y is equal to 1 plus x whole square is a particular solution of this general differential equation, right? Okay, so let's move further, okay? Now we need to know one thing more, which I am going to tell. Just let me erase it. That when we are solving the solution, it can be written in two forms, right? What are those forms? We are going to see in just a minute. Okay. Just let me erase this, and yeah. So the solution can be explicit and implicit, right? Okay. It can be explicit and it can be implicit. What do I mean by explicit? In this case, the variables, or you can say that y is equal to some function of x. You get something like this. Suppose y is equal to x square plus x plus 2, right? And in this case, you get fx comma y is equal to 0. Basically, it is a two variable function. And suppose x square y plus z plus x sine y is equal to 0, right? This is how, suppose here also some other term, maybe cos x, right? So this is a implicit differential equation and this is an explicit differential equation. Of course, you can convert a explicit into implicit, okay? But it is difficult to convert implicit to explicit, right? Okay. So now let's see what next we have to do, okay? So let's see how we solve the first order differential equations of first order and first degree. Okay. Of course, we'll be dealing with only first degree only in most of the cases. So let's see. Okay. So solution of first order, first degree differential equation, right? So we are going to see this now, and the first one is, and I hope that you all must have studied in your 12th grade also, but still I will be telling from a very down level so that everyone can understand. Okay. So first is this variable separable method, right? Variable separable method. Okay. I hope my spelling is fine. Whatever. Even if it's not understand. Okay. Even if it's not kindly understand it. Okay. So suppose you are given dy by dx is equal to e to the power x minus 2y plus x square e to the power negative 2y, right? So of course you can see you can separate the variables. How? Let's see. Dy by dx is equal to e to the power x into e to the power negative 2y. You know the property of e to the power alpha plus beta is e to the power alpha dot e to the power beta, right? This is simple property, you know, na? Okay. Be it plus or minus. Okay. If it is, then it is plus minus over here. Okay. It's okay. Plus x square e to the power negative 2y, and you can take e to the power negative 2y as common. When you take common, you get e to the power negative 2y into x square plus e to the power x plus x square, right? You get this thing. So you get dy by dx is equal to e to the power negative 2y into e to the power e to the power x plus x square, right? So you get e to the power 2y dy is equal to x e to the power x plus x square dx. You integrate it and you will put an arbitrary constant of integration. It is e to the power 2y by 2 is equal to e to the power x plus x cube by 3 plus c, right? This is how you solve using variable separable method, right? Now maybe my answer is wrong because there might be some calculation error at any point, so kindly neglect that. And yeah, now let's move further. Basically I'm trying to tell the concepts of the differential equations so that you all can understand things. Maybe if I make some calculation error, kindly rectify it on your own, okay? And if I see, I will write in the comment section if I see it later, okay? Or I will put it somewhere over here also, okay? So basically now we are seeing equation variable separable, or let me write equations reducible to variable separable, right? Okay. Suppose you are having dy by dx is equal to some function ax plus by plus c, right? So in this, how you convert it to variable separable? Let's see. You will do ax plus by plus c. You set it equal to t, right? And if you are having problem in understanding using this, you can see it using dy by dx is equal to 2x plus y plus 3 whole square, right? Over here you will do 2x plus y plus 3 is equal to t, right? And then solve. So I am telling the general approach, you all try using this, okay? So we get dt is equal to a dx plus b dy, and so we have dt by dx is equal to a plus b dy by dx, right? Of course it's fine. Okay, so from this we get dt by dx minus a into 1 upon b is equal to dy by dx. So we get 1 upon b into dt by dx minus a is equal to f at t, right? Is it fine? And now it is variable separable, right? Oh, I was checking my mic is working or not. So we can solve it. Dt by dx minus a is equal to b times f at t, right? So you get dt by dx is equal to b f t plus a. So now what you can do is you will write dt by a plus b f t is equal to dx. You simply integrate it, you will get the answer, right? If I'm correct, right? Yeah, whatever be the case. And over here also you get dt is equal to 2, dt by dx is equal to 2 plus dy by dx. So you substitute over here, you get dt by dx minus 2 is equal to t square. So you get dt by upon t square plus 2 is equal to dx, and you integrate it, and it's your job after that, okay? It is simple integral, right? So yeah, let's see further that what we need to do, and let's see. So suppose if you are given a question that sec x plus y is equal to dy by dx, right? You can do it as your homework. Of course, the method is same. I had chosen a general function. So if in this case the function is equal to sec x, right? Okay. Now let's see another form. Now we are going to see homogeneous equations, right? Okay. So how do we first of all check that whether the given function is a homogeneous function or not? So in that case, suppose it is like this: f of x comma y, it is given like this. What you do when you substitute phi of t x comma t y, where t is some variable, if you get t to the power n as common and then you get phi x comma y, then we say that the given function is a homogeneous function, right? And we won't discuss what is n over here right now, but you need to understand this, okay? So suppose if you are given this, let's see with an example so it will be better to understand. Suppose you are given dy, basically the equations of the form dy by dx is equal to f of y by x, right? Okay, understood? Then in that case, what you will do is you will use y by x as t. So you get the differential as dy by dx is equal to x dt by dx plus t, right? You substitute it over here, you get x dt by dx plus t is equal to f at t, right? You get this, and so you get dt by dx is equal to f at t minus t, which means that when you solve it further, you get dt by f at t minus t is equal to the integral dx plus c. Write this, you can solve it, okay? Yeah. If you want to solve, you can take an example that x cube plus 3xy square dx plus y cube plus 3x square y into dy is equal to 0. So when you solve, you get negative dy by dx is equal to x cube plus 3xy square upon y cube plus 3x square y. How do you check that is it a homogeneous function or not? You substitute x with tx and y with ty. Of course this t and this t is different, right? This is another variable you can assume. Okay, so you get t cube x cube plus 3tx plus 3t square y by this stuff. And if you will see, when you take common you get t to the power 0 into phi again, right? It means it is your homogeneous function, right? So to solve this you have to make it to the form of y by x. So what you are going to do, you will do like this. You take x cube common from the numerator, you get 1 plus 3 into y by x, right, whole square, upon you take x square, you can take x cube as common from the numerator, from the denominator I mean, whole cube plus 3y by x. Now it is just a function of y by x, and just apply this. Okay, I mean this method completely. You can assume y by x as t and then solve it further. Okay, now we will see another method, I mean another problem, that equations which are reducible to homogeneous functions, right? Homogeneous differential equations, I mean. Okay, let's see. Okay, so equations, is it fourth or fifth? I guess it is fourth. Equation reducible to homogeneous differential equation, right? Now we are going to see equations which are reducible to the homogeneous equation, homogeneous differential equation. Suppose dy by dx, we will take a case, is equal to a1x plus b1y plus c1 by a2x plus b2y plus c2, right? And over here a1 is not equal to b1, a1 by a2 is not equal to b1 by b2. Okay, so in such case what you do is you substitute x as x plus h and y as y plus some k. So you get dx is still equal to dx and dy is still equal to dy, right? Which means dy by capital dy, capital dx is equal to a1x plus h plus b1y plus h plus c1, c plus I mean k, upon the quantity a2 x plus h plus b2 y plus k plus c2, which is equal to, if you solve it you get a1x plus b1y, a2x over here, 8 plus b2y plus a1h plus b1k plus c1 by plus a1h, I mean a2h plus b2k plus c2. And from these two equations, a1h plus b1k plus c1 is equal to 0, and a2h plus b2k plus c2. You know the values of c1 and c2. You know the value of a1, a2. You know the value of b1, b2. From this, you will solve for h comma k, and you choose such h and k, right? Okay. You can take an example also, x plus 2y minus 3 by 2x plus 3 plus y plus minus 3 is equal to dy by dx. Over here a is equal to 1, a1 is equal to 1, b1 is equal to 2 and c1 is equal to negative 3, and a2 is equal to b1, b2 is equal to 1 and c2 is equal to negative 3. Okay, so from that you can solve for h and k, right? And of course when you solve this you will get some function in capital X comma y, you have to substitute back to small x minus h, right? Okay, I will understanding this. And now we are coming to the exact differential equation. It is something really interesting. So we will see that. So now we are going to see how do we solve the exact differential equation. And it is simple, but it has some ideas which are like very interesting. So to solve for the differential equation, for the exact differential equation, suppose you have a differential equation m x comma y, where m is a function which is a m is a function of x comma y into dx plus n, which is a function of x comma y again to dy is equal to 0. And this is a general equation, right? Okay. So if m comma n are the functions of x comma y, then and this is equal to 0, then it is called an exact differential equation if del m by del y, right, is equal to del n by del x. This is your first condition, and of course it is basically the necessary and sufficient condition, so there's nothing much needed more. Okay, let me see if anything has to be done. But why is it so? Well, let's see. We'll see the proof also, that suppose we are given that mx comma y dx plus nx comma y dy. This is your equation, right? And suppose now what we are going to do is that in this we will assume a function over here that uh, suppose we get a solution of this as f of x comma y, right? So we have d of f x comma y is equal to del f by dx plus, I mean, del f by del x into dx plus del f by del y into dy, right? Where f is the function which is the solution of this differential equation, right? So let me see what we need to do. Yeah, now we know that this equation, right, when you take the derivative you will get back this equation, right? So it will be equal to, since it was a solution, if you take the derivative you'll get this equation back. It is obvious, right? So you get this is equal to m dx plus n dy, right? Is it fine? Okay. So what basically it means that m is equal to del f by del x if we compare the coefficients, and we get n is equal to del f by del y if we compare these coefficients, right? I mean the derivative terms. And you take again the derivative, you get del m by del y is equal to del 2f by del x into del y, I guess. Okay, if I'm not wrong, of course, since we are going, yeah, it is like this. And del n by del x is equal to del f by del x into del y. And now if we are assuming that f to be a continuous function up to the second order partial derivative, and of course which it is, right, then it means that del m by del y is equal to del n by del x if we assume f to be uh, continuous up to second partial derivative, second order partial derivative. Okay, so now we can say that m dx plus n dy is equal to df, right? And it should be equal to 0, which means that df is equal to 0, right? This is also the case. Okay, so now what we are going to do is we will see some problems and then we will see how we will solve it. Okay, let me erase this and let's see how we solve such kind of problems. No need to worry much about it. I know that it must be confusing, so no need to worry. I will tell how to solve and you will understand it. Okay? So first of all, let's see the question. It states that we have to solve x square minus 4xy minus 2y square dx plus y square minus 4xy minus 2x square dy is equal to 0. So term with x, dx is m, and with y is called n, right? We have this. To check for the exact differential equation, we will check del m by del y, which is equal to del by del y of the quantity x square minus 4xy plus minus 2y square, which is equal to minus 4x minus 4y. And if you take del n by del x, it is equal to del by del x of the quantity y square minus 4xy minus 2x square, which is equal to negative 4x minus 4y. So these two are equal, right? So the condition is satisfied. So it is an exact differential equation. And now we are going to solve this one. Okay. So let me raise this, then I will tell you how to solve it. We checked that it is so. Now we know that m is equal to del f by del x, which is equal to x square minus 4xy minus 2y square, and similarly del f by del y is equal to y square minus 4xy minus 2x square, right? You are getting this thing, and now you can solve it, right? So if you solve, you will get f is equal to integral of x square minus 4xy minus 2y square dx. Just integrate it. You get f is equal to x cube by 3 minus 4x square, 2x square y plus minus 2xy square plus a constant. And this constant is assumed to be a function of y, right? In this case, it is just assumed. We will see how, okay? And now what we are going to do is we will substitute the value of this thing over here. You get del by del y. What is f? F is equal to x cube by 3. X cube by 3 minus 2x square. This square, let me write it clearly. X square uh, into y minus 2xy square plus c of y, right? And this is equal to this quantity y square minus 4xy minus 2x square. And now we can solve it. And when you take the derivative, this term will become 0 and you get minus 2x square minus 4yx plus dc by dy is equal to y square minus 4x y minus 2x square. So this and this gets cancelled, this and this gets cancelled. So you are left with that dc by c by dy is equal to y square, right? Is it the case? So you can solve that c is equal to y cube by 3 plus some other constant alpha, right? Where alpha is an arbitrary constant, okay? So now we have the value of c. So from this we can find the value of f as x cube by 3 minus 2x square y minus 2xy square plus y cube by 3 plus some constant alpha, right? And this is the solution of the differential equation, right? Okay, this is very simple, right? And most of the cases you can use this method, right? There's a trick also that you take m dx, you integrate it, then you take the terms which are not x over here and you integrate it. That is also a method, but I don't believe in that much because it is like you don't you move away from the concepts, right? So if you want, I will tell in the later part of the video, or maybe in some other video when I make the probable questions or practice problems, then in that case I will tell. But for now I'm not telling that because else you will start focusing on that, okay? That is why I'm skipping that thing. And of course that is an option to avail or not. So if you want, I can tell in the later videos, but not in this one because it will be like more sort of rote learning, which I don't want. Let me raise this, and now let's see that what else can we do. Let me see, do we have another problem, or can we do it by another approach? Okay, now we are going to see reducible to exact form. Sorry for my writing. Okay, so suppose in the case of m dx plus n dy is equal to, so in the case of m dx plus n dy, if del m by del x is, del m by del y is not equal to del n by del x, then in that case it might be possible that the equation is not exact, or there's another chance that it can be convertible or reducible to the exact form, right? So we'll see that only. Okay, so if del m by del y is not equal to del n by del x, so how do we check it? Well, we multiply by an integrating factor of I x comma y. Okay, so what we get from this, we get I x, let me, you know this, it is a function, so I m dx plus I n dy is equal to 0. Now del by del y of I m you will take, it is equal to m di by del y plus I del m by del y, right? Similarly, I del n by, so it is a chance that they both can be equal, right? If they are equal, then you are good to go, right? So how we will check it, that is another thing to be noticed. But before that, let me tell you a small concept that suppose you need to remember that sometimes you can guess the value of I using, you know, dxy, you know, dy by x, you know, do you know dx by y, and then you should know d ln y by x, and d ln x by y, 6 d tan inverse y by x. Of course it is optional, you can calculate I, but sometimes it works in general sense, you can guess it using this. So if you want you can do, but I won't prefer it, right? But it is taught many times, so that is why I'm telling you all, right? And you should remember d ln xy y dx plus x dy by xy, and similarly you solve for all other. Suppose it is equal to x dy plus y dx, and suppose this is equal to, you can solve it, I've already solved, so that is why I'm not solving it, else it will take lots of time. So x dy minus y dx by xy, like this. Okay, so you can solve it, you should solve it actually, all of them, and you should write them in your copy if you want to guess the integrating factor. But it is more better to solve it, which we will see how we will solve. For example, let me tell you using a question that y into y square plus 1 dx plus x y square minus 1 dy is equal to 0. So notice here del m by del y is not equal to del n by del x, right? So in this case, what you're going to do is that if you solve, you get y cube plus y dx plus x y square minus x dy is equal to 0. So what you are going to do is you get y cube plus y dx minus x dy plus x y square is equal to 0. And notice that you have this term y dx minus this term. So notice that this, what is equal, this is equal to what, this is equal to y dx minus y minus x dy by x square, right? You know this thing, and this is equal to, sorry, it is x by y, and this is x by y over here. So it is equal to y dx minus x dy by y square, right? Is it fine? And it will be equal to x dy minus this. Okay, I'm not calculating, so there might be chance that I've written wrong only, and which I'm writing. So just notice that if it is wrong, just tell me in the comment section. Else, it is your homework to solve all this and write in your copy or whatever you want. You can remember, it's good. If you can't remember, then also it's good. So we will calculate it. Okay. So no need to worry about anything. So over here we will divide by, since we see a y dx, so we will divide by y square. So you get y plus y dx minus x dy by y square plus x is equal to 0, which means that uh, sorry, it will be a dx also. I forgot to write that. It will be equal to dx over here, and it will be dy over here. Okay, sorry, dy and dx, right? So you get y dx dy plus d by x by y, right? Plus x dx is equal to 0. You integrate, you get y square by 2 plus x by y plus x square by 2 is equal to some arbitrary constants. Okay, and this is how you solve this equation, right? And right, okay. I hope I made a mistake over here. Yeah, yeah, sorry. It will be dy over here, and this is dx. Sorry. This is this. I'm really sorry. I'm really sorry. This is y, and this is your x. Okay. Let me erase this. You get y dx plus x dy. I'm really sorry for that mistake. Plus dx by y. And notice that this is d of xy plus d of x comma y, x by y, which means xy plus y plus x by y is equal to c. This is your result. Okay. Are you understanding this? How we got this? Okay. So now let's see the general method, how we solve for it actually. I'm sorry for that mistake again. Let me erase all this stuff. Okay. Now what we are going to do next is yeah. So we had calculated that uh, let's del im by del y, it must be equal to del in by del x, right? Is it the case? And this is a partial differential equation. If you can see, it is a partial differential equation, right? So let's see. So if we assume I to be a function only of x, right? So in that case, you can bring I outside, you get I del m by del y is equal to, and then you can solve for this, I del n by del x plus n del I by del x. You will get this thing, okay? And from this, you can calculate the value of del I by del x, which is equal to I del m by del x minus I del n by del x upon n, right? Simple. And now we can see that this is equal to I times del m by del x minus I mean this is del y, sorry, this is del y minus del n by del x by n. This is your thing, okay? And this will be a function of x, okay? So what we can do is that it will be equal to, which means that del I by del x is equal to I times some function of x, right? So you get I is equal to e to the power integral fx dx, right? And of course you can check for y also. In that case, this is simply mi times my minus nx by n, right? This is the case, okay? How I got this? I got di by I is equal to fx dx. Integrate, neglect the constant, you get ln I is equal to fx dx integral raised to the power e, you get this thing, okay? I've been understanding this. And now if you don't understand this, let's solve it using a problem, so it will be very easy to understand, okay? So let's see it using a question that how the things are going actually, and we will see that how it will be working. Okay, so suppose the question is x square plus y square plus x dx is equal to plus xy dy is equal to 0, right? Of course, if you check originally, this is not of the form. It is not exact. It is not in the exact form, I mean. Okay, you can check also. If you take del m by del y, you will get 2y, and if you take over here, you will get of course they are not equal. It will be y and it will be 2y, so they are not equal. So you have to multiply by an integrating factor. So what you will get is that integrating factor over here, if you take 1 upon n, nx minus, sorry, my minus nx is equal to 1 upon x. If you solve this, just solve it. How? D, it will be equal to 2y, right? This is 2y and this is equal to y. So 2y minus y is y upon y x. Y and y gets cancelled, you get x, 1 upon x. So how did I knew that I have to take this only? Because if I took ny, like if I would have solved for y, then it would have been a different case. In that I would have got nx minus my by m, right, as the function. So in that case, what will I get? I will get negative y upon what is m? M is x square plus y square plus x. So you have to remember that you have to choose like that you have to take my minus ny or nx minus my, so that you get a function of one variable only. That is why I said that time that it is a function of x. Then only we can solve it, else we can't. Okay. So we have the value of the function fx. So now we have integrating factor is equal to e to the integral 1 upon x dx, and it is equal to x simply, right? If you can understand. So just multiply both sides by x, you get x square plus y square plus x dx plus x square y dy is equal to 0. And now it is a differential equation. It is an exact differential equation, right? So now you know how to solve this equation, right? Very simple, very easy, right? Now let's see linear differential equation of, okay, of first order. Yeah. Now we are going to see the linear differential equation, that how do we solve this, and let's see how it goes. First order. Of course, we are dealing with the degree one, so it's fine. So, so dy by dx plus py is equal to, or you can say px into y is equal to q of x. So it is linear in y, and what is meant by linear in x? Dx by dy plus p of y into x is equal to q of y, right? This is the linear in y, and this is the linear in x. Okay, sorry, this is the linear in x and this is linear in y. Okay, sorry, I'm very sorry. So how do we solve this? Well, again, in this case, we can multiply both sides by dx and all, and if you see, you get dy plus px y minus qx into dx is equal to 0. And again, if you solve for the integrating factor, in this case it will come out to be e to the power p dx. Okay, over here m is equal to 1, so in that case del m by del y is equal to 0, of course, and over here when you solve this, you will get your answer. Okay, so it is simple. If you want, you can do it. Okay, so you can take nx and ny. Yeah, it will work. Okay, so now let's see what else can we do. uh, Sorry, over here n is equal to, sorry, n is equal to 1, right? M is equal to this term, m is equal to this, the term with the dx is called m, right? So m is this term and n is this term, so del m by del y will be equal to p. So we got e to the power integral p dx, right? Okay, I'm sorry for that. If I make some mistake while speaking, please neglect that and try to manipulate things on your own also, because it's like it's a one shot, so there are chances that I make some mistakes because it is in one go. There's no pause between it, so that is why. Okay, kindly bear with it. So of course you can solve like this. Okay, so you get, and what is the solution? Solution will be equal to y into integrating factor is equal to the integral q of x into the integrating factor dx, right? You get this, and of course an arbitrary constant. And in this case also you will get the same thing. Okay, just over there we will get x into integrating factor is equal to q of integrating factor dy plus c, and integrating factor in this case will be equal to e to the power p dx, right? This is how the things goes. Okay, and you can work on things, and yeah, it will work. Now equation that is reducible to the linear form, we will see that also, and let's see how it will work. Okay, so let me raise this, then we will see. Okay, so now let's see equation reducible to linear differential equation. Suppose f dash of y dy by dx plus p f of y is q of x, right? So you can assume f of y as t, right? Fine. So you get dt is equal to dfy, and with respect to x, we get, okay. Now what is it? It is equal to f dash of y, and by the chain rule, it will be dy by dx also. It is equal to dy by dx, right? So you get dt by dx plus p t is equal to q, and now it is a linear differential equation, and which you can solve very easily, right? Very simple, very simple. Okay, and now we don't need to see much on it. Bernoulli's theorem, I mean Bernoulli's equation, dy by dx plus py is equal to q by n y to the power n dy by dx plus p to the power y n minus 1 is equal to q, y to the power n minus 1 is equal to x. So we have dx is equal to, I mean, is equal to t. So we have dt is equal to n minus 1 to the power, if you, it is 1 minus n, sorry. You get y is 1 negative n dy by dx. You bring over here 1 n minus 1, you get over here. So we have 1 upon n minus 1 into the quantity, it is 1 minus n, sorry, 1 minus n into dt by dx plus pt is equal to q. Okay, it's like that. Okay, simple. So this is how you get to solve this kind of problem. And now we are going to see solvable for p. What does it mean? We will see. Okay, no need to worry. Let me show you all how it goes. So we are going to see equation solvable for p. Solvable for p. What does p mean? P over here is dy by dx. Okay, remember this. Okay. Now see, it is, suppose question is d y by dx square minus dy by dx minus 6 is equal to 0. So you substitute p square minus p minus 6 is equal to 0. So which means p is equal to negative 2. I mean, you can factor as p minus 2, p plus 2, p minus 3 is equal to 0. So you get p is equal to negative 2 or p is equal to 3. So you get dy by dx is equal to negative 2. You get negative 2. So you get y is equal to minus 2x plus c1, and you get y is equal to, if you substitute over here, you get 3x plus c2. So you can combine the result, you get 3x plus c2 into negative 2x plus c1 is like the equation, the solution is equal to 0, somewhat like that. Okay. uh, y minus this, y minus this is the solution. Okay, let's say like that. Now we are going to see the power, the equation solver for y. This is how you solve for y. Okay, I mean for p. P is just the differential term. Okay, now let's see for y also. How do we solve for y in such cases? Solver for y, then we'll see for x, and then we'll move further. Okay, solvable for y. So in this we have to note that the power or degree should be equal to 1 of y, right? Suppose the question is y is equal to y minus 2px plus xp square is equal to 0, right? We have this thing, and of course p is equal to where dy by dx. We are given this thing, okay? So how we will solve this? We will do 2px minus xp square. We will get this thing. Just differentiate y with respect to x. So we have dy by dx is equal to 2. What is the derivative of x is 1. 2p plus 2x dp by dx minus p square minus 2xp, I mean dp by dx, right? You will get this thing. And of course, what is this? This is equal to p. So we have p is equal to 2p plus 2x dp by dx minus p square minus 2x dp by dx. And of course, can you solve this equation? Well, let's see. Okay, let's see that how we are going to solve this expression. So you get, if you make it like this, p, it will be equal to p times 1 minus p plus 2x into dp by dx. 1 minus p is equal to 0, so you get 1 minus p into p plus 2x dp by dx is equal to 0, and you won't put this as equal to 0 since it don't have any differential term over there, so you'll put only this one as equal to 0. So you get p plus 2x dp by dx is equal to 0, right? And can't you solve this equation? And if you solve this, you will get p is equal to root c by x. Of course, there will be plus minus, but for simplicity, I am assuming it to be plus only. Okay. So to solve for y, you will substitute this value over here. So y is equal to this thing. So when you solve this, you had y is equal to p 2px 2px minus xp square. You substitute the value of p, you will get the value as 2 root xc minus c, right? This is how you solve for y. Okay, this is solvable for y. Now you see for the solvable for x, right? Okay, I hope it's not going too fast, right? Of course, I have to cover it in less time, so that is why I am a bit fast. But I will make sure that you will understand everything, every possible concept over here, right? And please do subscribe my channel, and please like, share, subscribe my channel, and please share it as much as you can. And now we are going to further. Okay. So yeah, so now we are going to see for solver for x. We'll see it using a question. X is equal to p plus 1 upon p, right? Okay. Simply again you will do dx by dy is equal to dp by dx plus dp to the power negative 1 dx. And what's the derivative of t to d of the quantity x to the power n? It is equal to n x n minus 1. So it will be also equal to dp by dx, n will come outside, minus 1 into d 1 upon p square dp by dx, right? Are you understanding that? How is it going? It is very simple, right? Since it is by the chain rule, I have applied the chain rule. Okay, so and what is it? We know that p is equal to dx dy by dx, so we have dx by dy is equal to 1 upon p, right? Okay, which means that 1 upon p is equal to dp by dx p square minus 1 by p square. You can divide, multiply both sides by p, you get this thing. And I am sorry, I made a mistake over here. It will be dy dy. Sorry. dy over here, sorry. So it will be equal to, it's correct, this is dy. So we get dy is equal to p minus 1 upon p dp. So you get the value of y as p square by 2 minus ln p plus c, and this is the answer. Okay, this is how you solve for this is the solving for x. Okay, now we are moving to the other concept of the linear differential equation of higher order but of 1 degree of the first degree. Okay, so we'll see, let me resolve this. So now we are going to see linear differential equation of higher order with constant coefficients. So what is its general form? We can write it like this: d to the power n y, I mean dn by y dxn plus a1 dn minus 1 by dxn minus 1 y, and so on till an y x of x, right? This is your linear differential equation, and we'll see how to solve this one. Okay, a1 a2 till an are the constants, are arbitrary constants. So in this case the general solution is equal to the complementary function, complementary, I'm sorry if my spelling is wrong, complementary function plus particular integral. And how do we see all this? We will see in some time. So before all this, I have to tell one thing, that now we are going to use some operators. You know what is the operator? When you give some input, it will give some output, right? Okay. Suppose over here we will take d is equal to d by dx. It will take the derivative. Okay, it is the derivative operator in this case. So if you take the nth derivative, it will be like this. Okay, this is the operator, and you will apply this operator on a particular variable. Suppose d ny by dxn is equal to d ny, right? And this will be really helpful for our calculation purpose, right? Because we will be using auxiliary equations formed of d, right? So don't worry about those terms, we will see. Okay, so basically we will see first of all what is a complementary function, and then we'll see the particular integral, and then we will solve it further. Okay, let me resolve this. So we are going to see complementary function. So what we are going to do in this is that we will take the original equation dny by dxn and a1 dn minus 1 y upon dxn minus 1 and minus 1 till a and y is equal to 0. I mean, earlier it was equal to x, but now we'll set it equal to 0, right? So it has become a homogeneous equation, right? Okay. So now what we are going to do is that we will solve this. We will get some solution out of it, and then we will, yeah, we will keep those solutions for finding the general solution. Okay. And the particular integral, it states basically that you take a particular solution of this equation, and you do like this: d and v, where v is the particular solution of the given differential equation, dxn plus a1 dn minus 1 v by dxn minus 1, and so on till a and v is equal to 0, right? This is how you, is this is equal to x, sorry, in this case it will be equal to x. Okay, so here you convert it to homogeneous one. Okay, so now let's see that how we are going to solve. But before that, you have to remember that what is meant by linearly independent solutions. Suppose if y1 and y2 are two solutions of a equation of something, then y1 by y2, if it's not constant, then they're called, they're independent, then they are said they are linearly independent solutions, right? So which means, for example, y1 is equal to sin x and y2 is equal to cos x. Of course, they are linearly independent solutions, right? If they are not the constant multiple of each other, right? Okay. So let me see what else I need to teach right now. And you can also represent it using c1y1 plus c2y2 is equal to 0, right? And over here c1 is equal to 0 and c2 is also equal to 0. So for n solutions you can write c1y1 c2y2 till cnyn is equal to 0 and c1 is equal to c2 is equal to till is equal to cn is equal to 0, right? Okay, so this is what is meant by linearly independent solutions, right? But it is of course many times difficult to calculate these kind of variables, so these kind of constants. So we use something called Wronskian's determinant. And how we do it like that? How we do y1, y2 until yn. Okay. If it's not equal to 0, then we say that they are linearly independent. Independent, right? Okay. And how we calculate this determinant? Let's see. Just a minute. Wronskian determinant. Okay. We need to see Wronskian determinant. So Wronskian determinant. W of y1, y2, y3, and so on till yn is given by this determinant y1, y1 dash, y2 dash, sorry, y1 dash, y1 triple dash, so on till y1 n minus 1th derivative, and y2, y3, and so on till yn, right? Similarly, y2 dash, y2 double dash, and so on till y2 n minus 1th dash, and similar is the case with this, and this one also yn n minus 1th derivative, right? This is how you calculate the Wronskian determinant, and if it is not equal to 0, then you say that the solutions are linearly independent, right? Okay. So now what we are going to do is that, yeah, let's take our complementary function equation now. What was that? Let me erase this, then we will discuss it. And I hope that you all are understanding whatever I am teaching. And if you are not, then please to comment me in the comment section that where am I going wrong, so I will improve upon that thing. And of course no one is perfect, so maybe I'm also making many mistakes in this video, but please forgive me for that. Okay, so now we had dny by dxn plus a1 dn minus 1y by dxn minus 1 and so on till a and y is equal to 0, right? Okay. So we know this, and suppose that y1 is a solution and y2 is also a solution, a linearly independent solution. Linearly independent solution. Okay. This is just a short form which I'm using. Don't use this. Okay. So when we solve this, what we get? Yeah. So we substitute y. So we have dny1 by dxn so until a n y1 is equal to 0. And if you multiply by c1 to both equations, to this equation, it makes no difference, right? So you can make constant inside also, so you can write c1 like this also. It's okay? Yeah. And similarly dn y1 y2 c2 so on till a and c2 y2 is equal to 0. Just add these two equations, and what you're going to do from this? Well, let's see. If you add them, what you will get is that simply c1 times, suppose if I name this one as a, capital A, and this as capital B, so we have c1a plus c2b is also equal to 0. And if you know some of the algebra, you can say that d of c1 y1 plus c2 y2 by dx till an c1 y1 plus c2 y2 is equal to 0, right? If y1 and y2 are linearly independent in that case, right? That is why. So basically it means that if y1 and y2 are linearly independent solution, then it implies that c1 y1 plus c2 y2 is also a solution of this equation. And of course if it would have been like n terms, then c1 y1 till cn yn would also be a solution of this differential equation, right? Okay, so where c1 and cn are like they are the arbitrary constant, this is called the general solution of this equation. Now we are going to see the solution of complementary function, which is a homogeneous equation, right? So let's see that how you solve it. Suppose you are given d2 by dx square plus a1 dy by dx plus a2y is equal to 0, suppose, right? What I told about the operators, d2y by dx square is equal to simply d, fine, and like that is equal to d2. So we get d2y plus a1 uh, dy plus a2y is equal to 0, fine. Now just take y outside this expression. So we have d2 plus a1 plus a2 into y is equal to 0. I mean this whole operator is being applied on this y, okay? So, okay, what next? Well, now it will be something illogical because we will be creating an auxiliary equation of it where we will replace m square plus a1m plus a2, where m is a number now, it is not an operator, m is a number, m is a variable, whereas d was an operator, right? Still, the way we factorize this, we can factorize this expression also. For example, d cube plus d square, I mean d square plus 2d plus 1 can be written as d plus 1 d plus 1, right? This is how you do like this, okay? So it is something really amazing that how the things are interrelatable, right? This is known as your auxiliary equation, okay? This is your auxiliary equation, and if you solve it, well, we will see. um, Suppose it has a root of alpha 1 and alpha 2, right? Suppose, so let me erase this and then let me tell further that what has to be done in this case. So we have m square plus a1m plus a2 is equal to m minus alpha 1 into m minus alpha 2, right? We have this. So we can write similarly this also. So we have d minus alpha 1 into d minus alpha 2 applied on y. So basically you are first applying this expression on y, then you will apply this on this complete, okay? So basically there's a first case to solve this equation, right? If alpha 1 is not equal to alpha 2, right? And alpha 1 and alpha 2 are real, right? Okay. So in that case, you can say d minus alpha 1 into d minus alpha 2 is equal to, or applied on y is equal to, suppose, okay, this is something which you will understand in some time. So you can say d minus alpha 1 y alpha 2y, suppose it is equal to 0 in this case, okay? Suppose the first expression is only equal to 0. So you get dy by dx, I mean, let me write clearly. So this is a solution, dy minus alpha 2y is equal to 0, which means that dy by dx is equal to alpha 2y. So it means that dy by y is equal to e to the power alpha 2. So you get y is equal to, I mean, alpha 2 dx. So you get e to the power alpha 2, right? And similarly we can say that d minus alpha 1 can also be equal to 0 applied on y. So from that you can get y is equal to e to the power alpha 1 also. So we get y is equal to e to the power alpha 1 and y is equal to e to the power alpha 2. And when you take the difference y1 y2, you get e to the power alpha 1 minus alpha 2, and which is not a constant, of course, right? So which means that from this you can say that y is equal to c1 e to the power alpha 1 plus c2 e to the power alpha 2 is a general solution. And for nth degree, if there are n solutions, you get y, the general solution is equal to c1 e to the power alpha 1 plus c2 e to the power alpha 2 and so on till cn e to the power alpha n, right? This is general solution for nth degree, for nth order one, right? Degree is one only, right? So this is for the case when alpha 1 is not equal to alpha 2 and alpha is a real value, right? But what happens if they both are equal? So in that case, what we are going to do? Well, let's see. Okay. So for the second case, when we are saying that they are equal, what we will do is that in the case alpha 1 is equal to alpha 2 and alpha comma beta are real or whatever, okay? Let me change the chalk. So alpha and what I have written this, alpha is real, right? So in that case what we are going to do is that yeah, we can say that we can assume them as alpha. So d minus alpha applied on d minus alpha applied on y is equal to 0. We know this, okay? So now what we are going to do is that we will say d minus alpha applied on y is equal to z. Z is some other function, and we will apply this d minus alpha on that z, and that will be equal to 0. This is how we are going to solve this problem, right? Okay, now notice that d minus alpha means, I mean to say that d minus alpha is equal to d minus alpha applied on z is equal to 0 is similar to this case, right? This one, which means that z can be written as c1 e to the power suppose alpha x, right? Where alpha is the value, right? So we can say that d minus alpha applied on y is equal to c1 e to the power alpha x, right? This one, okay? We substitute the value of z over here. Are you understanding it, right? So now you get dy by dx minus alpha y is equal to c1 e to the power alpha x. You will get this. And isn't it solvable? Let's see. Just a minute. So just observe that we have dy by dx is equal to c1 e to the power alpha x, or just leave it, plus minus alpha y is equal to c1 e to the power alpha x. We have this expression. Now notice that this is a linear differential equation, right? It is a LDE, right? It is very simple to solve. It is a linear in y, right? So we get integrating factor as e to the power negative alpha dx, get e to the power negative alpha x, right? And the next thing which you get is that y times e to the power negative alpha x is equal to simply the integral c1, of course, it is c to the power minus alpha x into c1 e to the power alpha x dx. You remember formula, right? That integrating y into integrating factor is equal to the integral q times the integrating factor into dx, right? This is the case. So you get y is equal to e to the power alpha x into the quantity c1 we can take common. So we get this and this gets cancelled. So we have cx, right? And this is it. So we get the value of y as x c1 x e to the power alpha x, right? So do you understand that how the things are going? And if there are and if alpha repeats r times, right? It has repeated for 2 times, right? In this case, if it repeats for r times, then in that case this is equal to c1 x to the power r minus 1 plus c2 x to the power r minus 2 and so on till cr e to the power alpha x, right? This is how. And of course you can solve it using, for example, d minus alpha, d minus alpha, d minus alpha. You can check for 3, then 4 and so on till n. You can check, okay? You get this result only, okay? Is it simple, right? Is it easy to understand? And of course it will be a constant over here also, so it will be basically equal to c1x plus c2 e to the power alpha x, right? Now it's correct, okay? So I hope you are understanding this. So now if we have the case of imaginary roots, then what is gonna happen? Let's see. Well, let's see. So now we see the case of imaginary roots, right? So suppose the roots are alpha plus I beta and alpha minus I beta. So what we are going to do is that we know that they both are independent. I mean, they both are different. They both don't have the same numerical value. So which means that it is the first case of different variables. I mean, what was that? With different values, right? They don't have same values. So it is like this. So we can apply the same concept that y is equal to c1 e to the power alpha plus I beta plus c2 e to the power alpha minus I beta, right? This is how you will write it like this. And of course c can be some imaginary number also now. That is why, okay? So now what we can do is we can bring e to the power alpha is common, e to the power alpha is common. So we have c1 bar e to the power I beta plus c2 bar e to the power negative I beta, and we know the relation that e to the power I theta is equal to cos theta plus I sin theta. So we can just apply this over here. So we get y is equal to e to the power alpha into the quantity. It will be alpha x, of course. This x also. So beta x, alpha x. So when you substitute this, you will get c1 plus c2 bar cos beta x plus I times c1 minus c2 bar sin beta x. Of course, it is a simple calculation. You have to just substitute beta x over here and negative beta x, and then you just add, you will get this result, okay? So what you get is that you can say this as c1 and this as c2. So you get the result as e to the power alpha x into the quantity c1 cos beta x plus c2 sin beta, including I also over here, beta x, right? This is how you solve in the case of imaginary, right? And now what we are going to do is that yeah, if alpha plus I beta and alpha minus I beta are repeated r times, right? They are repeated r times, right? So in that case, y is equal to e to the power alpha x p1 plus p2 x so until pr x to the power r minus 1 into cos beta x plus q1 till qr xr minus 1 into sine beta x, right? This is how you solve. And you can derive it using the first theorem also, that first problem which we discussed when the roots are different and they are real in that case, okay? So basically let's see what we need to do now. Suppose, let's see, we will understand complementary function using a question now. So it will be better for you to understand also. Let's see. So suppose the question states that let me erase this, then we will see. Suppose the question is d2y by dx square minus 5dy by dx plus 6 is equal to 0. So you can write it like this: d2y by d2 minus 5 dy plus 6 is equal to 0, and you substitute m square and you take y common, you get d square minus 5d plus 6 plus, like, sorry, not 6 will be over here, y plus 6 is equal to 0. Is it correct? Yeah, is it? I guess there is some problem in the question. Yeah, it will be y over here then. Yeah, now it's fine. Y. Yeah, now it's correct. There was some misprint in the question. So now you can substitute d as m to create an auxiliary equation. You will get m square minus 5m plus 6 is equal to 0. So you get m is equal to 2 comma 3. So of course you can write this as d minus 2 d minus 3 into y is equal to 0. Either you apply the complete procedure or you write y is equal to c1 e to the power 2x plus c2 e to the power 3x, and that is your complementary function in this case. Okay, this is how you solve the things, right? Is it correct? Yeah. And similarly you can apply for different cases also, right? It will be very similar. Okay, so let's see for the particular integral now. Okay, and don't worry, we will do questions in the last in one of the last videos of this semester, right? I guess in the April, no, not in April, maybe till the March end. Okay, so in that we will do a practice session. In that we will discuss all the tough questions, right? So no need to worry about this. This is videos for basically to improve your concepts and everything, right? It is not related much to the problems, right? To high level problems. Of course we are doing problems, but they are not that high, that much high, right? Okay, so of course if your concepts are clear, then everything is fine. If it is not, then there are problems even if I do hundreds of problems, right? That is the thing. Okay, so just focus on concepts right now, that what is going on, right? Okay, so now we are going to see integral particular integral, right? Okay, so what we had done, that we had fd into y is equal to x, right? Remember this, you had dny by dx n minus 1 plus a1 dn minus 1 y by d x n minus 1 and so on till a n y is equal to 0 is equal to x, sorry. So similar thing which we can do is you can dny plus a1 dn minus y and so on till a n y. So you can take y as common. So we have dn till a n y is equal to x, which means that function of d applied on y is equal to x, right? It is not the multiplication, it is the operator that is being applied on the variable y. Okay, so f of d which is being applied on y is equal to x. So particular integral is equal to 1 upon f of d applied on x, where f of d is just an inverse of this expression. For example, 1 upon f of d is inverse of what? Of this, of f of d. For example, if I said dy is equal to x, which means y is equal to 1 upon d applied on x, which means integral of x dx, right? I will mean this. Okay, this is like this. Okay, so let's see. Let me erase this, then we will see it using some problem, then it will be better. Okay, so let me show you all. Suppose well, if you can write it in general form, f of d can be written as d minus alpha 1 into d minus alpha n and 2 till d minus alpha n. Can we write it like this? Of course we can write it like this if it is a polynomial. If we are using the auxiliary equation of nth degree, then it can be written as like this. Okay, which means that We can say 1 upon d minus alpha 1 till d minus alpha n applied on x, right? So what we are going to do is that in this we will assume 1 upon d minus k, where k is between 1 and n, right? It can be 2, 3, 4, whatever, okay? Applied on x is equal to suppose t, so you get x is equal to dt minus dt by dx minus alpha k t, right? And whatever be the value of x, and of course it is linear in t, so you can evaluate it. It is very simple, okay? So if you try to solve, you will get the integrating factor is equal to e to the power this, and you will get e to the power negative alpha k x. So you get the solution as x, I mean t times e to the power negative alpha k x is equal to the quantity integral e to the power negative alpha k x into capital X dx. This capital X is a function. It is a function of small x, right? Okay. So get t is equal to e to the power alpha k x integral e to the power negative alpha k x capital X dx. This is how you solve it, okay? And then you continuously apply the same thing, okay? I will understand in this, and of course there will be a constant plus some constant, right? So, but in the case of particular equation, we neglect this constant at 0, okay? So that is how you get the equation, right? Okay. So now let's see if we have a problem which we can solve right now. Let's see a simple one first of all, then we will see if we can do some higher level problems too. Let's see. So we are going to see a problem, then we will find its general solution, and then we will be almost done with our lecture, but we have to still see some one or two theorems, and then how to solve linear equations, I mean the ordinary differential equations simultaneously. We have to see that, but of course we won't do much questions related to that because we will see it in the last video in the practice session also. So that is why don't worry about it, just see the concepts, okay? Okay, so let's see the question. It states d square minus 3d plus 2 of the quantity y is equal to e to the power 3x. So we get y is equal to 1 upon d square minus 3d plus 2y 3 to the power e to the power 3x, which is equal to 1 upon d minus 1 d minus 2 e to the power 3x, right? So what you're going to do is 1 upon d minus 2 e to the power 3x is equal to t, which means that e to the power 3x is equal to dt. Let me write it. D minus 2 applied on t. So we get e3x is equal to dt minus 2t. 3x is equal to dt by dx minus 2t. From this, if you solve, you get t is equal to e to the power 3x by 2. And again you will do 1 minus 1 upon d minus 2 d minus 1, sorry, of e to the power 3x by 2, and when you apply you will get set it equal to u now, or you can use t also, there is no issue. 3x by 2 is equal to du by uh, dx minus u, and if you solve you will get the answer as the particular solution means the solution as in this case as e to the power 3x by 2, right? From all this, final result is this only, okay? So let's see if something else we can do. So let's see if we have a general solution question, if we can try doing it. um if we can see some solution, so of course we can do. So let's try to find the general solution of this equation only, okay? Let's see. So we have got the particular integral. We have got the particular integral as what? We have got it as e to the power pi is equal to e to the power 3x by 2. We have got this, okay? And now what we are going to do is that let me see if I have any questions, so it will be then better to see the things. Maybe I don't have right now any question like that. Well, no issue. Um, so this is a particular integral, and what is the complementary function of this? You can simply write d minus 1 into d minus 2 applied on y is equal to e to the power 3x, and of course here alpha 1 is equal to 1 and alpha 2 is equal to 2. So y is equal to, in this case, it is equal to c1 e to the power c1 e to the power, this is your function as it is, but you have to set it, so this is equal to 0, right? So e to the power alpha x plus c2 e to the power 2x. So we have the general solution as c1 e to the power x plus c2 e to the power 2x plus e to the power 3x by 2. This is your solution. You substitute it, it will work, right? If you want, you can check also. You can take the derivative test and it will work. You just substitute it over there, it will come equal to 3x, right? E to the power 3x. Okay, so this is how you solve this problem. And now let's see what else we need to do. um, Now let's see Cauchy Euler equation. Let's see how it goes. Okay, and then we will see Clairault's theorem. Then we will see the solving of differential simultaneous differential equation, and then we will be done. Okay? So no need to worry about anything. It is very simple. Okay. So you remember that how I got the general solution? General solution was equal to the complementary function, whatever you get the result from complementary, then whatever result you get from the particular integral. And in particular integral, you don't have any constant because it is a particular solution. So in that case, you won't get any constant. Okay, that is why. So now let's see Cauchy Euler equation. Cauchy Euler equation, right? Okay. So a linear differential equation, a linear differential equation of the form xn dny by dxn plus a1 xn minus 1 dn minus 1 y by dxn minus 1, so until a n y is equal to x, right? And I hope that you are understanding this, and it is simple, just don't worry about it. And what does it mean is that the coefficients in this case is not a constant value, but they are dependent upon the variable x, right? So they are variable constants. So Cauchy Euler theorem is used to determine the solution in the case of variable constants. Okay, I mean variable, yeah, variable constants, whatever. So let's see, non-constant coefficients, variable coefficients, right? So in this case, we choose a function x is equal to e to the power z, where z is an independent variable, right? Uh, just just a minute. Is independent variable. Okay. So you get z is equal to ln x. So you get dz by dx is equal to 1 upon x. So we have dy by dx is equal to dy by dz dot dz by dx, which is equal to 1 upon x dy by dz. So we have x dy by dx is equal to dy by dz. Do you know this is chain rule, right? This chain rule, okay? If you remember that, okay? So you get this expression first of all, and when you take the second derivative, or you can write it like this also, that it is x d is equal to, suppose d by dx we are calling as d, and d by dz we are calling as d1. Okay, just for simplicity, let me use another chalk. So what we are going to get is that it is equal to d1y, right? This is how it goes. Okay, it is of course applied on y. Okay, so here xd is equal to d1 is an operator, right? Okay. Now you take the second derivative, what do you get? d2y by dx square, right? This is equal to, this is equal to uh, what was the expression? It was this, yeah. It was equal to d by dx of the quantity 1 upon x dy by dz. Okay, and if you solve this expression you get negative 1 upon x square dy by dz plus 1 upon x, right, into d by dx of dy by dz, right? How we get this? Well, how we solve this? We will do dx dy by dz. So first of all, we are going to apply the chain rule, of course. So we, it will be d2y by dx square, I mean dz square into dz by dx, right? And what is dz by dx? It is equal to 1 upon x. So it is equal to negative 1 upon x square plus dy by dz plus 1 upon x square d2y by dz square, right? This is how you approach the things. So you get x square to d2y by dx square. This is equal to d2y by dz square minus dy by dz. So you get x square dy is equal to d1 square minus d1, which means that uh, d1y, which means that x square d is equivalent to d1 minus 1, right? This is d. Okay, this is how you get the function. This is d2, so this is d2. Okay, so let's generalize this expression and let's see that for nth degree what will be the expression. Let's see. So for the nth degree we will have x and d, and using a similar method you will get d1 minus 1 into d2 minus 1, so until d and d1 minus 2 d1 minus n minus 1, right? This is how the things work, right? This is very easy to understand, right? Let me see it. Yeah, I have written correctly. So how will it help us? Let's see. Okay, so let's see it using an example that how it is going to help us. This substitution and this. Okay, so I have an example and we'll see. So let's see that example. It will be then clear. Suppose the question states that x square d minus xd plus 2 into y, right, is equal to x ln x, right? So here the constants are not indeed constant. These coefficients are non-constant, means they are variable. So basically this 2. Okay, so what is x square d2? It was equal to d1 into d1 minus 1, d1 minus 1. Okay, so we have d1 minus 1, and what we have xd, it is equal to d1, it is equal to d1, right? So what else we can do? We can just yeah, now we can substitute the value, and we have e to the power z is equal to y is equal to x, sorry. So we can write it like this: d1 minus d1 minus 1 minus d1 plus 2 times what is y? Well, over here y is equal to, well, let's write y as it is. And what is x? X is equal to e to the power z into z, right? So we have d1 square minus d1 minus d1 plus 2 into y is equal to e to the power z into z. So we have quantity d1 square minus 2d1 plus 2 y is equal to e to the power z. So we have the expression, and now notice that this is just the linear differential equation of higher order, right? And it is easy to simplify, right? You can see that over here you are going to have imaginary solutions, so you know how to solve it, and you know how to solve its particular solution, right? And of course, in the case of particular solution, it will be 1 upon d square minus 2d plus 2 times e to the power z into z, right? This is the case. But now you would be thinking that how to factorize this. Then of course you can do d minus alpha minus 1 upon d1 minus alpha 2, where alpha can be imaginary number also. Who said that it has to be real only for partial fraction, right? Okay, I mean this has to be in multiplication, sorry, right? Do you understand it? Okay. Then apply it on f at z. Apply this on this, then apply this on this. Okay. There are tricks also, I mean some methods which we use generally, but I'm not discussing it right now. We will discuss in the problem session, right? So I hope that you understood that if it is in Cauchy-Euler, you substitute x as e to the power z, then you make this changes depending upon the power, and then you make it look like the linear differential equation in higher order, and then you solve it. Okay, this is the general approach of the Cauchy-Euler theorem. And now one thing which I need to tell is the Clairaut's theorem. Let's see, where is it? Yeah, this is it. So what is the Clairaut's theorem? Let's see. Let me erase this, then we will see it also. And then we will see the simultaneous ordinary differential equation. And I hope that much is the only syllabus. I don't think so that there is anything much more in it. Okay. So let me erase all this. So we have Clairaut's equation. So if we have y is equal to px plus f at p, where p is equal to dy by dx, then the solution of this equation is you replace p with a constant c. It is an arbitrary constant. So y is equal to cx plus f at c. This is the solution of this equation. It is very simple, right? Just in a single step you can do. Okay. Just substitute it with the arbitrary constant c and you get the answer. This is the Clairaut's equation. Okay. Okay. So I think we have done almost everything. Just the thing which is left is the simultaneous linear equation. I mean simultaneous differential equation, ordinary differential equation. Let's see that also how we will do. We will just see an idea, then we will solve the questions in the solving session. Okay. So let's see. Okay. Simultaneous ordinary differential equations. So simultaneous differential equation, in this case it is, suppose you have p1 dx plus q1 dy plus r1 dz is equal to 0, and p2 dx plus q2 dy plus r2 dz is equal to 0, and you are set to solve this differential equation simultaneously. So of course you can solve it using the cross multiplication method. If you remember that if ax plus by plus c is equal to 0 and dx plus ay plus f is equal to 0, then you solve it. Similar is the case in this also. So dx upon the determinant of this quantity, it will q1 r2 minus q2 r1, sorry, dy. You put a negative sign over here, but I'm neglecting the negative sign. It should be p1 r2 minus p2 r2 p2 r1, but due to negative sign it will be reversed. So we will get P2 R1 minus P1 R2 is equal to dz, that determinant P1 Q2 P1 Q2 minus P2 Q1, and we can write it as dx by capital P, this dy by capital Q, and dz by capital R, right? This is how it will look. And here P1, P2, Q1, Q2, R1, R2, P, Q, R, they are the function of x, y, and z. Okay, understood? Okay, so let's see it, understand it using a problem. It is, will be a very simple, right? Let's see. Let's see how we will solve this equation, this problem. This is ODE. So suppose a very simple problem, the simplest one, dx by 1 is equal to dy by 1 is equal to dz by 1. It is very simple, right? So in this case, you will equate these two, then these two. You don't need to equate the third equation, because the third one can be formed using these two equations only. Dx is equal to dy, which means that x minus y is equal to c1, and dy is equal to this one. Dy is equal to dz, which means that y minus z is equal to c2. So one can be dx is equal to dy dz, which means x minus z is equal to c3. But notice that if you subtract these two equations, if you add these two equations, x minus z is equal to c2 plus c1, which means that third equation was contained in these two equations only. So you just need to evaluate these two equations only. No need to evaluate the third one. Okay, are you understanding it? Okay. So now let's see another kind of problem. It is, we are doing just very simple right now, because we are doing the best problems in the problem solving sessions, right? So dx upon x, y, z, and of course it is your duty also to do the problems on your own also, right? It is useless even if I tell all the concepts and you don't practice anything, right? So you have to practice things, of course, but the thing is that don't stress yourself a lot about anything. Okay, life is just like that. Okay, it is like it should be stress free, of course. Whatever you are doing, it should not have any stress on yourself, because you are the priority. Okay, okay, just leave all that. So we have dy by y is equal to dz by z. Okay, no need to equate these three. Okay, so you can integrate, you get ln x by y is equal to ln some c. So we have x is equal to, in this case, y e to the power c1, and in this case y is equal to z e to the power c2, something like that. Of course this is also a constant, this is also a constant, e to the power c. So we can write x is equal to k1y and y is equal to k2y, k2z, sorry. Okay, now there are few methods which we use to solve this simultaneous equation. The first one is said solution by cancellation of variables or variable, right? Suppose dx by yz is equal to dy by zx is equal to dz by xy, right? Equate these two, you get dx by yz is equal to dy by zx. So you cancel z and z, you get dx by y is equal to dy by x. So you get x square is equal to x dx is equal to y dy, and you, when you solve, you get x square minus y square is equal to a constant. Okay. And now when you equate these two, you get dy by zx is equal to dz by xy. So you cancel this, you get y dy is equal to z dz. You solve y square minus z square is equal to c2, c1, and this you can see c2. Now it is solvable. Okay, not solved actually. Okay. So now the second is the use of one What is integral? Integral means solution. To find second, like particular integral, it was particular solution. Okay, understood what is the meant by integral over here. So let's see the second one. I guess it must have been like 2 hours since I started. So the second is use of one integral. Integral, by integral I mean the solution of to find second equation. Okay, suppose dx by 1 is equal to dy by 2 is equal to dz by 5z plus tan y minus 2x. Well, we can first of all solve this equation. You get dx by 1 is equal to dy by 2. So you get 2x minus y is equal to some constant c, or y minus 2x is again equal to some constant c. Okay, suppose this is c dash. So notice that dx is equal to dz by 5z plus tan y minus 2x, right? So notice that y minus 2x is a constant. Okay. So we have dx is equal to dz by 5z plus tan c. So now we can simply integrate it since tan c is a constant now. Earlier it was a variable. Integrate, what do you get? X is equal to ln 5z plus tan c by 5 plus a constant c. You get the answer. Right? Simple? Easy? Okay. So suppose c double prime. Okay, we need another constant. Now we can use multipliers to solve this. Use of multipliers. What does it mean? Well, let's see. Use of multipliers such that the denominator of new fraction is 0. Okay, so if you remember ratio and proportion, in that it was suppose uh, x1 by x2 is equal to y1 by y2 is equal to y3 by z3 by z1 by z2, then it is equal to ax1 plus b y1 plus c z1 is 1, a x2 plus b x2 y2 plus c z2, right? If you remember this thing. Okay, similar we can apply in this case also, right? I have written correctly? Yeah. Similarly, in this case also we can do the same thing. Just what we are going to do is that we will choose a, b and c such that ax1 ax2 plus bx2 plus cx2 is equal to 0, right? Let's see how it goes. Suppose dx by mz minus n y is equal to dy by n x minus lz is equal to dz by ly minus mx. But what is meant by multiplier? Well, here b c is the multiplier. Okay, is the multiplier. Okay, multiplier whatever. So in this case, you have to make the denominator equal to 0, right? So just see mz minus ny plus nx minus lz plus Ly minus mx is equal to 0, a, b, c. Now, what can be a, b and c? So that is where practice is required. So you just see that you have m over here and a z, and you have a m and a x. So what if it was a z over here and it was a x over here? Okay, it will cancel. You have a ny, you have a l, you have a nx. So if it was z and then it was x and here it was y, it would cancel. It means that a comma b comma c is equal to x comma y comma z in this case, just by some manipulations. So it is equal to x dx plus y dy plus z dz dz, and of course when you solve this will be equal to 0 when you substitute x. You substitute x over here, you substitute y over here, you substitute z over here upon 0, and if you set it equal to suppose x dx plus y dy plus z dz by 0, of course since these are finite values, which means that to make it finite this expression must be equal to 0, right? Which means x dx plus y dy plus z dz is equal to 0. Just integrate it. You get x square plus y square plus z square is equal to some constant. And this is how you solve these equations. And of course, there's one more topic in which there's a fourth one also, use of multiplier such that denominator of the new fraction is not equal to 0, but that is something complex. So that is why I will not discuss it right now, since you will get confused. So whatever I've taught till now, just practice questions on it. And I hope that you all enjoyed this video, and if you really like this, then please do like, subscribe my channel, and bye bye, take care. Hello everyone, this is Aditya, and today we're going to study partial differential equations in one shot. But before that, I want to clarify one thing, that I have my flight in like 3 to 4 hours, so that is why half part of this lecture will be recorded on this board and the next part will be recorded on another board in NIT Durgapur. But of course they both will compile in one lecture only, so you don't need to watch two parts, right? But just I want to clarify that the board will change in next half. Okay, so now let's start with the lecture, but for that please do like, share, subscribe my channel, and please support this video. Now let's start. Now what is meant by partial differential equations? Well, if you must have studied ordinary differential equation, then you must know that in that case we study one dependent variable and one independent variable, the relation between them, right? But in this case, we'll be studying about one independent variable and two or more independent variables. So one dependent and two or more independent variables. Suppose z is equal to 3x plus 2y square. Let's assume this, okay? Or simply y square, right? So if I say you to differentiate it with respect to x, then you will get dz by dx will be equal to 3. Why? Because x and y are independent variables. So that is why when you differentiate it with respect to x, then of course y is a constant because they both are independent, right? And when you say dz by dy, you will get 2y, right? Correct? Why? Because with respect to y, x is a constant, right? Because they both are independent. So instead of writing d, we use a term del z by del x is equal to 3 and del z by del y is equal to 2y. And this is the basic introduction of partial differential equations, basically how we solve such kind of things and how we form them, right? Of course, we will dealing with more. This is just an introduction that what is meant by it. Okay. So basically, these are the functions that z is a function of x and y, of course, right? Correct? Okay. So it tells that it tells the gradient with respect to x and it tells with respect to y, right? So that is how we solve, means this is how we represent the functions, right? So of course we are going to see further that how we solve them and how we form them, right? This was the basic introduction that why, that what is meant by actually these partial variables over here. Okay, so this is the dependent, this is the independent, this is also the independent variable. So you can have multiple such independent variables in this case, for example x1, x2, x3, and so on and so forth, where x1, x2, x3 all are independent variables, right? Understood? Okay, so let's erase this and let's move into the definitions. Now let's write some definitions that a differential equation which involves partial derivatives derivatives are called partial differential equations. Well, it's simple. We know what is a differential equations, right? We know we studied in ordinary differential equation. You can check that video, right? So which involves partial derivative, that is del z by del x or del z by del y and so on and so forth, right? Such derivatives, if they are involved, then it is called a partial differential equation, right? Okay. Now, yeah, there can be many examples. For example, x del z by del x plus y del z by del y is equal to z, right? And suppose let's take some examples to understand some concept. We will discuss it just a minute. Okay, and another example we can take del 2z by del x square plus del 2z by del y square is equal to 0. And suppose del 2u by del x del y is equal to del u by del z whole cube, right? Okay, so why did I give three examples? I could have just given one example to explain it, because I needed to explain something called order and degree of a partial differential equation. Correct? Okay. So basically it is it is the order. Of course, you know what is meant by order. You have studied in ordinary differential equations, right? You can check that video if you don't know that. Okay, of highest derivative, highest ordered derivative. You can say ordered derivative, and it is the degree of highest ordered derivative. So let's understand it using this example. So in this case, we can see that it is just del z by del x and del z by del y. So it means that only one times this is involved, this operator. So we say that its order is equal to 1 and its degree is equal to 1. Why? Because there is no power involved, it's just one power. Of course, this is raised to the power 1, raised to the power 1. Simple? Okay. Now see this, in this we have second order, this 2 and this 2 and this 2 and this 2. So it is order 2 and degree is 1 because it is raised to the power 1. Correct? Okay. Now notice one thing, that in this case order is equal to 2, but many people get confused that degree will be 3 or 1. So the degree we have to take of highest order derivative, so it will be equal to 1, right? So this is the basic introduction of partial differential equations, and let's move further and let's see some other concepts to enhance our knowledge, right? So let's see something called standard notations in derivatives in partial differential equations, right? Let's see. So standard notations, let's see what is meant by it. So suppose if z is a function of x comma y, means it is dependent upon x and y. So in that case, del z by del x is called p. Del z by del x is called p. Suppose z is equal to x square plus y square. So del z by del x will be equal to p is equal to 2x. Correct? Simple. And suppose del z, and let me write it next line, right? In next line. So del y, it is called q. So del z by del y is called 2y, right? It is equal to 2y, right? Simple. Basically x is constant with respect to y, so it is equal to q, right? Correct? Okay. Now there's something called del 2 z by del x square, which is equal to r, and del 2 z by del y square, which is equal to t, right? And I should write it in sequence. So del 2 z by del x del y is called s, and del 2 z by del y square is called t, right? Simple. So basically take the second times derivative of this quantity. So basically it is equal to del p by del x, and this is equal to del q by del y, correct? Okay, so understood this? Simple. Okay, so basically what we are going to do is we will apply these notations frequently in next problems, so we should remember them. Okay, these are some of the standard notations basically, right? So it is not necessary to remember them, but in questions it is important, right? So it is just a notation, if I say in simple words. So del z by del x is called p, del z by del y is called q, del 2z by del x square is called r, and it is also equal to del p by del x, right? Simple. Okay, so this is how we write such expressions, right? Okay, so let's move further. Now let's see how we formation of partial differential equations. So let's see how we form partial differential equations. So well, there are two methods in this case, by elimination of, let me write it like this, elimination of first arbitrary constants and second arbitrary functions, and we'll see them, right? So let me explain it. Suppose first of all, let's see arbitrary functions, I mean arbitrary elimination by arbitrary constant, right? So suppose there's a function f of x y z a b is equal to 0. We have such kind of function, so where x y are independent variables, z is a dependent variable, a and b are constants, right? So a and b are constants, a b are constants, right? You should remember this. Okay, so in this case, when you differentiate this expression, suppose with respect to x, right? So when you will differentiate it with respect to x, then you will get del f by del x plus del f by del z dot del z by del x is equal to 0. It is with respect to x. Now I know that there must be a question that why I did this. Well, I recently made a video regarding this, but if you don't know that video, if you did not watch that, then in that case I can explain you that z is a function of x itself, of course x and y. So if z is also a function of x, so it means that we have to apply chain rule in this case. Simple, understood? So that is why we had this expression, then we had this expression, right? Basically, if you have zx plus y is equal to 0, if you take its derivative, then it will be del f by del x plus del f by del z plus, I mean, into del z by del x. Simple. So when you take its derivative, this is z, this is z. So you can just write it like when you take its derivative with respect to x, you get z plus del f by del z, it will be equal to x into the quantity del z by del x, which is equal to, again, x is equal to 0. Correct? Simple, right? Correct or not? Correct? Yeah. Sorry, del z by del x. It's right. Sorry. Okay. So understood this thing, right? And yeah, you can do it like that also, like zx derivative, it is equal to, of course you can take its derivative easily. It will be z plus x del z by del x itself. Very easy, right? Simple. Correct or not? Correct? Yeah. So this is the expression z plus x del z by del x is equal to 0, and we get from this expression itself, right? If you don't understood this part, then you can watch my that video in that I've explained it in bit detail. Of course, it's one shot, so I could explain this much only. And if you want to learn more, it's just a 10 minutes video. You can watch that. Okay, I will put its link in description, right? So basically, this is the concept. Okay, and now let's differentiate it with respect to y, right? So let's see what we get then. So it will be del f by del y plus del f by del z dot del z by del y is equal to 0. It is with respect to y, correct? Understood? So it was with respect to x and it was with respect to y, right? So clear. Again, z was a function of x and y both, so that is why we had this expression also. Simple. Okay. So but I told this much. How can we do actually? I mean that we solved this much part, so what else we need to do? Well, we need to just eliminate a and b from this, and notice one thing, that this is equal to q and this is equal to this is equal to this is equal to p, right? Correct. Okay. So when you eliminate a and b, you will get the equation, you will get the expression form of f of x, y, z and p and q, probably a different function, suppose phi, right? And this is the differential equation, which is required partial differential equation, right? Simple. Okay. So now let's do a problem to understand this concept, but we need to know one thing, that the number of arbitrary constant, if they are equal to the number of independent variable, then in that case it is a first order differential equation. Of course, in this case a and b, there were two variables, two arbitrary constants, I mean, and there were two independent variables. So in this we got p and this expression in terms of p and q. So if we got in terms of p and q, so p is also first order and q is also first order, right? Okay. So of course this is a first order differential equation. But if number of arbitrary constants is like greater than number of independent variable, then it is second order or greater than second order, right? Okay. So this was the basic introduction. Let's solve a problem. So let's see a simple example, that z is equal to ax plus by plus ab. It is a very simple example. So in this case, del z by del x, what it will be equal to? It will be equal to a, and del z by del y, it will be equal to y. It will be equal to b. Correct, right? So just substitute this over here. You get z is equal to x del z by del x plus y del z by del y del y plus del x, I mean del z del x dot del z by del y, right? So it's a first order partial differential equation, right? Very simple, very easy. Let's see another problem also, and it is a bit typical, so let's understand it, right? So x square by a square plus y square by b square plus z square by c square is equal to 1, right? So how we are going to solve this kind of problem? Well, it's very simple. So let's differentiate it with respect to x. Differentiate with respect to x. Let's do this and let's see what we get. So we get 2x by a square plus it will be 0 plus 2z by c square d del z by del x is equal to 0. Simple. Okay. And of course 2 and 2 will get cancelled. Okay. So we get x square by a square and this by c square. Simple. Understandable? Okay. So now with respect to y, we will get similarly y by b square plus z by c square del z by del y, right? This expression. Now we need to use this expression and this expression to do something, right? But we know that here we have three variables, three arbitrary constant. I mean we have three arbitrary constants. So it means that it is greater than the number of independent variables, that is 2. Hence it will be second order or greater than that. So of course we need to differentiate one more time. So let's differentiate this expression with respect to x again. So we get in that case it is equal to 1 upon a square plus 1 upon c square. Now when we differentiate it, what will we get? We'll get del z by del x whole square plus z del 2z by del x square is equal to 0. Wait, let me tell you. Z del z by del x, del by del x. We are applying this operator on this given variable or a function. So we'll apply the product rule in this case, right? So we'll get del z by del x into the derivative of this quantity. It will be del z by del x, of course whole square, plus z times the derivative of this expression. We get del 2z by del x square, and this is what is required. Correct? Simple. Okay, right? So when you solve this expression, you get c square by a square plus this expression is equal to 0. And when you solve this expression, you will get what? You will get c square by a square plus z by x del z by del x is equal to 0. Correct? We got this expression. Simply we just divided by x both sides and we multiplied c square both sides, right? So of course we did not need this expression actually, but still we solved it. So from this we can say that this expression c square by a square is equal to negative z by x del z by del x, right? Now we can substitute this expression over here. So we get negative this quantity del z by del x, we get this expression plus del z by del x whole square plus z del 2z by del x square is equal to 0. And this is the required partial differential equation. It is of second order actually, right? And what is its degree? It is the degree is 1, right? Simple. Okay, so now we solved the problem with respect to first order and second order. So of course that is what is required in this. Okay, so now let's move to formation of partial differential equation by elimination of arbitrary functions. Let's see that. So by elimination of arbitrary functions, right? So let's assume a function, let's assume that z is equal to a function of u, where u itself is a function of x, y and z, right? So where f of u is an arbitrary function of u, and use this expression. So when you solve for del z by del x, you will get del f by del x plus del f by del u dot del u by del z dot del z by del x. Why? Because again here it's the chain rule simply, right? Why? Since this is a function of u, so with respect to u itself is a function of z, so that's why we have a z, and z itself is a function of x, so we went to that level, basically like that. Okay, so this is the chain rule. Basically you can watch my that video, that 10-minute video, in that you will understand it better, right? I've explained that. And similarly del z by del y, it will be equal to del f by del y plus del f by del u plus del u by del z dot sorry, it will be a dot over here del z by del y, right? Simple, this expression. And from this you have to eliminate arbitrary function, which we will understand in a few seconds when we see example, right? Okay, so one thing to be noted over here is that order is equal to the number of arbitrary function eliminated, right? Correct. Okay, and one more thing I forgot over here, it will be del u dot del u by del x, sorry, it will be del f by del u dot del u by del x, sorry, this I forgot this del y. Okay, yeah, this one, because again we have to apply chain rule. Okay, so we're right, simple, understandable, right? Okay, so you can watch my that video in that I've explained it clearly. Okay, so let's move further. So let's see a question that z is equal to a function of x square minus y square. So this is a function which we need to means over here basically u is equal to x square minus y square basically, right? So in this we have to form a partial differential equation. So let's see how we'll form using, so where f is the function of u with respect to, where f is an arbitrary function of u, right? Basically, right? So we get z is equal to f of u, so we get del z by del x is equal to the quantity del f by del u dot del u by del x plus the quantity del f by del u dot del u by del z dot del z by del x, right? Now notice that in this case del u by del z is 0. Why? Because you can clearly see from here because del u by del z will become 0 since there is no z in that case. So this expression is equal to 0 in this case, right? So we get del z by del x is equal to del f. Now del f by del u, del f by del u dot dot del u by del x, it's 2x. Simple. Okay. Now similarly, del z by del y, you can apply that formula in that you will get del u by del z is again 0. This expression is already gone. So del f by del u dot negative 2y. Simple. You can solve it on your own. Now let's just divide these two expressions. We get del z by del x divided by the quantity del z by del y is equal to negative x by y. So this is p, this is q. So we get p by q is equal to negative x by y. Correct? Simple. Okay. So this is how you solve such kind of expressions. And yeah, there's one more problem which I had discussed before, like z is equal to f of x plus it plus g of x minus it. You can check out that video. In that I discussed this problem. So there are two arbitrary functions. So it will be partial differential equation of second order, right? Because we have to eliminate two arbitrary functions in this case, f and g. There are two arbitrary functions of these two variables. Of these two means x plus it and x minus it, right? Okay. So let's move further. Now let's understand solution. Solution of partial differential equation. So let's see that how we solve a partial differential equation, and of course we have to understand many things in this. So we'll go in a sequential order. First we'll study Lagrange method. Basically I will tell. Okay, don't worry. Okay. So first of all, let's see that how do we solve a first order partial differential equation. But first of all, let's see its form. We have seen it is x, y, z, p and q, right? This is a general form of a first ordered partial differential equation. Simple. Okay. So now let's understand. So it is just the reverse of that, or the yeah, that is just the reverse. Let me explain. So if you are solving for you are finding its solution, so its solution will be f of x, y, z, maybe some phi, you can say a comma b is equal to 0, right? Where you just replace p and q with some constants which you need to find first. We will see it. So x, y, and z are the variables. X, y is the independent variable. Z is the dependent variable, and b are the constants. Simple. Okay. So this is how you solve it. Basically, we will understand this in some time. This is just some theory which I'm telling. Okay. So yeah. Okay, that's it. And the solution of print form. What is the particular integral solution? Pi. Well, in this reference, it's something different. So basically, when you substitute some value for x and y, and you get some answer in that case, so in that result is called particular solution, basically. But you don't need to worry much about that. Okay? Basically, when you are set to evaluate at when x is equal to 1 and y is equal to 2, that case, right? Basically, that yeah, phenomena. And general solution, basically general solution is like that. Okay. So specified function uv, yeah. So that is not much required, that I will tell in later part. Okay. So let's see a problem to understand this concept. So we are given that proof if u1 and u2 are the solution of the quantity del 2u by del x square plus del 2u by del y square plus del 2u by del z square is equal to a del 2u square u by del t square plus b del u by del t, then c1 u1 plus c2 u2 is also a solution. Well, let's see it. Basically, it is the linear combination of these two functions, these two solutions, u1 and u2, right? So first of all, let's substitute u1. You get del 2 u1 by del x square plus del 2 u1 del y square del 2 u1 del z square is equal to a del 2 u1 del t square plus b del u1 by del t, correct? Simple. And you substitute u del 2 u2 by del x square plus del 2 u2 del y square plus del 2 u2 by del z square plus a del 2 u2 by del t square plus, I have written plus over here, it is equal, plus b del u2 by del t, correct? Okay, now basically multiply both sides by c1. In this case, c1 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 c1, right? Correct. Here c2 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 c2, correct, right? Now there's no harm if I bring c1 over here, correct? And similarly I can do with all the expressions, and in this also I can do like this, and I can simply add these two expressions. So will it make any sense? Well, we have to prove this only, so we can't do like this. Okay, so that is where we lose marks. I say many people ask that this is correct, then why it was said wrong? Basically you need to prove that expression. So how can you say that yeah, I can bring c1 over here so it's correct? No, that's wrong. Okay, so now let's assume that this is the solution of the given differential equation. So we get del 2 of the quantity u1 c1 u1 plus c2 u2 by the quantity del x square plus del 2 c1 u1 plus c2. Let me solve this one first so you will understand the rest on your own, right? So basically you just expand this expression, so you get del 2 c1 u1 divided by the quantity this expression plus the quantity del 2 c2 u2 del x square. Now c1 and c2 is constant, so you can bring them out, yeah, like this. So it means that you just multiply over here, and when you add you will get this expression itself. So it means this is equal to this quantity, right? Hence the linear combination is also the solution of the given differential equation of these two, which has these two solutions u1 and u2, right? So of course if there are n solutions, the n linear combination of these variables will be the solution of this differential equation, right? Correct. The linear combination of these solutions, right? Okay. So understood, right? Okay, so now let's see Lagrange's linear equation, how we solve them. Let's see that. So linear partial differential equation of first order, which is often referred to as Lagrange's linear equation, right? We will see it, don't worry. Okay, linear equation, linear equation, right? Okay, so before that we should know that what is meant by a linear differential equation. This is the linear differential equation. So basically if dependent variable and its differential coefficient, right, occur only in uh, in the first degree and not multiplied together. Yeah, they should not be multiplied together and not multiplied together, right? Okay, correct. So it's called a linear differential equation. And what is partial linear differential equation? Well, if dependent variable z and its derivative remember this, if the dependent variable z and its derivative occur only uh, r of basically r of degree 1 and product of z and its derivative not involved. Basically this definition only, but here we have specified a variable z. That's it. Okay. And what is a homogeneous partial differential equation, right? Okay. So if in a partial differential equation each term contains what I'm writing contains the dependent variable, right, or its derivative, then such PDE or partial differential equations is called a homogeneous partial differential equation, whatever you want to say. Okay. So these are some of the definitions which you won't be tackling, I know it. So most of the problems which you will see, it will just based on like the mixture of these kind of things. So you don't need to worry much about the definitions. But of course, for conceptual purpose, you should know the definition, right? So what is the linear differential equation? What is the partial differential equation? What is the homogeneous partial differential equations, right? So what is the this? Each term contains the dependent variable or its derivative, then it is called this. Okay, simple. Dependent variable is necessary in this case. And what is linear partial differential equation of first order? Now that's something interesting. Let's see. So of first order, sorry, first order. Now if it's of first order, then it is of the form, I mean, a partial differential equation of first order is of the form this P and Q, right? PQ. So it means that in this also P and Q will play a great role, a significant role, right? Okay. So let's define it. So this is the first order, and so in this case, P and Q must only appear in derivatives, and they must not be multiplied together, right? Correct. And of course, the basic definition of linear differential equation, it must follow the partial linear differential equation, right? That z and its derivative should not be in product and something like that. Okay. And of course, P and Q must not be in product, right? Correct. Yeah. So now let's see something called quasi linear partial differential equation, right? Let's see what is it. Okay. So basically it is a non-linear partial differential equation if I explain it in simple words, right? So if degree of highest ordered derivative is one and no product of partial derivatives of higher are present of higher order are present, correct? Okay. So basically you don't need to worry much about the definition. Basically it is something called basically it is a non-linear partial differential equation, right? If I explain it right. Of course there are some differences, but we don't need to worry right now. Okay, when we will solve problem we will understand it, right? Don't worry. Okay, so these are some of the definitions. Let me see that is there any definition which is left. Probably no. So let's move to the next part. Now let's see something called Lagrange's linear equation. Let's see. Okay, so general form of a quasi-linear partial differential equation which we studied, it is of the form P x y z P, where P is equal to not capital P, this P, capital P is a function, and P is equal to del Z by del X, right? Okay. Plus Q of X, Y, Z, Q is equal to R of X, Y, and Z, correct? Okay. So where P, Q, and R is linear in Z, so if P, Q, and R is linear in Z, then equation becomes linear partial differential equation, right? And of course, notice one thing, that in this case P and Q, it must be independent of Z. Why? Because of course if they will be dependent upon Z, then in that case it will be Z times P, right? Z times P. So in that case, if it is Z times P, then, so basically, let me write it, reframe it. If P and Q are independent of Z and R is linear in Z, then the equation becomes a linear partial differential equation. How? Because again, if it is dependent upon Z, then it will become Z times P or Z times Q. So of course, then it will be non-linear partial differential equations. Is the product of the dependent variable and its derivative must not be involved, right? So hence it must be independent of Z, this P and Q, and R must be linear in Z, right? Of course, R can be a linear function in Z, right? Simple. Okay. So, right. Now let's see how we solve such kind of equations. Let's see. Okay. So such equations is obtained by eliminating arbitrary function. Let's assume phi. For now, let's assume it, right? Then we'll see it using examples in a better way, right? From phi of u comma v is equal to 0, right? Where u and v, they are the known functions, of x, y, and z, right? So basically we have to define an arbitrary function which is the function of u comma v, where u and v are itself the function of x comma y comma z, right? So don't worry about it. We will see in examples that yeah, that is not even required. It is only required for derivative, and of course you need to know a function, an arbitrary function, to solve this equation. Of course, we form a differential equation using the elimination of arbitrary function. So of course we'll solve it also using that. Okay, that is the basic concept. Don't worry about it. Now let's see how we solve that kind of equation. So we know something called Lagrange's auxiliary equations. So of course that is Lagrange linear equation, and now we are going to solve Lagrange auxiliary equation. That is, we had phi of u comma v is equal to 0. We had this expression, remember, from that. Okay, so we are going to solve now Lagrange linear equation using something called Lagrange's auxiliary equation, right? So let's differentiate it with respect to x and y. So when you differentiate it with respect to y, first of all, let's do it with respect to x. You get del phi by del u times the quantity del u by del x plus del u by del z times the quantity. Basically, if you don't understand this, let me just write it. So del phi by del u dot del u by del x plus del phi by del u dot del u by del z dot del z by del x is equal to 0, right? Correct? But remember, this is for this expression for u. We have to check for y, for v also, since it's the function of u and v. So del phi by del v dot del v by del x plus del phi by del v dot del v by del z dot del z by del x, and it must be equal to 0. Why? Because we had it is equal to 0, simple, right? So this is just a chain rule and some sort of product rule which we applied, but you don't need to worry about it. You can understand it using chain rule easily, right? since phi was a function of u, so we had done chain rule over here, and now use itself is a function of z, so that is why we have del z by del x, right? Let me see that is it correct or not. So yeah, it is correct. And yeah, instead of del z by del x, you can write simply p, and over here, sorry, it will be, yeah, over here also you can write it p, right? Simple. Okay. Now with respect to this, with respect to x, we differentiate it, and when we differentiate with respect to y, we get del by u, del u by del y plus del phi by del u dot del u by del z dot del z by del y plus del phi by del v dot del v by del x plus del phi by del v dot del v by del z dot del z by del y is equal to 0, and it is with respect to y, right? And of course this is equal to q. Of course del z by del y was equal to q, so let's substitute that. Okay, so this is how you basically, this is the expression when you differentiate this expression. Okay, so let me check, is it correct? Yeah, del u, this is del u, remember I had written it like v. Okay, yeah, that is correct. Yeah, this expression, sorry, this will be y, forgive me. Yeah, it will be y, sorry. Okay, so this, okay, so from this you have to eliminate pi. Remember in the elimination what we had done, elimination of arbitrary function, we have eliminated a function. So here this was the arbitrary function, so we will eliminate phi in this case. So we have to eliminate in this del phi by del u and del phi by del v, right? So when you eliminate this, what you will get is that when you solve it, you will get this expression. Of course, you can solve it on your own. This is just an equation. You can assume basically you can assume this as variable and this as variable, this one, and then you can solve for x. Maybe you name it as t1 and this as t2. You solve for t1 and t2, and when you solve them, you will get this expression. When you eliminate these two expressions, what you will get is that del u by del y dot del v by del z minus del u by del z dot del v by del u del y, correct? Yeah, times p plus, basically I've eliminated this and this, and after eliminating them I'm getting this equation, right? So we get del u by del z dot of course I'm not solving this equation, I'm not eliminating this, you can do it on your own because it will take unnecessary time, which you can do easily, right? Minus del u by del x dot del v by del z q is equal to del u by del x dot del v by del y minus del u by del y dot del v by del x, whatever, right? This is the expression. Now this is something, this is p, this is q, and this is r. So p, p, q, q, and is equal to r. That was a Lagrange's linear equation, right? Remember, just few seconds ago we had just, I mean, few minutes ago we discussed that. Okay, that is what we need to remember right now. Now, how to determine u and v? Well, now that's something interesting. Let's see that. Okay, now just remember this expression if you can, or just note it down, so if it is required we can see it in next part, right? So let's see it further. Now how to determine u and v? Well, now that's an interesting question. So there's a method to solve this. Let's see it. Let u is equal to a and v is equal to b, right? Where a and b are constant. So of course we had taken just randomly u and v, so that is why we assumed it as constant, because a constant, if it is a constant, then it is very easy to solve because its derivative will always equal to 0. So that is why it is very much easy to solve using a constant. So why not? Okay. So we had this expression that well, you know one thing, that du is equal to del u by del x into dx plus del u by del y dy plus del u by del z into dz, right? This is the complete derivative basically, okay? So basically this is how you do it. And similarly you will have dv is equal to del v by del x dx plus del v by del y dy plus del v by del z dz, right? This will be also equal to 0 and this will also be equal to 0, right? Okay. Now when you cross multiply these expression, so you will get dx by del u by del y dot del v by del z minus del u by del z dot del v by del y, right? Basically you must have studied cross multiplication method in solving a linear equation. So basically that's what I'm doing over here. And just this is solving for dx dy dz, right? Is equal to dy by del u by del z dot del v by del x minus del u by del x dot del v by del z is equal to dz by del u by del x dot del v by del u minus the quantity del u by del y dot del v by del x. Now just rewind this video and go to the section where I had written P, Q and R. This was P, this was Q and this was R. If you have written in notes, then good. If you have not, then just rewind this video. You will see that this was P, this was Q and this was R. Right? Okay. So dx by P is equal to dy by Q is equal to dz by R. And it is now very easy to solve such kind of equation, right? Simple. So understood that what we are going to do. Okay, so yeah, from this we get this expression, right? So we got this. Okay, so what's next? Well, let's see a problem to understand this. Okay, so let's solve this question that pz minus qz is equal to z square plus x plus y whole square. Simple. Okay, so we can write it like p minus q, or basically you can write over here that p is equal to z and q is equal to negative z and r is equal to z square plus x plus y whole square, correct? Okay, simple. So we have dx by what quantity? Z is equal to dy by negative z. Dy by negative z is equal to dz by z square plus x plus y whole square, correct? Now just equate these two expressions. So dx is equal to dy z negative z and z gets cancelled, so it is equal to negative. So we have del dz plus dy is equal to 0. Just integrate this expression, so you will get x plus y is equal to some constant a. Now notice this expression that you have dx by z is equal to dz by z square plus a constant a. So you have dx is equal to z by z square plus a square, dz multiply by both sides 2. Now just integrate this expression. What you will get? 2x is equal to the natural log of mod of z square plus a square plus another constant b, right? Okay. So you got this expression, you got this expression, right? So instead of a, you can substitute that, and so we can get from here that we can say we can solve for b from there. So we get the expression phi. Now of course, why I'm writing phi? We have got the result. Then why I'm writing phi? Because a and b are constants. Remember, a and b are constants. So b is equal to natural log of z square plus a square, that is x plus a, minus 2x. Now we assume that the solution was phi of u comma b, but u comma b was a comma b. A comma b is equal to 0. So the solution is this expression x plus a, x plus y, sorry, x plus y is equal to a comma, the natural log of z square plus a square plus, x plus y whole square minus 2x is equal to 0. Correct? Now understood, this is the solution of the given equation. Now phi is an arbitrary function of u and v or a and b or this expression. So you can define any function, it will satisfy this. And that's the beauty of partial differential equation. Ordinary one, you did not got many solutions, but over here you can have infinite solutions also. Simple, right? Okay. Now let's see how we solve non-linear partial differential equation of first order, and we are going to see standard forms, right? Standard forms, okay? Like the forms like so basically, let's see a partial differential equation which involves first order partial differential p in q. That is just basic definition, right? Of course, you know what is meant by linear partial differential. A non-linear partial differential is the one which is not a linear partial differential equation, right? Simple. And that is how you answer in your vibe also, right? We all answer like that. A non-linear partial differential equation is a partial differential equation which is not linear, right? Okay, you leave that. So, why I'm writing solution? Okay, so what are the standard equations? The first one is f of p comma q is equal to 0, right? And the second one is z is equal to px plus qy plus a function of p comma q. Third one, f of z comma p comma q is equal to 0. And fourth one is f1 x comma p is equal to f2 y comma p, right? Okay, don't worry. So these are some of the standard forms which we are going to solve, right? So we are not going to solve it like for a general case, but for these standard forms, and we are going to see Charpit method in maybe in the next part of this video, which I have recorded in NIT, because probably there's very less time now. So that is why I will stop this lecture, means this one, after maybe I complete this part, okay? And then I will record the second part in NIT itself, right? And then I will club them together and I will upload it, okay? So don't need to worry, I will make two parts. No, not like that, okay? So let's start with this. So let's see the first form, f of p comma q is equal to 0. So in that case, solution is z is equal to ax plus by plus c, right? Where now here there are three arbitrary variables. So is it wrong? No. Where f of a comma b is equal to 0. So from this you will get an expression for means a relation between a and b, right? So instead of three arbitrary constants, you'll have only two arbitrary constants, right? Okay. So right, okay. So instead of this, if you solve, you will get like b is equal to some phi of a, right? If you solve this expression, so instead of this, you can write phi of a, right? Simple. Okay. So let's see. Let's see a question. Suppose root p plus root q is equal to 1. Very simple question. Solution z is equal to ax plus by plus c, right? Now we have to substitute a and b, so you get root a plus root b is equal to 1. Correct? So you get b is equal to 1 minus root a whole square. You get a plus 1 minus 2 root a, right? Substitute it back, you get z is equal to ax plus a plus 1 minus 2 root a y plus c, and that is the answer, right? Simple. Okay, now let's see a question which is like reducible to this form. Let's see that one also. Now let's see this question. It is like reducible to this form. Let's see it. Y minus x into the quantity qy minus px is equal to p minus q, right? Whole square. So of course you saw y and x in this, so you thought no, it is not of this form, but actually it can be converted. Let's see how, right? So basically there's some substitution which you have to do in this. X plus capital Y is equal to, or I mean small x plus y is equal to capital X, and xy is equal to capital Y. Let's do the substitution for now, right? So when you do this, you will get del z by del x is equal to del z by del capital X dot del capital X by x plus del yeah, that's it. Why I'm writing further, right? So yeah, plus del z by del y capital Y dot capital Y by capital small x, right? Since y is also a function of this, so that is why we have to do this also. So basically it turns out to be equal to what? Del z by del capital X plus y del z by del capital Y, right? Okay. Similarly, del z by del y is equal to del z by del capital X dot del capital X del y plus del z by del capital Y dot del capital Y by del y. Simple. And this is equal to what? This is equal to, well, simple. It is equal to, we can solve it, right? So you will get del z by del capital X plus x del z by del y. Simple. Okay. Now, what is the value of y minus x in this case? Well, we will solve all this. So what is it equal to? It is equal to p and it is equal to q, right? Of course, del z by del x is equal to p and is equal to q, right? Let's substitute this value. So y minus x as it is, right? Now q times y, q times y means y times this expression. So y del z by del capital X plus xy del z by del y, right? This is qy minus x times x del z by del x plus xy del z by del y is equal to the quantity is equal to p minus q. P minus q, it is equal to y minus x whole square into the quantity del z by this quantity, basically del z by del y capital Y whole square, right? Okay. So this expression gets cancelled. So you have y minus x whole square. Just do a little bit of maths over here. You will see yourself is equal to y minus x whole square del z by del y whole square. This and this gets cancelled, right? Okay. Now this is suppose P1 and this is Q1, right? Let's assume it. So P1 is equal to Q1 whole square. This is again of the form f of P1 comma Q1. That's it, right? Or P comma Q. So again you get the answer as Z is equal to A capital X plus B capital Y plus C, right? Where f of A comma B is equal to 0. So we get yeah, whatever. So you substitute the value A is equal to B square, right? So you can say B is equal to root A, maybe, right? Z is equal to root, I mean A. What is the value of X? Capital X? Well, from these two you can solve for the value of capital X, right? Whatever you get the value plus root A, whatever you get the value of capital Y from this, I mean capital X is simply X plus Y, what I'm saying. Yeah. And capital Y is simply XY, right? XY, right? Plus C, right? Okay. Simple. So this is the answer, required answer, okay? Right, so it's correct also. Yeah, maybe. Okay. So x is equal to x plus y and y is equal to xy. Yeah, correct. Okay. So these are you solve the reducible problems, right? In this form. Now let's see the second form. Okay. Now the second form is z is equal to px plus qy plus a function of p comma q. Okay. Now the solution in this case is z is equal to ax plus by plus f of a comma b. Correct? Now let's see a question. Right? Okay. So it is very simple now, right? Z is equal to ax plus qy plus a plus by plus root 1 plus a square plus b square. Simple. That is the answer. This was the function. We substitute a and b in place of it. We got the answer, right? Now let's see a reducible problem, reducible to this form. Let's see that also. Okay, so it's a simple problem. Just you need to do some sort of manipulations. Of course, the solution was ax plus by plus a function of a comma b is equal to z, right? Okay, so let's see the question. It says that 4xyz is equal to pq plus 2px square y plus 2qxy square. Simple? Not simple. We will first of all need to solve this expression. So we see x square, we see y square, so we get an idea that yeah, we can substitute x square as capital X and small y square as capital Y, right? And of course we can see that yeah, it is not of this form, so we can make it, right? Okay, so let's say x square is equal to capital X and y square is equal to capital Y, right? Okay. Of course, whatever substitution you have to make, it just comes with practice, right? There's no remedy for that, I will tell you that these are the substitutions which you need to remember. No, that comes with practice, right? I can tell some of the problems in and the problem there might be some other substitution, and there is a possibility that that substitution I also don't know that what we can substitute. So it can only come with practice, right? I can't tell all the substitutions, right? It depends on the problem itself, right? So there might be a problem which has a something truly new substitution in that case, so that no one knows. It will take time to understand that one. Okay, so that is something which you should know. So from this you will get del z by del x again is equal to del z by del capital X dot del capital X by del x. Of course, y del uh, capital Y by del x is equal to 0. So we don't need to worry about that. Del z by del capital X, this it will become 2x, and del z by del y is del z by del capital Y dot del y by del y is equal to del z by del capital Y dot 2x, I mean 2y, right? Just substitute it over here, you will get the answer. Okay, let's see it. So it will be equal to, well, let's see it. Okay, so this is the expression which we are getting. Now we can say it as 4xyz is equal to the expression 4xy, uh, of course, p and q, 4xy del z by del x del z by del y plus this expression 4x cube y 4x cube y del z by del x plus 4x y 4xy cube del z by del y, right? Simple. Okay, xy gets cancelled, it becomes like this, simple. Okay, and now we have 4z is equal to, and of course 4 also gets cancelled, right? So we get z is equal to what? It is equal to x square is capital X del z by del x plus this is capital Y del z by del capital Y plus del z by del x dot del z by del y, right? Now we can say it as small p1, this is small p2, q2, q1. Okay, z is equal to x p1 plus y p q1 plus p1 q1, right? Now just substitute it over here, you will get z is equal to uh, ax plus by plus ab, right? A x square plus by square plus ab, right? Simple. That is the answer. Okay, yeah, correct. So let's see the second form now. It is, yeah, we have the second form. Now let's solve that. Okay, so this is the second part and I'm recording this in NIT Durgapur. So let's start the lecture. So we were on the third equation, that f of z comma p comma q is equal to 0, right? So to solve such kind of expressions, what we do? Well, in this case, we assume that let z is an arbitrary function of x plus ay. Okay, or you can say it is equal to phi of u, an arbitrary function of u, where u is equal to x plus ay. Correct? Okay, fine. Okay, so if you calculate del z by del x in this case, what you will get? Well, you will get del phi by del u into del u by del x. Correct? Of course, if z is a function of phi of u, so of course del z by del x is equal to del phi by del u dot del u by del x. Chain rule. Simple, right? Okay. So what is del u by del x? Well, del u by del x is equal to 1. Correct? Simple. It is u is equal to x plus ay. So when you differentiate it with respect to x, you will get 1, right? So it is equal to del phi by del u. Now the interesting thing over here is that you can say that z is equal to phi of u, correct? So you can say that dz, the proper integral dz by du is equal to d phi by du, correct? And of course they both are equal. Del phi by del u, since del phi by del u and since phi is a function of one variable only, phi is a function of u only, so we can say that del phi by del u is equal to d phi by du, since phi is a function of a single variable. So when you take its derivative, it will be equal to d phi by du. So it is equal to d phi by du. It is equal to dz by du, right? So we have p is equal to dz by du, correct? So we should write this expression over here. P is equal to dz by du, correct? Simple. Understood or not? Since when we have a function in a single variable, so in that case we get a proper differential equation or proper derivative, right? Not partial, right? Since phi is a function of one variable only, u, right? Okay, right. And over here z is also a function of u only, because we assume z is equal to phi of u. Okay, understood? Okay. So we have this expression. Now let's see for q what we'll get. Let's see. So let's solve for del z by del y. So over here also you will get this only, right? Okay. So del z by del phi, it can be written as del phi by del u dot del u by del y. What is del u by del y? It is equal to a, right? Okay. A d del phi by del u, right? What is del phi by del u? It is equal to d phi by du, and d phi by du was equal to p, which was equal to dz by du, correct? So it is equal to a dz by du, correct? Understood, right? So we have q is equal to a dz by du. So this expression is equivalent to saying that f of z comma p is equal to dz by du comma a dz by du, right, is equal to 0. So now let's see a problem to understand this. Okay, so let's see. So let's see the question. The question states that z square times p square plus q square plus 1 is equal to a square, right? Okay. So basically it is function of z, p and q only, right? So in place of p you can substitute dz by du, and in place of q you can substitute dz by this quantity. So you have z square times the quantity dz by du whole square plus a square dz by du whole square plus 1 is equal to a square, right? This expression, correct. So now what you can do, is that you can bring that expression over there. So you get dz by du whole square. You can take common. You will have 1 plus over here. Let's assume it as b, right? Because of course we have used the variable, the constant as a over here. So let's name, instead of a over here, let's name it b. Okay, fine. Okay, 1 plus b square, that one will go there, so it will be equal to a square by z square minus 1. Understood or not? Right? Basically, I brought that z square in the denominator, and then I had expression this expression, I mean dz by du whole square plus b square dz by du whole square plus 1 is equal to a square by z. So I brought this one term to the RHS, so it became negative 1. That is what I have written. Correct? Okay. So from this you can say that dz by du whole square is equal to a square minus z square by z square into the quantity 1 upon 1 plus b square, but it does not matter because 1 plus b square is a constant, right? So it's simple. You can take the square root both sides and then you can integrate it. You will get the answer, right? And it's so simple, right? So you know how to solve this kind of differential equation. It is ODE, right? You can watch my lecture on ODEs. So if you have problem with this kind of problems, right? So in this you can solve, and you know the value of u is equal to x plus ay, right? So substitute it, you will get the answer, right? So let's move to the fourth form. So the fourth form is f of x comma p, f of x comma p, f1, a function is equal to f2 of y comma q, right? Okay. So in this what we do is that we assume f1 of x comma p is equal to f2 of y comma q and set it equal to a, where a is a constant, right? A is a constant in this case, okay, right? So what we do next is that we assume let p is some f1 of x and q is some f2 of y, right? Okay, I will tell everything, just wait. So we know that dz, when you will see the question, you will understand. Okay, so don't worry why I am doing this. Okay, so dz, the complete derivative of z can be written as del z by del x dot dx plus del z by del y dot dy, right? So what is del z by del x? It is equal to f1 of x dx plus f2 of y dy. This dz, just integrate this, you will get your answer, right? So that is why I assume p as the function of x and q as the function of y, because it will be then easy to integrate this expression. So let's see it to understand it better, right? Let's see a problem in this, okay? So let's see the question. The question states that yp is equal to 2yx plus log of q. So what was the expression? It was f1 of x comma p is equal to f2 of y comma q, right? So this is the expression. So it is of this form that f of x comma p is equal to f2 of y comma q, right? So let's see, is it of this form? Well, we have to make it because it is still not in that form. So we can see a p over here, which should not be over here, right? So yp, we can bring this expression over here, minus 2yx is equal to log of q, correct? Okay, basically we have to make it of this form. So we want x and p to be together and y and q to be together, right? So that is why we are rearranging it. You can take y as common. P minus 2x is equal to log of q. So from this you can say that p minus 2x is equal to log of q by the expression y, right? Okay. Now it is of this form that f of x comma p is equal to f2 of y comma q, right? So now let's see how we'll solve it. Well, so our of f1 of x comma p, we assumed it as a constant. So we will get from this, we are going to get p minus 2x. P minus 2x is equal to a. So we get p is equal to 2x plus a, right? Which is f1 of x. Now you know that why I said there f1 of x only, not f1 of x comma y, because of course it is a function of x and p only. So when you will rearrange this, you will get only a function in x, p as a function only in x, not in y, right? Uh, do you understand it? Not. Similar is the case over here. Suppose it is only a function in x and p. So when you will set it equal to some constant, and when you solve it, you will get the relation between p and x only. No y will be involved in that, right? Similarly, we can say f2 of what was it? Y comma q is equal to a. We set both as a, which implies it is equal to log of q. Log q by y is equal to a. So we can say that q is equal to e to the power ay, correct? Which is equal to f2 of y, right? Again, when you separate y and p in this and set it equal to a, you will get only a relation between q and y. No x will be involved in that, right? Okay. So dz is equal to f1 dx plus f2 dy, just from that expression. So you have 2x plus a dx plus e to the power ay dy plus some constant when you integrate this, and it is equal to z. That is the answer, right? Understood? Now it is very simple to integrate. If you want, I can do that also. X square plus ax plus e to the power ay by a plus a constant, right? That is the answer. Okay. Yeah, correct. Yeah, instead of c, you can assume b, whatever you want to assume, right? So yeah, that's it. So now let's move to char pit method. What is it? Let's see that. Now let's see char pit method. Char pit's method. So it is basically a general method to solve a non-linear partial differential equation. So let's see it. Okay. So it is a general method to solve. Yeah. Let me write some point. General method to solve non-linear first order partial differential equation, right? Okay. And so, and in this we use this formula that dz is equal to del z by del y del x dx plus del z by del y dy, right? Okay, but what does this expression tell? Well, it tells a total gradient along x-axis and y-axis. So that is why we have a del z by del x, and this we have del z by del y, correct? Okay. So now we can integrate this expression to get our answer, like we did in the fourth method, similar to that, right? So to get result or solution, we define another function of the form another non-linear. Let me define that function also. Another non-linear partial differential equation of first order, right? Okay. So it is expressed as f of x comma y comma z comma p comma is equal to 0. So it should be of it should be non-linear partial differential equation, right? Okay. So if I did not define f over here, yeah, I should define over here. F of x comma y comma z p comma q is equal to 0. This is the general expression. This general method solve non-linear partial differential equation of first order of this form, and this is another another equation. Now you have to solve f and capital F, right? And from this you will get some p is equal to p of x comma y comma z comma a, and q is equal to q of x comma y comma z comma a, right? Don't worry, it's just theory which I am telling. You can just note it for now. and we will see it using some problems. It is just some theory part which you can remember or you can note for your reference purpose, because of course it is important to solve any question or to understand any concept, right? That is why. Let me write it, then I will tell everything. So when we substitute P and Q, we get some phi of x comma y comma z comma a comma b is equal to 0, right? Okay. Now let me tell what it all means. So basically, Charpit's method is a generalized method, or is a general method to solve a non-linear partial differential equation of first order of the form f of x comma y comma z comma p comma q, where p is equal to del z by del x and q is equal to del z by del y. Correct? Okay. So basically, in this we are going to apply this rule that dz is equal to del z by del x dx plus del z by del y dy. We can write as p dx sorry plus q dy, correct? Okay, you can just solve this expression and then you will get some relation which we will see using questions. And to get this desired result, what we are going to do is we will define another nonlinear partial differential equation of first order capital F of x comma y comma z comma p comma q, right? And then we are going to solve p and q, and from that we will get some result that p is equal to this expression, q is equal to this expression. And when we will substitute back in this equation the values of p and q, we will get some phi of x comma y comma z, this is z comma a comma b, right, is equal to 0. So this is the whole procedure of Charpit's equation, Charpit's method. So it is like straightforward, but the biggest question is that how we will define this another function f of where is it, yeah, f of capital F of x comma y comma z comma p comma q is equal to 0. How we will define this function, because we will be given this function, so how we will go from that to this, I mean, well, let me explain it now. Let's see that. Let me raise this. To determine f, how will it determine f, right? So let's see it. So we will differentiate f and capital F with respect to x and y. Of course we have to differentiate, this partial differential equation, so we have to differentiate, right? So we will have if we differentiate del f by del x plus del f by del z dot del z by del x, del z by del x. So del z by del x, I can directly write p, because it's like we are dealing with del z by del x again and again. So by now you must have practiced enough. You must have practiced enough that we can write p directly over here, plus del f by del p dot del p by del x plus del f by del q dot del q by del x is equal to 0, right? And second one, it is del capital F by x plus del capital F by del z dot p plus del capital F by del p dot del p by del x plus del capital P by del q dot del q by del x is equal to 0. Okay, yeah, I know it's like too much complex. Well, I made a video recently of 10 minutes. In that I have explained that if a function is u of x comma y comma z, which I have already shown in the previous part only, that I had made that, like that video, you can refer to that so that you can easily understand this expression if you are not able to understand. But it is basically a chain rule which I am applying, nothing else. Chain rule and product rule, that is it. So in this we have differentiated it with respect to p, with respect to x, and in this we will eliminate del p by del x. We have to eliminate, right? You have to eliminate, okay? And this is the expression. Now if we will differentiate it with respect to y, what we will get? We will get del f by del y plus del f by del z dot q correct, plus del f by del p dot del p by del y plus the expression del f by del q dot del q by del y is equal to 0, correct, yeah. And second expression del capital F by del y dot del plus sorry del capital F by del z into q plus del capital F by del p dot del p by y sorry del y plus del capital F by del q dot del q by del y is equal to 0, right? So in this eliminate del q by del y, right? Okay, so let me just see all these expressions are correct or I made any mistake. I have to just check it once. Yeah, it's this one is correct. Yeah, it is absolutely correct, and this expression is absolutely correct. This one, yeah, it is also correct, and del phi, yeah, it's also fine. Yeah, and now let's see this one. It is yeah, this expression is correct. This expression, yeah, okay, del phi by- yeah, correct. And this one is also correct, yeah. So in this we will eliminate del phi, I mean del q by del y and del p by del x, and then we will do some other mathematics which we will see in just few minutes. Let me erase this. So on eliminating del p by del x, what you will get is that the first expression as del, it's a big expression, so I should write it from here. So it is del f by del x dot del capital F by del x, I mean del p, minus del f by del x dot del small f by del p, this, plus del f by del z dot del f by del p minus del f by del z dot del f by del p into p plus del f by del q dot del capital F by del p minus del f by del q minus del q dot del f by del p into d into del phi del q sorry del q by del x is equal to 0. Okay, this is from the elimination of del p by del x, right? Okay, let me see this expression, is it correct? Yeah, del phi this and then this expression, this is capital F, and this expression, this is again capital F only. Yeah, it's correct, yeah. Now the second expression, del f by del u sorry del y dot del capital F by del p minus del f by del x dot del f sorry what is it, yeah, del f by del q, yeah. Okay, del f by del y into the quantity del f by del q minus del f by del y, sorry, yeah, or del y, and then del f, yeah, correct, plus the expression del f by del z dot del f by del q minus the quantity del f del capital F by del z dot del f by del q plus the expression over here, it must be there must have been a q over here, let me see it. I think there is some problem in this expression, this del f, and when we will eliminate this, yeah, there will be a q in this because of course if there, it won't be a q, then there will be a problem. Yeah, so okay, let me see it. Plus del f by del q, del f by del q dot del f, del capital F by del q minus del capital F by del p dot del f by del q into the quantity del p by del p is equal to 0, and this is from the elimination of del q by del y, correct? So let me see this expression. I have to confirm that whether it has a q or not. So let me think once that if we are going to add this expression, then what we'll get. So yeah, here it must be a q, right? Because of course you can see the pattern also, and when you eliminate, you will see that there's a q, of course, right? Of course, without q, how can you form a expression y, right? So yeah, this is the expression, and now you have to add them. You have to add them now. So when you will add them, what you will get is that it is a very big expression now. So it is del. I have to write bit small. Let me use another chalk. This one. So it is equal to del f by del x. Of course, I'm not showing the calculation because the calculation you can do on your own. I've already written the results which we will get because, of course, calculation is like elimination. It's like you studied in 11th, 12th, and maybe in lower class also. That is why I'm not showing that. I'm directly writing the result of elimination, right? It is just elimination, which you know, of course, right? That is it. So del f by del x plus p del f by del z into the quantity del capital F by del P plus the quantity del F by del Y. Don't worry, these are just very big expressions, but when you will solve the problems, you will see that it is very easy thing which I am telling you all. It is just a generalized expression. That is why it is like felt that it is a very very difficult topic. No, it is very simple. Once you will see the question, you will see that it was so simple, right? So just wait for a minute. Plus the quantity q times del f by del z times the quantity del f by the quantity del q plus the expression minus p del f by del q, I mean del p minus the quantity q del f by the expression del q, right? Okay, this is del f by del z, okay, plus minus del f by del p del f by del x plus minus del f by del q df by d, sorry, del y by del, sorry, del f by del y is equal to 0. So this is the expression, right? Okay, so what we are going to do this, what we are going to do with this expression? Well, it is a very simple thing now. Let me show you how. Now, just see this expression. You can easily say from this that this expression is a linear partial differential equation. It is a Lagrange's linear partial differential equation in which x, y, z, p, q are independent variable, and f is a dependent variable, right? Dependent variable, right? Of course, it is del f by del p, del f by del q, del f by del z, del f by del x, del f by del y, right? So x, y, z, p, and q, these are the dependent variables. I mean, these are the independent variables, and f is the dependent variable on x, y, z, p, and q. Right? Of course, we had that f of x, y, z, p, q is dependent on these quantities, right? So we can apply that rule that we had previously proved it for like x, y, and z only. Now we can extend that idea to x, y, z, p, q, and f, right? So we will have dx by dy by dz by dp by dq by f df by 0. Why 0? Because of course over here it is 0, right? So what is this expression? Negative del f by del p, negative del f by del p, right? Yeah, and that negative del f by del q, correct? And this expression negative p del f by del p minus q del f by del q. Just watch the Lagrange's auxiliary equation part so that you will understand. So from that you will understand that why am I writing it like this, right? Okay. So this expression, and then for p it was, yeah, it is del f by del x plus p del f by del z, correct? And for this it is this expression del f by del f by del y plus the quantity q del f by del z, q del f by del z, correct? Understood? Let me verify, is it correct? Yeah, this is correct. This is equal to 0. With respect to z it is equal to negative, and correct. And with respect to dp is equal to del f by this expression, it is equal to, yeah, correct. So from this you will get the values, the required values, whichever you want, and from that you will get the value, basically you will get the value of p and q. So from that you will integrate dz is equal to del is equal to p dx plus q dy. Just integrate that expression, you will get the value of z. This is how we will work. So let's see a problem to understand this expression, right? Let me raise this. So let's see the question. Solve 2zx minus px square minus 2qxy plus pq is equal to 0, correct? Okay, so basically it is of the form that f is equal to 0, right? Basically f of x, y, z, pq is equal to 0, right? Equal to 0, right? Okay. So let's solve this. So you have to find del f by del x first of all. It will be equal to 2z minus 2p 2xp minus 2qy, right? Correct? Yeah. Del f by del y, it will be equal to what? It will be equal to negative 2qx, right? Okay. And del f by del p you need to find now. So del f by del p, it will be equal to what? It will be equal to negative x square plus q. Negative x square plus q, and del f by del q, it will be equal to this expression that it will be equal to q minus 2xy, correct? Right? Yeah, correct. Okay. So from this, you know the expression that dp by the expression del f by del x plus p del z by del, I mean del f by del z is equal to the quantity del q del q sorry dq sorry, dq by del f by del y plus q del f by del z is equal to the expression that it is equal to dz by the quantity negative p del f by the quantity del p minus q del f by del q, right, is equal to dx by the quantity negative del f by del p is equal to dy negative del f by del q, right? Okay. Now let's solve this expression. So it is equal to 2z minus 2xp minus 2qp, right? We have this expression, and when you find del f by del z, it will be equal to 2x. It will just equal to 2x, right? Okay. So let's write this expression. So we will get dp by, what is del f by del x? Del f by del x is 2z minus 2xp minus 2qy. And what is del z by del f by del z? It is equal to 2x multiplied by p. So this expression and that expression will get cancelled. So we'll get 2z minus 2qy is equal to dq. What is dq? dq is negative 2qxy, negative 2qx, and what is del f by del z? It is equal to 2x. When you multiply by q, it will become plus 2qx, so it will be equal to 0. Correct? Okay. So dz by, similarly you will solve over here also, you will get px square minus 2qx plus 2p pxy, right? dz by px square minus 2pq, sorry, right? Okay, of course these are just you are substituting these values, nothing else. Okay, that is why I am just writing it like that. Okay, it is dx by what is negative del f by del p, it is equal to x square plus x square minus q, and it is equal to dy by this expression. You will get 2xy minus q, 2xy 2xy. Wait, why have written q over here? Sorry, it will be p. Sorry, it will be p over here, right? Minus p, right? Now you can take this expression as it is. So you will get that dq by 0, right? It means that dq must be equal to 0 to make it defined. So we can say that q is equal to some c1, some constant c1. Okay. Now when you have got the value of q as c1, you can substitute it over here to get the value of p. So when you substitute there, you will get 2zx minus px square minus 2c1 xy plus cp is equal to 0. And when you solve, you get p is equal to what? P is equal to 2x times c1, z minus c1y by the quantity x square minus c1 square, right? Correct? This c1 is squared, right? So basically we solve for q, then we substitute over here. From that we solve for p, right? So we have the value of p, we have the value of q. So we can now just solve it like that. So I should write, where I should write. Okay, let me erase this. Just a minute. Let me erase this so that I can write it. So yeah. So I have this expression that dz is equal to p dx plus q dy. So we are just going to solve this now. So it is simple. Dz is equal to the expression 2x 2 minus, sorry, it is z minus c1 pi divided by the expression x square minus c1 square dx plus c1 dy, correct? C1 dy. Okay, now you can solve this expression, right? So now you can easily solve this expression because now it is just ordinary differential equation which you know how to solve it, right? So basically what you can do is you can divide by both sides by z minus c1 y, and consequently you can solve it. Let me show you how. You can say from that dz minus c1 dy is equal to 2x by x square minus c1 square times the quantity z minus c1y dx. So from this you can say that d of z minus c1y by z minus c1y is equal to 2x by x square minus c1 square dx. You can integrate this. Now it is of the exact form. You can just integrate this, right? So this is how we solve the problems using Charpit's method. And of course the method which we used in its derivation, it is a very lengthy method, but when you solve questions, then it is like very simple, right? Understood? So let me raise this and then we move to the next topic, that is the homogeneous equations. Let's see that. Now let's start with homogeneous linear equation with constant coefficients. Let's start with this. Okay, so let's start. So what is meant by homogeneous linear equation? Well, let's consider a partial differential equation of the form a naught. Let me write it. A naught del n del z by del x n plus a1 del n z del n minus 1 x del y a2 del nz by del n minus 2 x del y square and so on till the expression an del n z by del y n plus plus b0 del n minus 1 z del x n minus 1 plus b1 del n minus 1 z del n minus 2 x del y. This is over here. Wait, sorry, it should be del x n minus 1. This is 1, this here is correct. Over here it should be at del x n minus 2. Yeah, so this expression, then this over here del x n minus 2 del y and so on like this, and you have to go till like till all the expressions till suppose k naught del z by del x plus k1 del z by del y plus some L naught times z is equal to 0. So you can write it as phi d dot d dash of the quantity z is equal to 0, right? Where d is equal to del by del x and is equivalent, and d dash is the operator del by del y, right? Okay, so this is called a linear partial differential equation of nth order with constant coefficients. We haven't discussed till now homogeneous linear equation. We have to discuss that now. So this is a linear partial differential equation of nth order with constant coefficients, right? So a linear homogeneous partial differential equation. Now let's discuss that. So it is a linear homogeneous partial differential equation is of the form where all the derivatives are of same order. So if we remove all this expression, if we just see this expression a naught, if I write in summation form, is it okay? Right. So it is as I goes from 0 to n, ai del n z by del x n minus I times del y I is equal to 0. This expression is called homogeneous linear partial differential equation, right? So the condition is that where all derivatives are of same order. So in this it is of same order, right? Correct? Okay. So nth order basically, if I say, right? This is called a homogeneous partial differential equation, right? Okay. So yeah, and if you want you can write it like this also. A naught d n plus a1 d n minus 1 d dash and so on into z is equal to 0. Applied on z is equal to 0. This is an operator basically. Remember from ODE we had certain operators, similar is the case over here. Just in this we have two operators. There we had only d by dx. Here we have del by del x and del by del y. We have two operators over here, right? Simple. So let's see how we find its solutions. Let's see that. So in this also we apply the same method as we did in ODE. We will find the complementary function and the particular integral, and then we will add them to get the general solution, right? So complementary function and pi we need to find, right? So complementary function, so suppose it was like phi of d dot d dash z is equal to some function f of xy, suppose it was this expression, then what we do is that in this case, to find CF, what we do, we set phi of d dot d dash z as 0. We don't consider this, and then we find the solution according to this, and then we solve for pi d dot d dash z is equal to the function x comma y, and then we solve for the pi in this case, and then we club these two results together, cf plus pi, to get the general solution, right? So this is how we do it. Okay, so yeah, this is just the theory part, and of course it is free from any arbitrary constant. Okay, and over here you will get arbitrary constants, right? Okay, so let's see a problem, or before that let me discuss how we'll find the CF. Let's discuss that also, and then we will be seeing a problem to understand it better, right? Okay. Okay, so let's consider a function, a differential equation, del 2z by del x square plus a1 del 2z by del x, del x del y plus a2 del 2z by del y square is equal to 0. Correct? This is the expression. So if you have studied ordinary differential equations, you must be knowing something called an auxiliary equation, right? So how we define auxiliary equation in this case? Well, I can write it as d square z plus d dash z plus, a1 times plus a2 times d dash whole square is equal to 0, right? Okay. Now I will write it as an auxiliary equation, m square plus a1m plus a2 is equal to 0, where m is equal to d by d dash. Correct? M is equal to d by d dash. So here m is a numeric value basically, right? So from this you will solve for the values of m, and then you can factorize this as suppose you get the result as m1 and m2, you get this result, so you can factorize it like minus m1 z into this quantity into the quantity d dash minus m2 z is equal to 0, right? Like this you can do. Okay, so this is how you will solve. Okay, so let's see how we'll solve it. Let's take some cases to understand this. Okay, let me raise this. So let's take the case 1 in which m1 is not equal to m2. Means m1 is not equal to m2, right? So in that case what we will get is that we'll be having this expression d minus m1 d dash times sorry, over there did I wrote this expression d minus m1 times d dash minus m2. Sorry, if I wrote this then please change it. It is not this, it is this expression d1 times d minus m2 d dash z is equal to 0, right? It is wrong, it is wrong, it is wrong, it is absolutely wrong. Sorry. So this is the expression. Okay, so what you can do is that you can set each of them as equal to 0, then you will apply the linear combination of the solutions. Okay, so d minus m1 d dash is equal to 0, of course applied on z. This is applied on z is equal to 0. So from this what you can do is that it is very simple. So dz minus m1 dz d dash z is equal to 0. So basically it is del z by del x minus m1 del z by del y is equal to 0. So it is basically equal to p minus m1 q is equal to 0. So we will apply it as a Lagrange linear partial differential equation. So you will get dx by 1 is equal to dy by negative m1 is equal to dz by 0. Correct? Correct? So from this you will get that z is equal to some constant, and from this when you solve it, it is like very simple, is y plus m2 m2 because we have taken m1, so it will be equal to x, right? Okay, so from this we can say that z is a function of this, what I am writing is equal to y plus m1x is equal to some constant a. So from all this we can say that, because from the arbitrary functions which we know how we defined them, we can say it like it is equal to function of y plus m1x, right? And we can also say that z from this one, from 2 1, we can say f is equal to y plus m2x, right? Correct. So this is the solution, right? So we can say that z is equal to f, this f1 f2, f1 times y plus m1x plus f2 times y plus m2x, right? Okay. And of course, there is no need to do linear combination, because of course, if you multiply by c1 or c2, then also it will be just the same function. I mean, it will be also included in that function, because of course, c1 times x can be written as x only, capital X only, right? You can write it like this, because of course, c1 is just a constant. So even if you multiply it, it will be absorbed in that expression only, in that function only. So it's not required actually. Okay. So okay. So let's see a problem to understand this all concept. So let's see it. Okay, let me raise this. So let's see the question. It is 2 del 2z by del x square plus 5 del 2z by del x del y plus 2 del 2z by del y square is equal to 0, right? Okay. So let's solve this. So again, it can be written as 2d square plus 5d d dash plus 2d dash square z is equal to 0. Applied on z is equal to 0. Correct? Okay. So we can rearrange it as 2m square plus 5m plus 2 is equal to 0. Right? The auxiliary equation. This is the auxiliary equation. Auxiliary equation. Correct? Now you can solve this easily. You will get what? You will get 2m plus 4 into m plus let's solve it only. So you will get 2m square plus 4m plus m plus 2 is equal to 0. So you will get 2m m plus 2 plus m plus 2 is equal to 0. So you get m is equal to -2 and -1 by 2, right? So you will get clearly that z is equal to some f1 of y minus 2x plus f2 of y minus x by 2. This is it. Simple. Okay. Yeah. So basically, of course, you have to apply the complete rule that over here it will be d minus d dash 2d dash into d minus d dash by 2 into z applied on z, sorry. And then you will just write d minus 2d dash applied on z is equal to 0. Then you will say that dx by 1 is equal to dy by the quantity -2 is equal to the expression, what? It is equal to dz by 0, and then you will solve this again to get the result. Okay, so it is like a lengthy method which you will apply. So basically this is how you will solve, right? Let me see if it is correct. Yeah, sorry, it will be plus, right? It will plus, over here, and then you will solve. You will get this expression, right? And when you will solve, you will get this expression, right? Okay, this is how you will be solving. Okay, and now let's see to the next. Let's move to the next case in which this is simply ordinary differential equation. If you remember what I am doing over here, it is all that. It is just over here. There's an extra step of applying Lagrange's linear partial differential equation, but this auxiliary equation, Lagrange's auxiliary equation, which we are applying, right? Just everything is same as we did in ordinary differential equation. Understood? Okay. So now let's move to the next case. Basically, let's see. So let's see the case 2 when m1 is equal to m2. So in that case, what you will get? So in that case, we will assume d minus. Basically, it will become like d minus md dash, d minus md dash applied on z is equal to 0. Of course, this will be the expression, right? Okay. So in this case, when we will apply it, we will say d minus md dash applied on z as equal to u. We'll set it equal to u, okay? And then we'll apply d minus md dash applied on u and then set it equal to 0, right? Okay. So let's start with this expression, okay? So from this, when you will solve, you will get this is that only partial differential equation. Sorry, when m1 is not equal to m2, that case only. When we will solve it, you will get u is equal to some function of x plus y plus mx. Correct? That is only if you remember, right? Okay. And just when you will move to this expression, you will get del z, basically dz minus d dash m d dash z is equal to u is equal to f of y plus mx. Correct? Okay. Basically, here also you will apply Lagrange's partial differential equation, linear partial differential equation, the auxiliary equations you will form, and then you will get this result only. Basically, in that case also when we were getting m1 and m2, and then we were saying that d minus m1 d dash is equal to 0, applied on z is equal to 0. So from that we were solving z is equal to f of y plus m1x. So similarly over here we get u is equal to f of y plus mx. Simple, right? Okay. So this expression, and we will get p minus m q is equal to f of y plus mx. Correct? So we have dx by 1 is equal to dq by negative m is equal to dz by f of y plus mx. Correct? We have this expression, right? Sorry, this is dy. I am writing this. Okay. Now we have to solve this expression. So how will we solve it? Well, dx is equal to this expression, we can say. So dx is equal to dz by f of y plus mx. Simply we can solve this expression. So what we can do is that we have to do something over here. So let's keep it aside for now. And when you solve these two expressions, you will get y plus mx is equal to some constant a is equal to some constant a. So y plus mx is basically over here a, f of a, which is a constant. So you get that x is equal to z by f of a plus some b. So you get b is equal to x minus z by function of y plus mx, right? I got two constants from this, okay? So you get these two. So you get the expression as z is equal to what? Z is equal to, we can say from here that, or we can clearly say from here that instead of doing this, we can say it like this also, that let me show you. We can say it like z is equal to f of a times x plus b f of a. Now b f of a is again a constant. Let's name it b only itself. So we get z is equal to f of y plus mx into x plus b. So it is minus and it is equal to this, right? So from this, where I can write z is equal to, so we can say z minus f of y plus mx into x is equal to this expression f of, this is f1, this is f2, y plus mx, right? So we get z is equal to f1 y plus mx x plus f2 plus f2, this is y plus mx again, right? This is the expression. Okay, correct? It is equal to this, yeah, correct. So now suppose if you have n powers included, suppose it was like instead of 2 here it would be have been if there would have been 3 expressions, then you would have get z is equal to phi 1 y plus mx plus phi 2 y plus mx x plus phi 2 y plus mx x square, right? Correct? Okay, this is how you write. Sorry, phi 3. Correct. So let's see a question to understand this. Let's see. So let's see a question. 4r minus 12s plus 9t is equal to 0. What is rs and t? If you remember, I told what is r, what is s, what is t. So let me write it. It is 4 del 2 z by del x square minus 12 del 2 z by del x del y plus 9 times del 2 z by del y square is equal to 0. It is similar to saying this. That is, I am trying to show the problems in such way that even if notations come, then also you can easily do it. Okay. So that is how you express it. So now let's write its auxiliary equation. It is 4m square minus 12m plus 9 is equal to 0. So when you will break it, you will get 4m square minus 6m, yeah, plus minus 6m plus 9 is equal to 0. So you can take 4m as common, sorry, 2m as common, so you get 2m minus 3 plus you can take negative 2 as common over here. 2m minus 3 is equal to 0, sorry, 3, right? So from this you can get, we will get 2m minus 3 times 2m minus 3 is equal to 0, right? So we get m is equal to 3 by 2 and 3 by 2. So m is equal to 3 by 2, right? So again you have to apply that whole procedure, but I will directly write the answer over here that z is equal to phi 1 instead of f1 I am using phi 1, you can use whatever you want. Y plus 3 by 2x plus x times phi 2 y plus 3 by 2 x. This is the complementary function. This is the complementary functions which we are calculating right now. Okay, is it correct? Yeah. So let's move to the next topic, rules for finding pi. Let's see how we find the particular integral, and then we will be well acquainted to learn that how we find the general solution. So let's see that. So let's see the rules for finding pi, that is particular integral. So let's see it. Rules to find pi. So before seeing the general method, let's see some of the standard methods or the formula to calculate the particular integral. So let's see that first of all. So let's see that. Okay, they are called the short methods. Let's first of all study short methods to find pi, right? Okay, so first one, when f of x comma y, that is the given function, is of the form e to the power ax plus by, then in that case particular integral is equal to 1 upon phi of d dot d by d dash, I mean d comma d dash, or d dash e to the power ax plus by d comma d dash, sorry, is equal to 1 upon phi of a comma b e to the power ax plus by, provided that pi a comma b is not equal to 0. Listen one thing, if I wrote there phi of d dot d dash of z is equal to 0, then change this and write this is wrong. D comma d dash is equal to 0, right? Okay. So you should write this expression instead of that. Okay. So pi is equal to this expression for this case. Okay. Because of course we are expressing it in terms of powers. Okay. So that is why. Okay. So this is the first one. Then see the second one. Second one, it states that function of x comma y function of x comma y, if it is equal to sine of ax plus by or cos of ax plus by, correct? If that is the case, then that case particular integral is equal to phi of 1 upon negative a square negative ab negative b square into the quantity sine of ax plus by is, that's it, okay? And this expression must not be equal to what? Must not be equal to 0, right? So let's see the third case. Let's see that also. So, and then we'll see the general case. That is better to discuss the general case because usually you can find for any value, any function. This is just some standards, that is the end discussion. Okay. So I'm not discussing the third one because it is like a bit complex, and instead of applying that method, you can easily do it using generalized method. That is why I'm not discussing that. Okay. If it will be required, I will make a video on it, like 5 to 10 minutes. You can watch that. But for now, let's discuss something which will help you to understand concepts better instead of like learning those things. Okay. So let's see the general method. So pi is equal to, similarly as you did in ODE, you have to apply the same rule in case of pi also. It will be the inverse basically d comma d dash of the quantity x comma y, which is equal to 1 upon, now as you just did before, d minus m1 d dash d minus m2 d dash and so on till d minus mn d dash, correct, of the expression f of x comma y, this expression. Okay. So what we are going to do, suppose we are evaluating 1 upon d minus m d dash, a general one, f of x comma y. So we will set it equal to some variable, suppose z. So you will get, of course, when you bring it over here, you will get f of x comma y is equal to d minus md dash applied on z. And now it is that expression only in which m1 was equal to m2. It is similar to that. It is exactly same like that. So we'll apply the Lagrange auxiliary function in this case, and you will again get the answer, right? So let's discuss it with respect to a question. So with reference to a question, so you can easily understand this. Okay. So let's discuss it. Okay. Let me raise this stuff. Del 3z by del x cube minus 2 del 3z by del x square del y is equal to 2 e to the power 2x plus 3x square y, correct? This is square. Okay. So let's evaluate this expression, and as a homework you can do this question also. You can do this as practice. Del 2z by del x square minus del 2z by del x del y is equal to cos x cos 2y, correct? You can do this from your part. I will discuss in this one. Okay. So let's discuss this. Let me stop here. So let's see solution. So again we will find the auxiliary equation. First of all, we will find the CF. So first of all, let's find the CF. What we will get? Let's see it. So when we find the CF, we can say it is m cube minus 2m square. I'm not writing the statements, that you can do on your own, right? I'm writing the concept which you need to follow in this. From this you'll get m is equal to 0, 0 and 2. Of course not 0 and 2. 0, 0 and 2, because over here it is m square, it is a degree of 3. So of course you'll get 3 results in this, 3 solutions. So that is why you get 0, 0 and 2. So there are 2 equal solutions in this case, right? Okay. Basically m square is equal to 0 implies m times m is equal to 0, which implies m is equal to 0 or m is equal to 0. So basically 2 solutions. Okay. Yeah. So you can say that CF is what? Is equal to, CF is equal to phi 1 of y plus 0x plus x times phi 1 of y plus 0x plus phi 3 of y plus 2x, correct? So you get phi 1, this phi 2, sorry. So you get phi 1 of y plus x, phi 2 of y plus phi 3 of y plus 2x. Correct? This is the expression? Yeah. So from this you will get your CF value, right? Okay. This is how you will get. Yeah. And now you will find the PI, right? So let me write the CF over here. This is your homework. You will do it. So CF is basically phi 1 of y plus x phi 2 of y plus phi 3 of y plus 2x. Correct? Okay. Let me erase this stuff. So now we are going to find pi. Pi will be equal to 1 upon phi of d comma d dash of the quantity f of x comma y. So it is equal to 1 upon d dot d into d minus 2 d dash of the quantity e to the power 2 times e to the power 2x plus 3x square y, right? This expression. So what we are going to do is that we will assume 1 upon d minus 2d dash as into 2 e to the power 2x plus 3x square y as some t. We'll assume it as t, and then what we are going to do is that we will solve for this expression. So I'm writing directly, it will be equal to p minus 2q is equal to 2 e to the power 2x plus 3x square y, right? We will get this expression. So we have dx by 1 is equal to dy by negative 2 is equal to dz by we will have dz by this expression, right? We will have dz by this expression. Sorry, dz, not dt, not dz, because we assumed over here dt as means this as dt as t. Sorry, 2 e to the power 2x plus 3x square y. Now we have to solve this. So first we will get that y plus 2x is equal to a, some constant, right? And the second expression which we are going to get is that we will set this expression equal to this expression, and then we are going to solve this expression. So let's see how we will solve it. Let me raise this. So from this we will get that dt is equal to 2 into e to the power 2x plus 3x square into what is the value of y? Y is equal to a minus 2x. From this we can say a is equal to, sorry, y is equal to a minus 2x. So a minus 2x dx, right? Just integrate this, you will get the value of t. And of course, here there will be no arbitrary constant because it is particular integral, right? So from this, when you will solve it, you will get some expression which I think I should write. Okay, so when you will solve it, you will get some expression. Suppose your t is equal to some z, suppose some alpha, you get some function alpha, right? Alpha of x comma y. Okay, suppose you get, or you can just integrate it simply. Let me integrate it. It is this is e to the power 2x plus ax cube minus 6x cube minus 6x to the power 4. So it will be 3 by 2, right? This t. Okay, this, let me check, is it fine? Yeah, 3 by 2, yeah, correct. And then you can substitute it as 2x plus y, and now you have 1 by d dot d dash into uh, this expression t, right? And set it equal to u. So you will get 1 by d t is equal to u. So you will get du is equal to t. So you will get over here del u by del x is equal to t, right? So from this you can say that p is equal to t. Hence you will have dx by 1 is equal to dq by 0 is equal to d u by t. And what is t? We know the value of t is this. From this you will solve for z. You will solve for, sorry, you will solve for u, right? You get some value of u, and then you will have 1 upon d into u is equal to Z you will do, and then you will solve for Z, and that will be equal to your Pi, right? And then you will do CF plus Pi, right? Simple. So I showed you for one expression 1 upon d minus 2, and then you will solve for this because it is very simple, because it is not involving a 2 in this case, right? So this is how you solve for Pi basically, right? And if I have to write the final answer, Pi will come out to be, Pi will come when you will solve e to the power 2x by 2 plus x to the power 6 by 60 plus y x to the power 5 by 20, right? So you know CF, you know Pi, so you can clearly find the general solution as CF plus Pi, right? Where I have written CF plus Pi is equal to the general solution. Okay, simple, understood? Okay, so let's see what we can do next. Yeah, let's just start with another topic now. Okay, so do this problem on your own and complete this also. I've told one method, and then I've told for one means 1 upon d minus 2, you can solve for 1 upon d and then again solve for 1 upon d, right? Understood? So now let's start with non-homogeneous linear partial differential equation, right? So how we will solve for this? Then for example, a linear partial differential equation which is not homogeneous is called a non-homogeneous partial differential equation. Okay, so basically suppose if I have phi of d comma d dash of z is equal to some function of x comma y, so it is not homogeneous if it is if all its derivative don't have same order. For example, if I say d square plus 2d dash plus d dash square minus 2d dash uh, applied on z is equal to some function of x comma y. So in this case, we can say that we can see that this expression is of order 2 and it's of order 1, right? So of course, it is not of same order, so that is it is a non-homogeneous linear partial differential equation, right? So what's next we can do? How do we solve such kind of expressions? Well, in this also we will use CF and PI method. So we won't discuss for PI because in this case also PI is solved using that same method only which we are doing, right? That factorization and then setting it equal to some other variable, then using Lagrange equations to solve that, okay? Lagrange auxiliary equations. So in that case we will be applying, so for PI we will be applying the same method. So we won't discuss that. For CF there's some manipulations which are required. Let me discuss that so that it becomes easier for you. Let me discuss that. So in such cases, we can factorize the expression as instead of d minus md dash, there comes another constant as a. Just that's the difference in calculation of CF, right? When you factorize, you will get such expression, right? And applied on z is equal to 0 because we find the CF, right? So now what we are going to do is that we will open it. We will get P minus MQ minus AZ is equal to 0. So we get one, so we can say P minus MQ is equal to AZ. Now again it's Lagrange's auxiliary equation. That's only it is, right? So we get, yeah, divided dz by az, right? Y plus mx a, not a because we have already used it, let's name it as c1, and then dx is equal to dz by this expression, so we get dx is equal to dz by z and a, so we have ax is equal to natural log of z plus some constant, so we can say, or some constant we can say c2, okay? So from this we will get z is equal to e to the power ax, and you can say plus some c2 again, right? There's no issue in that. So this is how you will solve for this, or you can say it as c2 times e to the power ax. Let's leave it as k for now, and then we will rearrange it like this, okay? So we get this. So in this case, CF is equal to, well, z is equal to e to the power ax times the function of y plus mx. This is how you find the CF in this case, right? Okay. No need of F1 because we were just dealing with one expression. Okay. So if we have multiple such expressions, suppose the product from d square minus mi d dash minus ai applied on z is equal to 0. I goes from 1 to n. So of course when you will open it, it will become d square minus m1 d dash minus a1. Wait, it will be, there will be no d, sorry, sir. There is no d square there. Yeah, when you open it 1, you will get d minus m1 d dash minus a1 multiplied by d minus m2 d dash minus a2 and so on and so forth till d minus mn d dash minus an whole applied on z is equal to 0, right? That is the expression which we are going to get. Okay, so this is the expression, and when you will solve it, you will get the answer as z is equal to e to the power a1x f1 y plus m1x plus so on till e to the power a n x fn of y plus mn x, right? This is the expression. Okay, a1 is it? Yeah, this expression, yeah, this is okay. And you can express it in form of summation also, that z is equal to like sum of all those expressions. Okay, that's okay. So this is how you solve for z and all. And yeah, suppose if uh, repeated this, suppose if this expression is repeated, for example d minus m d dash minus a times d minus m d dash minus a and so on, means the m and a are equal, then in that case z is equal to e to the power ax f1y plus mx plus x times e to the power ax f times y plus f2 times plus mx and so on till if it is repeated n times, then you will have plus e to the power uh, plus x to the power n minus 1 e to the power ax fn of y plus mx, correct? Just like in that expression, but over here we have an extra expression of e to the power ax. That's it. Okay, so yeah, that's it. Is it fine? Yeah, okay. So now let's discuss it with reference to a question, so it becomes easier for you all to understand. Let's discuss it with reference to a question. So let's see the question. It states d square minus plus 2d d dash minus 2d plus d square d dash square minus 2d minus 2d dash 2d dash applied on z is equal to sine of x plus 2y. So let's calculate first of all CF. What you will get is that CF, when you will factorize it, you will get d minus d, and then you will get a plus 2, here plus and this over here minus. You will get this expression, and then you will have d plus d dash is applied on z is equal to 0. Correct? Is it correct? Yeah. So of course now it is very simple, you can easily solve it. You will get z is equal to e to the power ax 2x f1 of the quantity y minus x plus f2 of the quantity y minus x, correct? Yeah. Okay. Of course this is a homogeneous, this is a non-homogeneous, right? Expression. This is a homogeneous expression, this is not homogeneous expression, right? So we got CF, this CF. Y minus x plus f2 times y minus x, right? So let's see how we'll find the pi now. So let's calculate pi. Okay. So let me raise this. Yeah. So let's see pi. So how we'll find pi? Well, we are just now factorizing this expression. So now let's evaluate this. So pi will be basically equal to 1 upon d plus d dash multiplied by d plus d dash minus 2 applied on sine of x plus 2y. So let's set it equal to t for now. Okay. So from this, when we are going to evaluate this expression, so what we are going to get is that d dash d plus d dash minus 2 applied on t, applied on t, it must be equal to what? It must be equal to this expression, sine of x plus 2y. Or let's first of all do it with reference to this, because you already know how to solve such kind of expressions, right? That is why. Okay, so when you will open it, you will get p plus q is equal to sine of x plus 2y. So apply Lagrange's auxiliary equation, so you will get dx by 1 is equal to dy by 1 is equal to dt by sine of x plus y, right? You will get x plus 2y, sorry, x plus 2y. So from this you will get y is equal to y minus x is equal to some constant c1, and then you will just substitute that dt is equal to sine of x plus y dt. So you can say it like x plus y can be as 2x plus y minus x, and what is y minus x? It is equal to c1, right? From this expression y dx is equal to dy, you will get y minus x is equal to c1, right? So this, now you can easily evaluate this expression, whatever, sorry, dx over here, you will get some value, some expression of t, then you will again put it over here, and when you will put it, from this what we will get, we will get the expression as it will be equal to sorry, negative cos x plus 2y by 3. We will get this expression. Now we will substitute it over here. So let's see what we are going to get when we substitute over here. So we will get 1 upon d plus d dash minus 2 applied on this expression, that is negative of the quantity cos of x plus 2y by 3. Right, so let's assume it as z. Let's assume it as z. So from this we will get let me write it directly now. P plus Q minus 2Z is equal to negative cos of x plus 2y by 3. Is it okay? dz is equal to P, d dash z is equal to Q, and it is equal to negative 2Z. Okay? Fine? Okay. So from this, it is equal to plus 2Z. We can say, so dx by 1 is equal to dy by 1 is equal to dz by 2z minus cos of x plus 2y by 3. This is the expression. So from this you will get y minus x is equal to again a constant, suppose c1, and then when you will solve this expression, what you will get is that so we can say x minus y or y minus x, whatever you want to say, you can say it like that. Okay, so from this how we'll solve it? Well, now it's a tricky part, so let me erase this and then we will discuss. Now we can say dz by dx is equal to 2z minus cos of well, we had the expression y minus x is equal to constant, right? Or you can say x minus y is equal to constant. Both are equal, both are same, right? So when you will say this, you will get the expression as 3x minus 2 c1, right? Now it is a linear differential equation, an ordinary linear differential equation. How? Because it is dz by dx and it is z and it is a function of x. It is a linear differential equation which you can easily solve it by finding the integrating factor e to the power into the pdx, and then you can solve it, right? So I leave this to you. You can easily solve this expression, right? Understood? And of course, you have to remember that in particular integral there will be no arbitrary constant after you evaluate everything, right? And in fact, whenever you integrate also, there won't be any arbitrary constant, right? Okay. Yeah, it was auxiliary equation, so that is why we had constants in this case, but that also is not required after you solve all this, right? Because particular integral don't have any arbitrary constant. Okay. So from this you will get some result that z is equal to the final result as pi as it is equal to 1 upon 39 When you solve everything, 2 cos x plus 2y minus 3 sine x plus 2y, right? Okay, this is the expression which you will get final as pi, and we know the CF, just add them, you will get the complete, that is the general solution of this question, right? So let's see reducible to PD with constant coefficients. So let's see how we will do it. So suppose, let's see, there's a question, x square del 2z by del x square minus 4xy del 2z by del x del y plus 4y square del 2z by del y square plus 6y del z by del y is equal to x cube y to the power 4. So how we'll solve it? Well, so in this case, when we see such kind of problem, we will substitute x is equal to e to the power x and y is equal to e to the power capital Y, because over here we can see that the degree of the variable and the order of the expression is same. The degree is 2, order is 2. Degree is 2, order is 2. Degree is 2, order is 2. Right? Degree is 1, order is 1. So basically, if the degree of the variable is equal to the order of the derivative, then in that case, we say this, we use this substitution. So when we use this, we will have that x is equal to natural log of x and y is equal, and capital Y is equal to the natural log of x, natural log of y, right? So we get del z by del x is equal to del z by del capital X dot del capital X by del x plus del z by del capital Y by dot capital Y by capital X. But this expression is 0, so we don't need to worry. It is equal to 1 upon x del z by del capital X and del z by del y. Similarly, it will be equal to 1 upon y del z by del capital Y, right? This expression. So we can say that del z by del capital X is equal to x del z by del y, del x, and del z by del y, capital Y, is equal to y times del z by del y. Correct? Correct? We get this expression, right? Now we know this expression, so that is why we can say that x square del 2z by del x square is equal to del 2z by del capital X square is equal to x square del 2z by del x del small x square, right? From this expression only we can say it, right? So like this we can say for this also, and for everything else. Okay, so when you solve it, you will get the whole expression. If you say this as d and this as capital D dash, then you will get the expression as d minus 2d dash of this multiplied by d minus 2d dash minus 1 is applied on z is equal to e to the power 3x plus 4y, capital Y and capital X, right? So this is how you solve for such kind of expressions. When you see the relation between degree and order of the derivative, then you can easily say what substitution you have to make. For example, in this case it was this one. Okay, so this was a basic thing which I need to tell. Now let's see non-linear PD of second order. That is the last topic of our today's video, and heat equations and another topic I will cover in separate videos in like 5-10 minute video, because it's like totally a different topic. So that is why I will discuss in different short videos, right? So don't need to worry about that. Let me erase this. So let's discuss non-linear partial differential equation of second order. So basically it is a equation, it is a partial differential equation which includes at least R or S or T, or can include any of them, right? But it must have at least one of them, and no other higher derivative must be involved in the equation. So you can't have del 3 by some expression, you must have only R, S or T, or you can have a first order also, but R, S and T are compulsory. Not all, you can either have R, you can either have S, you can either have T, you can have R or S, you can have S or T, you can have R or T, or you can have all of them. That's no issue. but at least one should be there of R, S and T, right? So if I want to express its general form can be given as f of x comma y comma z comma p comma q comma r comma s comma t is equal to 0, right? So we have this expression, right? Okay. So we are going to find its solution using the Monge's method. Its solution is founded by using solution by Monge's method, right? So we'll find its solution using Monge's method. Okay. So let's see it. So which form we will study? Like in that case, in Lagrange's linear partial differential equation, we studied TP is equal to R. Here we will study R plus SS plus TT is equal to some V, right? Okay, where R, S, T, V are the functions of R, S, T, V are the functions of P, Q, X, Y, and Z, right? Okay, okay. So now let's see how we'll solve this expression. So using Monge's method, what we are going to do is first of all, let me raise this, then we will discuss it. So we had this equation R plus SS plus PT is equal to what? Is equal to V. We know that dz is equal to p dx plus q dy. We had derived this expression, right? And what is then dp? It is equal to del p by del x dot dx plus del p by del y dot dy. Correct? Okay. Now notice one thing that p is equal to del z by del x. So del p by del x is equal to del 2z by del x square, right? I told this expression already, right? And similarly del p by del y is equal to del 2z by del x del y. Okay? So this is equal to r dx plus this, okay, plus t dy, okay, and similarly del q by del x dx plus del q by del y dy is equal to the expression s dx plus r dy, right? So from these two you can solve for r and s, right? You can solve for r and s. So you'll get the expression as let me erase this one. So you'll get r is equal to what? R is equal to the expression dp minus s dy by dx, and we will have t is equal to wait a minute, what I wrote, it is equal to rs plus, yeah, of course, right, it will be t, right? Sorry. Okay, so here we will get t is equal to dq. Of course, del q by del y is del 2 z by del y square, which is equal to t, not r. R is equal to del 2 z by del x square, right? Is equal to del q minus s d. So this is small s, right? Minus s dx by dy, right? This is the expression for r and t, right? And now we will substitute these value into the equation of into our this equation. So let's see what we'll get. Let me erase this. So when you substitute this, you will get r times the expression dp minus s dy by dx plus s times the expression, sorry, s is as it is. What is t? T is dq minus s dx small s divided by dy is equal to v, right? So we get this expression, and then we can simplify it, and when you simplify it, you will get r dp dy plus t dq dx minus v dx dy, right? This expression minus s times r dy whole square minus s dy dx plus t dx whole square is equal to 0, right? We get this expression. Now Let me see, is it fine? Yeah. Okay. Now, this expression is only possible. This expression is only possible because it was derivatives and all. When this expression and this expression are zero, right? Why? Because again, I told you all, it is because they all involve derivatives, so it's not always true. Because it has to be always true, so that is why this expression, these two expressions, these two coefficients have to be always equal to zero. So we get from this r dp dy plus t dq dx minus v dx dy is equal to 0, and we have r dy whole square minus s dy dx plus t dx whole square is equal to 0, right? We have these two equations which we need to solve now, right? From the coefficients, we just say, if you remember, if I say x square plus y square is equal to 0, then that is x is equal to 0 and y is equal to 0 for x and y belong to real numbers. Remember this, right? If it has to be always true, correct? Okay, that is what I'm applying over here, right? So let me erase this and let's move further. Okay, so we had this expression that r dy whole square minus s dy dx plus t dx whole square is equal to 0. Now it is something which you can factorize: square, then product, then and the square. So you can write it like this: plus is equal to 0, given that a1 b2 is not equal to a2 b2, correct? Okay, so this condition should be satisfied, and so we can say that a1 dy plus b1 dx is equal to 0, or you can say a2 dy plus b2 dx is equal to 0, and along with it the first equation must be satisfied. Which one? This one: r dp dy plus t dq dx minus v dx dy is equal to 0, and dp dy plus t dq dx minus v dx dy is equal to 0, right? So they must be satisfied, they both must be satisfied. So from this you will get the answer. So let's see a question to understand what do I mean from all this. Let me explain using a question so it will be much clearer. So let's see this question. So it states r is equal to a square t. So you can say r is equal to a square t, which implies that r minus at is equal to 0. So from this we can also say that r 1 times r plus 0 times s minus plus minus a square t, sorry, it is square over here, is equal to 0. And if you compare it from the original form, that is r plus s plus t is equal to v, right? So from this we can say that r is equal to 1 and t is equal to negative a square and s is equal to 0, correct? So you remember this equation: r dy whole square plus plus minus s dy dx plus t dx whole square, right? We had this expression, remember this one? So it is equal to dy whole square, s is equal to 0, and t is equal to negative a square dx whole square, right? R was equal to 1. Okay, so dy by dx whole square is equal to a square. So from this we can say that dy by dx is equal to plus minus a. We can say this expression. So we can say that y is equal to plus minus ax plus c. We can say this expression, right? So from this we can say y minus ax is equal to c1. We can say c1, or y plus ax is equal to c1, right? So these two are the expressions which we have got right now. Okay. Now we remember the second equation. It was like it was r dp dy plus t dq dx minus v dx dy is equal to 0, we had this expression. So we have dp, what is the value of dy? It is equal to plus minus ay, it is equal to plus minus a, right? So instead of writing plus minus a dx, I write just a dx, so calculation becomes a bit easier, right? Okay, plus what is t? It is minus a square dq dx, v is equal to 0, so it is equal to 0. So from this we get the expression that dp is equal to a dq, we get this expression. So we get p minus aq is equal to some constant c2. Now again, since it's plus minus this expression, so we have this answer also, plus AQ is equal to C2, right? Because here we had two values of dy, negative A and plus A, correct? Okay. So from all this, we can say that P minus, let me write it, let me erase this, then I will write. So from this we can say that P minus AQ is equal to, is a function of y minus ax, and P plus AQ is a function of y plus ax. We can say this expression, correct? So from this we can say that P is equal to 1 by 2 times the quantity f of y minus ax plus g of y plus ax. Similarly, you can solve for q also. It's just you can easily solve for these variables. It is very easy. It is just simultaneous linear equations in two variables, which you know how to solve, right? So from this you can solve for q, and then you know that dz is equal to p dx plus q dy. So from this you can say that z is equal to the integral of p dx plus q dy plus some arbitrary constant. We have this expression. So we know how to find, so we have the value of p, we have the value of q, so you can just substitute it and you will get the answer. So this is how you will solve such expressions. And there's one more thing which I need to discuss right now, and I have to be a bit fast because it's like going too long. That is why. So we had this expression RR SS TT is equal to V. So it can have, it can be hyperbolic, it is hyperbolic, it is parabolic, it is elliptical, if it follows such conditions. Let me tell the conditions. If it's like s square minus 4rt is greater than 0, if s square minus 4rt is equal to 0, of course these are capital variables, these are coefficients. Or if it is elliptical, if s square minus 4rt is less than 0. So let me check the conditions, are they correct? Yeah. So this, yeah, this is okay. So with this we come to an end of this lecture, and I hope that you enjoyed this lecture. And if you did enjoy this, then please like, share, subscribe my channel, and please support this video. And of course the remaining portion like heat equations and all, I will cover in separate short videos. So because they are just an application of these things, so that is why I'm not covering it in one shot. And if it is required, I will cover it in some short videos. You can watch that. Okay. So if you did enjoy this video, then please like, share, subscribe my channel, and please support this video. Bye bye, take care, and all the best. Hello everyone, this is Aditya. Before starting this video, I want to clarify one thing, that I am really not well, and I was never in the condition to record this lecture, but to help you all, I am recording this lecture. So please bear with me, because I might sound very much down, or maybe very much less energetic than my other videos. So please bear with that, but still I tried my best to provide you the best content which I could give. So please do understand this problem and please bear with it. And now let's start with the video. And I want to apologize also, because I could not make the video earlier because of my health. I really did not got time actually to make the video, because I wasn't in the condition. Right now also I'm not in the condition to record this lecture. Still I am doing. I really apologize for being so much delayed, and I again say sorry, because in the lecture I might sound really different again. So I am really sorry for the further video also, but I hope that you will really understand this lecture and you will do great. Hello everyone, this is Aditya, and today we are going to cover linear algebra in a one shot for Engineering Mathematics 2. But before that, please do like, subscribe my channel, and please support this video and please support my channel so that this video can reach to maximum number of people. And now let's start with the video. Okay. So first of all, we will see system of linear equations in linear algebra, right? And of course, I have made algebraic structures and ordinary differential equation one shots before, so you can check that out. And of course, now here coming to the topic. And I'm a bit unwell, so please bear with me, okay? So now let's start. So system of linear equation. Well, what do I mean by system of linear equation? Well, equations involving the variables with degree 1, right? Basically, that is it. So if I want to say, suppose 2x plus 3y is equal to 7 and 5x plus 2y is equal to 3. So this is a system of linear equation, right? Why? Because it involves the variables with degree 1, okay? So how do we write it in a general form? Like suppose you have m equations and there are n variables. Let's see. So this is the coefficient, it is a variable, and likewise this 1 n xn is equal to b1. What is the next coefficient? It was a11, so it will be a21, x1, a22, x2 till a2n xn is equal to b2, right? Is it correct? Okay. And it will go so on. And suppose there are m equations, which means it will be am1 x1 plus am2 x2 till amn xn is equal to bm, right? You can understand this, okay? So this is a linear equation, the system of linear equations involving m variables, I mean m equations and n variables, right? Okay. So how do we express it in a more compact form? Well, we use a matrix form to represent it. First of all, we will see with respect to this, then we will come to that, okay? So matrix form is given by ax is equal to b. Well, don't worry, what does it mean? I'm telling. So here A is the coefficient matrix, right? So how do we express this? Let's see. Okay. So you have the coefficients 2, 3, 5 and 2, right? So A in this case will be equal to, A is equal to 2, 5, 3 and 2, right? This is with respect to the variable x, the coefficients of x, and this is the coefficients of y multiplied by, I mean, of course not in this one. Now if you want to represent it in the form of ax is equal to b, what you will do is that you will write 2, 3, 5, 2 multiplied by what is x. X is just the set of variables which are given here, x and y. There are two variables, so write x and y is equal to 7, 3. And of course when you multiply it, what you will get? You will get 2x plus 3y and 5x plus 2y is equal to 7, right? And this is of course the same equation, right? Just we represent it in a more compact way. Similarly, you can write a in this case as coefficients a11, a21 till am1, and this goes till a1n, and this will go till amn, right? So this is how you represent the coefficient matrix in a general way. And the variable is of course x1 till xn, and this is the coefficient with respect to x1, and this is still xn. Of course I did not wrote in the between, but you can understand it, okay? So again ax is equal to b. What is b? B is equal to b1 b2 till bn, right? So basically you can write it like this, even a11 till am1 till and this one a1n, and this goes till amn multiplied by x1 till xn is equal to b1 till bm, right? I were understanding that how am I getting this. Okay, so let me raise this and then we will discuss further. So let's see that when we say the system of linear equation is consistent and when it is not consistent, I mean inconsistent. So for consistent, for being consistent, it must have at least one solution, right? And for inconsistent system, there will be no solution, right? Of course, in this case, it can be finite, I mean one solution also, and there can be infinite solution also, depending on the conditions, right? So basically, this is what I wanted to say, and now we will see further. So let's see that how do we solve linear equations, the system of linear equation. Well, there are many methods like Cramer's rule, the matrix rule, which you all know. So we will be sticking towards Gauss elimination method only, which is important also. Gauss elimination method, right? Okay. So let's see that what is it actually. Okay. So for this, you must know about elementary row operations, right? What are those? Suppose you have a matrix, so in that case you can interchange the ith row, I mean ith and jth rows. It means Ri can be replaced with Rj, right? Like this. And multiplication of the ith row by a non-zero number, suppose lambda, right? You can do multiplication like this, right? Ri, it can be written as R, can be multiplied with this, right? Okay. And addition of lambda times the jth row to ith row. Well, don't worry that what am I saying all this. Of course, we will see example, then you will understand it better. I'm just telling you theory right now, okay? So don't worry about it. So it will be Ri is replaced with Ri plus suppose lambda times Rj, right? This is how. So of course I've written everything. Now we will see the problem to understand the theory better, right? Okay, so give me a minute to raise this. So now we have a question to solve, and let's see how we are going to solve it using Gauss elimination. Well, you can write the coefficient matrix as 1 2 1, right? 1 3 2, right? You can see the coefficients over here, and 1 1 3, right? This is the coefficient matrix, okay? And what is B matrix? It is 4 7 9. So to apply Gauss elimination method, you should know what is meant by augmented matrix. Well, let's see what is it. So suppose you have this matrix and this matrix and you want to augment them, I mean to club them together, right? So what we are going to do is that we are writing it like this, and it is 1 2 1 1 3 2 1 1 3, and you have clubbed this matrix over here 4 7 9, and this is called a augmented matrix, right? It's just a fancy name, but it's just this, nothing else. The clubbing or the combination of two matrices like this. You just clubbed it, right? Okay. So let's see how we are going to now solve. Well, now we are going to apply elementary operation methods for row, of course. Okay. So notice that this is your row 1, and this is your row 2, and this is your row 3, right? I hope this is understandable. It is simple. Okay. So let's see. Okay. So this is your augmented matrix, write it like this. We get over here 1 2 1 1 3 2 1 1 3, and here get this. Okay, so okay, we are going to apply elementary operations, but how are we going to apply? Well, basically you have to create zeros. What do I mean by that? Suppose here it is 1, so beneath it you have to make all the numbers as 0 to solve the equation, and in this case you have to make a 0 over here to solve the equation. Well, let's see, then you will understand it better. Okay, so how we are going to create a 0 in the second row? Well, if you remember, we can do r2 as r2 minus 2 r1. Why? Because twice of r1, when subtracted from it, we will get a 0 over here, right? Let's see, 1 1 1, right? And this will become 0, and 3 minus 2, it will become 1, and negative 2, this will become negative 1. You get 1 2 3 and 4. 7 minus 8, it will become negative 1 and 9, right? Is it correct? So now what we are going to do is, we have got 1 0. Now we need to create a 0 over here also, so that there are all zeros beneath this number, right? So R3 we will change, we'll apply the elementary operation R3 minus R1, right? Is it correct? Okay. So you get 1 1 1, and here 0 1 negative 1. When you subtract, you get 0 in this case, and you get 1 over here, and you get a 2 over here, and you get 4 negative 1 8, right? Okay, let me erase this. I'm sorry, it was a 5 over here, because 9 minus 4 is 5, sorry. Okay, so now you get 1 1 1 0 1 negative 1 0 1 2 augmented 4 negative 1 5, right? You get this thing. Now we can make another 0 over here if we subtract r3 from r2, right? Well, we can. So we get r3 as r3 minus r2, right? Simple, very simple. 1 1 1 0 1 negative 1 0 1, 0 0, and then it will become 3 4 negative 1, and this will become 6. Okay, we got zeros over here, but what is its use? Well, it has a great use. Let me erase this and then I will explain. So if you remember that originally the matrix was like this, Ax is equal to B, right? Remember this? Okay. So in this, the coefficients were, this was for x1, this was for x2, and this was for x3, right? Is it correct? Okay. So now we'll place the variables at the places where they are required. What I mean is that this one was for x1, this was for x2, this was for x3. So you write x1 plus x2 plus x3 is equal to 4. This is your equation number 1. And what you get is 0 times x2, x1, plus 1 times x2 plus negative 1 times x3 is equal to negative 1, and 0 times x1 plus 0 times x2 plus 3 x3 is equal to 6. And now you know that why we were trying to make 0 in this row, because we can easily then find the value of the last variable. In this case we get x3 as 2, and now it is very simple. You can just substitute the value of x3, so you will get the value of x2 in this case, and then you will get the value of x1. I'm not solving that, it is very simple. So this is called, what is this matrix called? Well, it is called echelon form. Echelon form, right? Okay, did you understand that what is it actually? And when you are substituting the variables back to their places, it is called back substitution. This is back substitution, right? Okay, don't worry about the echelon form, we will see it in some more time in great detail. but for now understand that this is echelon form, and basically in this case you are going to get something called pivots, and using that you are going to understand more concepts. Okay, so don't worry about it, just wait. So this is how you solve it using the Gauss elimination method. So first it is to create augmented matrix, then you go to echelon form using the row operations, and then you use back substitution, right? Okay, so this is how the process is going to find the values of the variable using the Gauss elimination method. Okay, so let me erase this and then we will be right back. So this was the echelon form which we had got, and in this we are going to discuss about pivots. What is it? Okay, so this is your first variable, I mean the first number or first entry. So for this case, if this number is non-zero and is surrounded by zeros, I mean beneath it it has all zeros and in the left it has zeros. Of course there's no number at the left, so we don't care about that. So we care about that if this number, it should be non-zero and has zeros beneath it, then it is called a pivot, right? Okay, is there any other pivot over here? Well, if you consider this one, it has a variable, I mean a number which is not zero placed beneath it, so of course it can't be, right? Okay, so can it be a pivot? Well, it is surrounded by a zero beneath it, right? And towards the left also, which means that this is also a pivot, right? And in this case it is surrounded by zeros towards the left, and of course there is no number in the beneath, which means that this is also a pivot. So in this equations there are three pivot, right? So number of pivot in this case is 3. Well, why am I telling this? Well, let's see. If number of pivots is equal to the number of unknowns, then we have unique solution, right? Do you understand this? If the number of pivots is equal to the number of unknowns, then we get a unique solution. Notice that here the number of pivots was 3 and the number of variables were also 3, which means that that is why we got independent, I mean unique solutions in this case, right? Not independent, sorry. Okay, so I hope you understand what is a pivot in a basic term, and of course we will see some questions to understand it better, right? Let me raise this, then I will be right. So this is an augmented matrix, and now we are going to solve it using the Gauss elimination method, right? Okay, so let's see. Well, in this question I will leave the calculation part to be done by you only, but I can tell the operations that what you are going to do. Well, I won't tell that. Okay, you have to do it on your own. I can tell that what will the final matrix which you will get. Let me see, what is it after elementary row operation. You are going to get 1 0 0 1 1 0 0 negative 1 0, and in this case 4 negative 1 and then 6, right? Okay, so notice that in this case when you substitute the variable over here in this row, you are going to get 0x1 plus 0x2 plus 0x3 is equal to 6, which means that 0 is equal to 6. Well, it is clearly a wrong statement, which means that this system was inconsistent, right? I mean, is inconsistent. Okay, is it fine? Because you won't get a solution because of this row, right? I hope you're understanding. You just substitute the variables over here, right? Okay. Well, there's one more thing over here. Suppose, just assume that if it was not 6, it was 0. Suppose it was 0. Then in that case, you would be getting over here 0, which means 0 is equal to 0, and it is clearly a valid statement. So in this case, you would get infinite solution. So you can just see that just by changing the variable towards 0, you got infinite solution, right? And this is how the things are going, right? Don't worry about it. I hope that you're understanding it and you're enjoying the video. And one more thing to be noted over here is that this is a pivot. Of course it is, since it is 0 beneath it. This is a pivot since it has 0 towards its left and in its beneath also. But notice that there's no pivot in this column. Why? A pivot cannot be 0, so these two are eliminated. And this is of course surrounded by 0 in its beneath, but it is not surrounded by 0 on its left because of this one, which means that due to this the pivot is not there, which means that this column don't have a pivot, and the column which don't have a pivot but still it is satisfying this equation, then the variable of that column, in this it was x3, is a free variable. Free variable, I mean, you can substitute any value of x3 to solve this equation, right? The whole equation will be dependent upon x3, right? If you want to solve, I can show x1 plus x2 is equal to 4. Of course you have to do the calculation on your own, okay? And x2 plus, I mean, minus x3 is equal to -1, right? And the second one, the third one is 0 is equal to 0. It don't mean anything. And notice that we had assumed x3 is a free variable, okay? So let's assume x3 as alpha, right? Okay. So we get x2 is equal to -1, I mean simply alpha minus 1. And I'm going to substitute x1 over x2 over there. You get x1 is equal to 4 minus x2, which is equal to 4 minus alpha minus 1, which is equal to 5 minus alpha. So the whole equation is dependent upon alpha. And what is alpha? Alpha is simply x3, right? So that is why this is a free variable and rest all are dependent upon this. That is why it is called a free variable and these are called the dependent variables, okay? So let's see further. So now we are going to see the rank of a matrix. Let's see how we find it. Rank of a matrix. A matrix. So rank, suppose your matrix is A, is equal to the number of pivots. Suppose R. Basically number of pivots is represented by R, okay, in many cases. So this is how you find the rank of a matrix. But what's the need to find the rank? Let's see. So to check for inconsistency, for inconsistent system, the rank of A will not be equal to the rank of A augmented B matrix. And this is how you will check. You can check for inconsistent system, but of course we also know other methods also. We don't need to check for rank because you remember the previous example, right? But still this is also a method, okay? And for consistent unique solution system, the rank of A is equal to the rank of A augmented B matrix and is equal to n. Well, what is n? N is the number of variables, right? The number of variables. Okay, I hope it is clear. And for consistent infinite solution system, the rank of A is still equal to the rank of A augmented B matrix, but in this case, suppose this is equal to K, the K is less than the number of variables. So in that case, you will get infinite solution. Okay. So this is how the rank helps us to determine the consistency of a system and the number of solutions, that will it have a infinite number of solutions or will it have unique solution, right? So this is another question, and in this also we need to solve for this augmented matrix. Well, let's see. I won't solve it on the board. If you want, I will just upload the solution. I'm right now just writing the answer, that what we are going to get. Since of course we have very less time, and if I devote the class time towards the calculation portion, you won't learn anything. I'm worried about to make you learn new things, not about the calculation part. This is just very simple thing which you can do on your own. Okay. So you get basically A augmented B one zero zero negative 1 2 to 0 140 beta. I guess it is beta plus 1. So on solving that augmented matrix, you are going to get this matrix, right? It is a very big matrix, of course, but you should know the basic method, that you have to create just zeros beneath these numbers, nothing else. And in the row, you have to try to make as many zeros as you can. Okay, this is the basic idea. So notice that if beta is equal to negative 1 is not equal to negative 1, in that case the system is inconsistent. Why? Because in this case it will be like 0 is equal to some non-zero quantity, which is not possible if beta is negative, if beta is not negative 1, right? So in this case it is inconsistent, right? And notice that if beta is equal to negative 1, in that case it is consistent, right? Okay, is it fine? It is consistent. But does it have infinite solution or finite? Well, we need to check. Okay. So how many pivots are there in this case? Well, this is a pivot. Of course, 2 is not a pivot because it is covered by, it is having zeros beneath it, but it is not having 0 towards its left. Similar is the case with this and all this number. Okay, 1 is a pivot in this case, 2 is a pivot, right? Okay. So we have 3 pivots in this case, and how many unknowns are there? There are 5 unknowns, which means that the rank of A is equal to 3, since the number of pivots is 3 in this case, and the rank of A augmented matrix B is also 3, right? Notice that when you substitute 0, it will become 0 in this case. So it also becomes a matrix with 3 pivots, right? You can see easily. You won't get any other pivot except these 3, right? So they are equal, but the number of variables is 5, which means that 3 is less than 5, which means that solution, there are infinite solution in this case, right? Okay. And one thing to be noticed over here is that x1, x2, so x2 and x5 are free variables, right? Are free variables. Why? Because they don't have pivot. That is why they are free variables. So you can assume x2 as alpha 1 and x5 as alpha 2, and you can write all the variables x1, x3 and x4 in terms of alpha 1 and alpha 2, and you will get the solution, right? But there will be infinite solution which will depend upon the value of alpha 1 and alpha 2, right? So this is how you solve a linear equation which has infinite solution. You will find out the free variables and then write the dependent variables in terms of x2 and x5, right? you can of course do it. You have all the equations. You can just express x1, x3 and x4 in terms of alpha 1 and alpha 2, and then you'll get the solution, right? Infinite solutions. Okay, so with this we come to an end to the system of linear equation, and now we are going to start with field and vector spaces, right? So now let's start with fields, right? Okay, let me write the definition first of all, then we are going to see it further. So let F be a non-empty set which is closed, under two binary operations. I hope you know binary operations. If you don't know, you can check out my video of algebraic structures so that you can get a clarity. I can't discuss that right now because of lack of time, as the lecture will go very big. Binary operations, okay, denoted by, in most of the cases we will be only dealing with the plus and the multiplier sign. So that is why I'm going to represent it with plus and multiplication sign, right? Okay, then if this is a field, if for all a comma b comma c belonging to f, the following property holds. Let's see what are the properties. Well, there are many properties in this case, but don't worry. The first one is very simple, the commutative law. A plus b is equal to b plus a, and this one, right? This is the first property. Then there's associative law. Of course, I'm not writing the associative law because you know this. I mean this associative law, the term I'm not writing. A this, okay, and this is equal to a, right? Like this. And the distributive property holds in this case. Okay, is it fine? Okay. Fourth property, there exists 0 comma 1 belonging to f, satisfying what, a plus 0 is equal to 0 plus a is equal to a, and a operation 1 is equal to 1 operation a is equal to a, right? This is how you write it. And for any u belonging to f, there exists a negative a belonging to f such that a plus a inverse is equal to 0. Let's see the sixth property. For any a belonging to f, a is not equal to 0, there exists a inverse belonging to f such that a operation a inverse is equal to a inverse operation a is equal to 1, right? So these are the properties for a non-empty set to be called a field f, right? Under the operations plus and multiplication, addition, multiplication, right? So we will use this idea of field, and we are going to apply it in the concept of vector space, right? So let's see that, and it is a really interesting topic, right? Okay, so now we are going to study vector space. Okay, let me write the definition and then we will discuss it. Okay, a vector space over a field f, and in most of the cases we will be assuming the field as a set of real numbers in this case, right? And okay, let me write the definition, then I will tell one thing. Is a set V of elements of elements called vectors. Well, it is not the normal vectors. In this case, a matrix is also a vector. Okay, so don't worry about that. It is just some terms which we are using. Okay, a polynomial will also be a vector in this case, so don't worry about that. Together with two binary operations um, called vector addition and scalar multiplication. And I'm really not well, so that is why uh, maybe I might sound a lot down than my other lectures, but still try to bear with me because I am also trying my best to record this lecture, but I wasn't in the condition to record this lecture. Still, I thought to record so that I can help. Okay, so please understand this. Okay, so scalar multiplication, if the following axioms hold. Okay, so what is a vector space? A vector space, we are operating over a field F, is a set V of elements called vectors together with two binary operations called vector addition, vector multiplication in the following axioms hold. Well, I hope you did not understand anything what I said. But still, let me tell the condition first of all, and then we will see it using example. Some examples actually, not just a one. So the first property which it should hold is that the closure property u plus v should belong to, suppose let me write it clearly, if u comma v belong to capital V, then it implies u plus v should also belong to v, right? For all u comma v, right? Okay. The second property, if lambda belongs to f, then and u belongs to v, then it implies that lambda times u should also belong to v. This is again the closure property, right? Okay. For all lambda. The third property, u plus v must be equal to v plus u for all u comma v belonging to capital V, right? The fourth property, u plus v plus w is equal to u plus v this associative property. U, v and w are the vectors of the set capital V, right? Okay. The fifth property, there exists this is a zero vector belonging to V. This is called a zero vector in vector space. Of course, a zero matrix, a null matrix is also called a zero vector in this case. So don't worry about the terms right now. Just understand the concept, nothing else. Okay. So such that a plus 0, a plus the null matrix is equal to u. Sorry, it should be u. Why I wrote a, I don't know. For all u belonging to capital V, right? Let me write the sixth property, and what it states, for each u belonging to V, there exists an inverse element belonging to additive inverse belonging to V such that u plus this quantity must be equal to 0, right? The additive inverse. Let's see the next property. Well, don't worry that I'm telling so much properties, the axioms. So how will you remember I'm telling it? Okay, don't worry about it. So lambda times mu u is equal to lambda mu times u for all lambda mu belonging to f and for all u belonging to v, right? This is another axiom, and let's see the eighth axiom. Lambda times u plus v must be equal to lambda u plus lambda v. Lambda belongs to, for all lambda belonging to the field f, and u comma v belonging to f, I mean vector v, vector space. And ninth property, lambda plus mu u is equal to lambda u plus mu u for all lambda comma v belonging towards to r and u belonging towards not r, sorry, the field f, right? But in most of the cases we will be assuming the field as the real number, right? The set of real numbers. So that is why we could have written r over there, but since I've defined over here fields, that is why I'm writing f over here. Okay, don't worry about this. Okay, now this is clear. And last property, for each u belonging to v, there exists one belonging to the field such that one operation u is equal to u. Okay, and this is the identity element, of course. Okay, so I told so many properties. So how we are going to remember this? Well, it depends. Of course, to check for a vector space, you only need the first and the second property. Just these two properties to check for a vector space, right? Do you understand this? Why? Because if you proved the closure properties, then all other properties are trivial, which means that they all are contained inside these two properties. So for any calculation, I am going to use only these two properties, but it depends on your exam that if they want you to prove all the properties, then you have to prove everything. But of course, in general, these two properties are enough to check for a vector space. You don't need to check for this because it will be automatically available after you prove this. And you can yourself check that if you prove these two properties, then these all are trivial. Even if you don't remember in the exam, you can still prove everything if you know these two properties. Okay, so these two are really important to check for the vector space. Okay, so let's see further. We will see some questions, right? I will try to cover some questions, but really I'm not well, so that is why I won't be able to cover much questions, but still I will try my best to provide you the best knowledge in less time so that you can do better, right? Okay, so let me erase this and I will be right back. So in this we have to check that Rn, is it a vector space over R, where R is the field, right? And what is Rn? Well, if I write the coordinate system a comma b, then it is R2, right? And if I write a, b and c, it is R3, right? Since it is formed by this cross product, right? Okay, and similarly for n system, I mean the n tuples, it is Rn, right? So this is how you write it. Okay, okay, so I told this, but how we are going to check for vector space? Well, I said we need only two closure properties to prove this. Okay, it is very simple. Let's see, suppose you have a vector space a1, I mean the Rn set as this one is your first set, I mean the element, you can say whatever. Okay, and this second till bn belonging to Rn. So what was the closure property? U plus v should belong to the vector space, I mean the set v, right? So in this case, if you add them, you will get a1 plus b1, a2 plus b2, right, till an plus bn, and it will be belonging to Rn. Why? because a1 was also a vector and b1 was also a vector. So when you added it, you again got a vector only, right? And similar is the case with the other system, other coordinates, which means that your final result is also belonging to Rn, right? So that is why first property stands. Okay, now let's see the second one, that lambda times u must belong to v, where lambda belongs to, for all lambda belonging to f, in this case it is r, right? Okay, suppose you have x1 x2 till xn belonging to Rn, you multiply by x1 and like this. No, I mean with lambda you are multiplying this whole element. So when you multiply, you get lambda x1 lambda x2 till lambda xn, right? And it is belonging to Rn. Why? Because it is a scalar and it is a vector, so the product is still a vector. That is why this whole expression is still belonging to Rn. So we proved these two properties, which means that Rn is a vector space over R, right? Don't go by my writing, of course. So it means that R2 is also a vector space, R3 is also a vector space over R, right? Remember this. Okay, so now let's see the next question. So we need to now check that is it a polynomial space or not. Again, it is just another way to say about vector space, so don't worry about it. Okay, let's see how we define this polynomial p and t. It can be written as like this. Suppose let me write it simply like this: pt is equal to a naught plus a1t till suppose as ts, right? Where s is less than or equal to n, since the maximum degree is n in this case, right? Okay. Okay, so p1t ast p2t b naught b1t till bsts. I hope you're understanding. This is the first polynomial, this is the second polynomial, right? And now we're what going to do is we are going to add them, right? To check for the closure one, closure property, p1t plus p2t is equal to a naught plus b naught plus a1 plus b1t till as plus bs t to the power s. And notice that a naught plus b naught is a scalar, a1 plus b1 is a scalar, and so it means that this is also belonging to R, I mean the p and t, right? Okay. And the second property, suppose lambda belongs to R, for all lambda times suppose p1t, you can assume p2 also, you can assume anything, right? Suppose p of t, just a general term, c naught plus c1t till cn or csts multiply by lambda at lambda c naught plus lambda c1 t till plus lambda cs ts. Again lambda c naught is again a scalar, this is also scalar, this is also scalar, which means that it belongs to p and, right? Which means that this is a polynomial space over R, right? Is simple. Now we have to check the matrix space over R, right? Let's see. So m cross n can be written as a11 till am1 till a1n till amn, right? Okay. So this is your suppose first one, and the second one, m cross n is equal to suppose b11 till b1n and so on till I mean bm1 till bmn, right? and if you add it, you will get a11 plus b11, and like that. It will be, the general term will be this, right, of the whole matrix. Okay, maybe the representation is wrong, but still I want to just tell, because I can't write everything due to my health right now, but still if you can understand and cooperate a bit. So if you add, you will get these type of expressions only, and which will belong to the matrix mm cross n only, right? And if you multiply by a lambda in this case also, then also it will be still belonging to m cross n. Why? Because lambda is a scalar and these are the vectors, so it will yield a vector only, right? This is how you check for the matrix space, right? Okay, let me see what next we are going to do now. Now we are going to do vector subspaces, right? Okay, so what is a vector subspace? Let's see that. Well, let V be a vector space, and of course over F, and let W be a subset of V, right? Then W is a subspace of V if W is itself a vector space over F, right? Okay, with respect to same operations, right, as in V, right? Basically, if W is a subset of a vector space and that W is itself a vector space over F, then it is called a vector subspace. That variable, I mean the vector W, okay, the set W, I mean. So the criteria for vector subspace, well, let's see what are the criteria for vector subspace. First one, U plus V should belong to W, and second, lambda U should belong to W. U comma V belong to for all belonging to W and for all lambda belonging to F or the field, right? Just the similar condition, the same condition as in the case of the vector space, nothing else. Okay, so we have a question that U is equal to A comma B comma C such that A is equal to B is equal to C, and this U is a subset of R3. So we need to prove that this U is a vector subspace of R3 even. Okay, so let's see. So what are the conditions? Well, since A is equal to B is equal to C, which means you can assume the one vector as A comma A comma A, like this, belonging to U. You can assume B comma B comma B belonging to U. You add them, you get A plus B, A plus B, A plus B, which is again belong to you. What did I just did? Okay, I assumed a variable A first, and since A is equal to B is equal to C, which means that I choose any variable, it will still be equal to a single variable, that is A in this case, and in this case it will be equal to B. I mean all the three coordinates are same, right? So this is the first vector, this is the second vector. I added both the vector, the closure property U plus V belonging to U, I mean U, right? This is your U, this is your V, and U comma V belongs to U, right? Okay, so now notice that this and this all have the same value, just like the condition, which means that this itself belongs to U, right? Okay, first is checked. Now let's multiply by lambda A comma A belonging to, and this will be equal to, of course you need to know that what statements you have to write, of course, that lambda belongs to the field or R, right, like that, and then you need to solve. I am not writing everything because I'm not well. Please cooperate with me. Okay, so you just multiply, you get lambda a belonging to U again. Why? Because all the variables, all the elements are same as per the given condition, which means that U is a vector subspace of R cube. I mean R3. Okay. So now let's coming to the linear combination of vectors. Let's see what is it. So now coming towards the linear combination of vectors. Well, let's see. An expression of type lambda 1 v1 plus lambda 2 v2 till lambda n vn such that lambda I mean lambda 1, lambda 2, everything belongs to real number is called linear combination. I'm not writing everything of vectors v1 till vn belonging to suppose some vector space v. Okay, so don't worry about that term, you don't even need to write that. Okay, so basically if the vectors v1 till vn can be expressed as a linear combination like this, then this thing is called linear combination of vectors. Okay, let's see with the help of an example, right? Okay, so suppose the question states let alpha is equal to 435 transpose and beta is equal to 013 transpose, gamma is equal to 211 transpose, and delta is equal to 422, right? Okay, so express alpha as linear combination of the vectors b comma I mean beta comma gamma. And for your practice you can do this question: beta as linear combination of gamma and delta, right? So we will be doing this one, and this is your homework or your understanding purpose. Okay, solution. Well, alpha is basically equal to 435, beta is equal to 013. I mean it's transpose, so it will look like this, 013, and gamma looks like this, right, since it is a transpose. So to express alpha as the linear combination of beta and gamma, we need to write alpha as lambda 1 beta plus lambda 2 gamma, right? And we need to solve for lambda 1 and lambda 2. Let's solve it and let's see what we get. So now let's express alpha in terms of beta and gamma, I mean as the linear combination of beta and gamma. So what was alpha? Alpha is 435. 435 is equal to lambda 1 times what is the value of beta? 013 plus lambda 2 times 211. You can solve. 435 is equal to 2 lambda 2 and lambda 1 plus lambda 2, and this is 3 lambda 1 plus lambda 2. You can solve this equation very easily. What you will get is that lambda 2 is equal to 2 and lambda 1, how? Well, it is very simple. Still I'm telling, 4 is equal to 2 lambda 2, which means lambda 2 is equal to 2, right? And lambda 1 plus lambda 2 is equal to 3, which means lambda 1 will be equal to 3 minus lambda 2, and lambda 2 is 2, so we get lambda 1 is equal to 1, right? And this is the value. But still our job is not done. We need to check in the third equation also, because there's a possibility that these two roots or the solution for lambda 1 and lambda 2 may not satisfy this equation. If it does satisfy the equation, then alpha can be expressed as the linear combination of beta and gamma, and if it don't satisfy this equation, then in that case it can't be expressed as the linear combination of beta and gamma, right? This is how you check. So 5 is equal to 3 lambda 1 plus lambda 2. Let's substitute the value. 3 into 1 plus 2. Yeah, 5 is equal to 5, which means that alpha can be expressed as linear combination. LC means linear combination for my simplicity, okay? Try to understand it as the linear combination of beta and gamma, right? Given by lambda 1 is this, lambda 1 beta plus lambda 2 gamma, which implies alpha is equal to 1 times, I mean, beta plus 2 gamma, right? Like this. But suppose if it was a 6 over here instead of 5, then if you would solve, you will get 5, which is not equal, since 3 into 1 plus 2 was 5, and since 5 is not equal to 6, in that case we cannot express alpha as the linear combination of beta and gamma. So this is how you check for the linear combination of vectors, right? Okay, now let's see linear dependency, I mean the linear independent vectors and linearly independent variables. So let's see what do we mean by linear independence of vectors. Let's see. Suppose let V be a vector space, right? Of course, we are dealing with vectors, so we will need vector space, of course. A finite set of vectors v1, v2 till vn of capital V, this is capital V, is said to be linearly independent if till lambda and vn is equal to 0, implies lambda 1 is equal to lambda 2 is equal to lambda is equal to 0. Only then it is called linearly independent, right? The vectors then only will be called linearly independent if lambda 1 is equal to lambda 2 is equal to lambda n is equal to 0 for this linear combination, right? I've been understanding this, and we will understand it with respect to a question also. And of course, lambda I is a scalar, right? And vi is vectors, of course, simple, right? Let's understand it using a question also, and then we will move further to vector span, right? Don't worry about these terms, I mean not the vector span, sorry, linear span, okay? Don't worry about these fancy terms, they are just terms, right? Only, nothing else. They are very, very simple. It is very simple topic actually, if you try to understand it with pure dedication, because it is simply the vector space and everything. It is very simple. If you know the method, you can do the problems. And of course, I never teach for marks or anything like that. I teach for knowledge, because that is my passion. That is why I don't care that we practice many problems or not, but I try to make sure that you understand every concept. Just if you are done with the concepts, you don't need to practice much. You can apply them directly, right? Of course, you need some practice, but not that much to like rote learn the questions. No, you don't need to do that. You just need to understand the concepts, nothing else. That is the beauty of mathematics, nothing else, right? Because if you understood the concept, you can do anything in mathematics. But if you are just learning the questions for sake of marks, then mathematics is really tough. But if you love mathematics like anything, you are loving the concepts of mathematics, then you will be very much great in mathematics. Very much, I can guarantee that. Maths is not a subject, it is a part of life. Remember that. So this is a question that we have to check the linear independence of these vectors. So how we will check? Well, suppose V belongs to, I mean, We need to check for lambda 1 v1 and lambda 2 v2, lambda 3 v3 is equal to the 0, right? Of course it should be a 0 matrix, but for now just understand it. So lambda 1 times 1 negative 1 0 plus lambda 2 times 0 1 negative 1 plus lambda 3 times 0 comma 0 comma 1 is equal to 0 comma 0 comma 0, basically the null vector. Okay, so you get lambda 1 plus 0 times lambda 2, just add the components, right? Like you do, you add the x component, y component, z component. Similar is the case over here also. Plus lambda 0 lambda 3, right? Okay, comma lambda 1 negative lambda 1 plus lambda 2 plus 0 lambda 3, right? Are you understanding what I am doing? Wait. And then this 0 lambda 1 plus, I mean negative lambda 2 plus lambda 3 must be equal to 0 comma 0 comma 0. Well, what did I done just now? Let me explain it. I hope that you must be having confusion. You multiply lambda 1 with these elements, you get this negative lambda 1 0 plus lambda 2, you get over here 0 comma lambda 2 comma negative lambda 2 plus 0 comma 0 comma lambda 3. Now add them. Add, right, the components you are going to add, and you're going to get this, right? That is what I did in a one step. Lambda 1 comma negative lambda 1 plus 2 comma negative lambda 2 plus lambda 3 is equal to 0 comma 0 comma 0. So from this you can just match the coordinates. You get lambda 1 is equal to 0, and you get lambda 2 is equal to lambda 1 only, which is equal to 0, and lambda 3 is equal to again lambda 2, which is equal to 0, which means that lambda 1 is equal to lambda 2 is equal to lambda 3 is equal to 0, which means that the given vectors are linearly independent, right? Okay, now let's see a question in which the vectors will be linearly dependent instead of being independent. Let's see that question. Okay, so these are the given vectors and we have to check for the linear independence in this case. Let's see. Okay, lambda 1 v1 plus lambda 2 v2, it must be equal to 0, right? Simple condition. Lambda 1 0 comma 0 plus lambda 2 1 comma 2 is equal to 0, which means that lambda 1 will get vanish actually, plus lambda 2 comma lambda 2 is equal to 0, which means that lambda 2 comma 2 lambda 2 is equal to 0 comma 0 0 comma 0 0 comma 0, of course, which means lambda 2 is equal to 0, but lambda 1 belongs to real number, which means that lambda can take any value, which means that it is not necessary for lambda to take only 0. It can take many values, any value it can take. It means that it is linearly dependent, right? Not independent, because we are not getting the unique value of lambda 1 as 0. We are getting infinite values. Even if we would have get 0 also, 0 comma 1, just two values, still it was independent because there was 1. Lambda has to be 0, lambda I has to be 0 for being linearly independent. All lambda should be 0. I'm repeating again and again, just remember this thing. Okay, so with this we are coming to linear span now. Okay, so let's start with the linear span, and it is simple concept. You need to just practice and understand the concept, nothing else. Okay, so don't worry about it. Let's come to linear span now. So what is a linear span? Let me define it. Okay, linear span of vectors v1 v2 till vn is defined as span v1 v2 till vn is equal to the summation I goes from 1 to n of lambda I vi such that lambda I belongs to R. Well, it is just the linear combination, nothing else, right? Nothing else. Very simple. So basically it is the collection of all vector combinations of v1 comma v2 till vn. Okay, the collection of all the vectors is called the linear span of vectors v1 comma v2 till vn, right? This is how you define the linear span. Okay, very simple, very simple. It is just the linear combination, nothing else. And the name suggests that what is it, it is like what is it, but it is very simple, right? It was just linear combination, nothing else. Okay, so let's see a question to understand it better. Okay, so this is the question, that is the vector, this vector in the span of the vectors this and this. Of course, notice you have a transpose. Okay, solution. So basically if we assume okay, span v1 comma v2, it must be lambda 1 v1 plus lambda 2 v2. In this case v1 is equal to this matrix and v2 is equal to this matrix, right, or this vector, right? And as per the question, it must be equal to this vector, right? This suppose v, right, for simplicity. Okay, so what we are going to get is that lambda 1 times 4 to 7. Notice that it is a transpose sign, so that is why I transposed it. Plus lambda 2 times 314 is equal to 100. Notice the transpose sign, it is really important. You can't miss that. Okay, you will lose marks in the exam also, and conceptually also it is not good, because you should know the definition of transpose, right? Okay, so very simple. Lambda 1 4 lambda 1 plus 3 lambda 2 2 lambda 1 plus lambda 2 7 lambda 1 plus 4 lambda 2 is equal to 100, right? Very simple. So you get 4 lambda 1 plus 3 lambda 2 is equal to 1. 2 lambda 1 plus lambda 2 is equal to 0. 7 lambda 1 plus 4 lambda 2 is equal to 0. And let's solve these two equations to get the value. What we are going to get is that well, first of all, solve this. Lambda 2 is equal to negative 2 lambda 1. You substitute it over here. Here 4 times lambda 1 plus 3 times, what is lambda 2? It is negative of 2 lambda 1. It should be equal to 1. So we have 4 lambda 1 minus 6 lambda 1 is equal to 1. So we get lambda 1 is equal to negative 1 by 2. Right, I hope it is not too much inclined. You can understand lambda 1 is equal to negative 1 by 2, which means that lambda 2 is equal to negative 2 times negative 1 by 2, which is equal to 1, right? So we get the value of lambda 2 as 1 and lambda 1 as negative 1 by 2. Is it satisfying this equation? Let's see. 7 times what is lambda 1? Lambda 1 is simply equal to negative 1 by 2 plus 4 times 1. Of course, it is not equal to 0, which means that this given vector is not a linear span, or just is not a span of, is not in the span of given vectors. Okay, this is how you check for the span. Basically it is just the checking of linear combination, nothing else. Okay, now let's move to the next concept, something called spanning set. Okay, let's see what is it. So let's see what is a spanning set. Suppose the set this v1 comma v2 till vn is said to form a spanning set of a vector space if for any v belonging to capital V, this is a vector and this is the this is the vector space, scalars alpha 1 alpha 2 till alpha n belonging to R such that V, this element or this vector, can be expressed as this sum, right? Alpha I V I. Well, we will understand it using a question, right? No need to worry. So we need to check that whether these vector form a spanning set of R3 or not. Let's see, right? It is simple. So suppose a V belongs to capital V, and of course these also belong to the vector space only. So, and over here what is V? V is basically R cube in this case, right? So we can express V as V1 alpha 1 plus V2 alpha 2 plus V3, I mean not this, sorry, some lambda 1, the constant, the scalar, multiplied by the vector, given vector, suppose x1 plus lambda 2 x2 plus lambda 3 x3, right? So what is V? We can assume the V as a general vector v1 v2 v3, right? It is the vector, of course, since it is R3, so there has to be three elements, right? So basically it is v1 v2 v3 lambda 1 times 1 0 0, this is your first vector, plus lambda 2 lambda 3 0 0 1. We solve it. v1 v2 v3 lambda 1 lambda 2 lambda 3. Solve this much at least, right? Very simple equation, right? So we get lambda 1 is equal to v1, lambda 2 is equal to v3, I mean sorry v2, and lambda 3 is equal to v3, which implies that v can be expressed as v1 times 100 plus v2 times 001 plus v3 times 001, which means that these vectors form a spanning set of R3. I hope you're understanding that how we got this, okay? And of course V was V1 V2 V3, okay? This is how you express, you just substitute the value of the lambda, okay? Very simple, right? It is very simple, right? Okay, so and there might be a condition when you don't get unique value of lambda, or you get that there exists no lambda. In that case it is not forming a spanning set, right? Of course. And there's a chance that you get unique value of lambda 1 and lambda and so on, like you got in this, or you might get free variables. In that case also spanning set is formed, but there's not uniqueness in that, like in this case, because here it is only a single solution. In that case it can be infinite, and if no lambda exists, maybe suppose lambda 2 and lambda 3, lambda 1 lambda 2 lambda 3, in that case suppose lambda 2 don't exist, even lambda 2 don't even exist, in that case there will be no spanning set. But if suppose lambda 2 is a free variable, then spanning set exists, okay? We will see it later in the basis of a vector space, just a few minutes. So what is basis of a vector space? Let's see. Well, basis of vector space, basis is a linearly independent set that span a vector space V, right? Okay, so basis should be linearly independent set that span a vector space V, and we don't understand anything what it means. I know, but it's still wait for a few minutes so that I can explain it using a question, right? So there's one more definition I need to tell, and then we will understand it using questions. So don't worry about that. Okay. So number of elements in a basis is called the I have the ink is over, so I have to refill it. The dimension is called the dimension of the vector space V, right? Okay, don't worry, we are just going to see this using a question, and let me refill my marker also. So in this case, we have to check the vector space Rn. I mean the basis for the vector space Rn. Let's see. Suppose you have E1 is equal to 1, 0, 0, 0 and so on 0 transpose. E2 is 0, 1, 0 till 0 transpose and so on till En is equal to 0, 0 till 1, and I mean the transpose. Okay. So in this case, okay, why did I assume this? Because it is very basic thing which we will understand in some time. Okay, so notice that these vectors are linearly independent. Of course, you can check they are linearly independent because okay, lambda e1 plus lambda e2 till lambda n into lambda, I mean en, it should be equal to the zero matrix, and if you solve you get the unique value of lambda 1 lambda 2 till lambda n as 0 only. That is why these are linearly independent, which means e1 comma en, they are linearly independent. So the first condition of basis is satisfied, that it should be linearly independent set, right? And this is linearly independent, right? Okay, and the second thing was checking for the span of a vector space, right? So suppose the vector can be written as Vn, right? You remember how to find the span? It is like that, lambda 1 times 1, 0, 0 till this and so on till lambda n times 0, 0 till 1, lambda n times 0, 0 and so on till 1, right? Like this. Okay, solve, you get lambda 1 is equal to Vn and so on and so forth, which means that this vector, suppose V, this whole vector can be expressed as lambda 1 e1 till lambda n en. And what is the value of lambda? It is this, right? So you get V is equal to V1 e1 till V2 I mean Vn en, which means that it is also a span also, and it is linearly independent also, which means that this set of elements is forming the basis for Rn, right? Which means that, and yeah, to find the dimension was the number of elements in the set of bases, in the basis, the number of elements for bases, right? So notice that it is E1, E2 till En, which means how many elements? N elements. The dimension is n of this vector of this basis. Okay. So let's see if we have some more questions. If we have, we will solve them, and if we don't, then we can end the lecture. Well, let's see. So we have to check the basis for vector space of all 2 cross 3 matrix, and of course it can be of any dimension, I mean of any number of rows and columns, but for simplicity I've assumed 2 cross 3. You can assume any matrix, you can assume m cross n also in a general sense, and you can solve, right? So in this case, the first uh, element we can assume is 1 0 0 0 0 0. Why we are assuming like this? Because we know that all this will be linearly independent, right? 0 e3, okay, e4, 0 0 0 1 0 0, so until, of course I did not wrote e5, you know how to write it, that 0 0 1, right? So this is your basis vector. I mean, we don't know it is basis or not, but still they are linearly independent. How? You check lambda 1 plus lambda 2 into e2 and so on and so forth. You set it equal to 0, you will find that lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6 are 0. So that is why it is linearly independent. First condition is checked. Now we have to check for the span, right? So suppose your matrix is A, B, C, D, E, F, right? So it has to be expressed as lambda 1 times E1 and so on till lambda 6 into E6. You need to solve for lambda now. 1 0 0 0 0 1 till lambda 6 into 0 0 0 0 0 1. You get the value of lambda 1 as A, lambda 2 as B, and so on till lambda 6 is equal to F. So basically you expressed this matrix in terms of A times 1 0 0 0 0 0 till F times 0 0 0 0 0 1, right? Okay, which means that this matrix, suppose if I represent it using M, is equal to AE1 till FE6, which means that E1, E2, E3, E4, E5 and E6 are the elements of the basis, and we prove that these are the basis of 2 cross 3 matrix. And what is its dimension? Dimension is simply equal to what? 6, or 2 cross 3, which gives 6, because we have 6 elements in the basis, right? Simple, very simple, right? And with this we come to an end to our lecture of linear algebra, and I hope that you understood a lot from this lecture, and maybe you enjoyed this video. Then please do like and subscribe my channel. And I'm really sorry, because of my health I might sound very much different than my other videos and not that much energetic. Still, I thought to make the video so that I can help. And if you enjoyed this video, please do like and subscribe my channel. Bye bye. Hello everyone, this is Aditya, and today we are going to cover Fourier series in a one shot. And in this, I'm going to cover every concept which is related to Fourier series. But before that, please do like and subscribe my channel. And now let's start with the lecture. So first of all, let's start with a definition of Fourier series, and let's see what is it. Okay, so it is a series expansion of a function. Well, this function is a periodic function in terms of trig functions, trig function like sine mx and cos nx, suppose, okay, is called Fourier series. So basically the expansion of function in terms of trig functions sine mx and cos mx is called a Fourier series. Okay, so it is fine, but let's see that how it comes, and what is the idea behind the Fourier series. Okay, so before that you should know what is meant by orthogonality. Well, let's see orthogonality of a function. Okay, so orthogonality of a function. So suppose not of a function because there can be many functions, right? So suppose you have f1 as one function, f2 as second function till suppose fn, right? And suppose they are defined in the interval x belongs to closed a to b, right? Okay. So now let's see what is meant by orthogonality. So for being orthogonal, two functions must satisfy this x dx. It should be equal to 0 for all I not equal to j, right? If the function satisfy this condition when I is not equal to j, then it is called that these functions are orthogonal, right? Okay. So I hope you understood what is it. For example, well, we will see right now an example, but for now you can assume it like this. Suppose if I substitute I as 1 and j as 2, right? So a to b f1 of x into f2 of x dx, it should be equal to 0 so that they are orthogonal, right? And suppose if I put I is equal to j, in that case it is suppose is equal to 1. So in this case it need not to be 0, right? It is only for I not belonging to, I mean I not equal to 0, right? Okay. So now let's see a set which will use the property of orthogonality of functions, and from that set we are going to come to the conclusion of Fourier series, that why is it important. Okay, so let's see. Okay, so suppose I define a set like this: 1 cos x. Suppose let me define it more properly. Suppose cos pi x by l, then cos 2 pi x by l, and so on till infinity. Then you have another set, I mean another element, another set of elements in the same set like this: sine pi x by l, this is x, sine 2 pi x by l, and so on till infinity. So basically it is of the form, you can say like this: cos n pi x by l, and here n can take values from 1 to infinity, like any value where n belongs to natural numbers, okay, as per the given condition. And similar is the case over here. It will be sine n pi x by l, where m, you can take n or m, whatever variable, m belongs to n. Okay, so clear. Okay, so let me erase this, it is of no use right now. So we have to check whether it is orthogonal or not. Let's see. So first of all, let's see the orthogonality with 1 and cos function. So, and of course here x is from minus pi to pi. Okay, so integral minus, or you can take from minus l to l, right? Okay, this l. Okay, minus l to l of the quantity 1 times cos pi x by l, right? And if you will evaluate it, it will be equal to 0. Suppose n pi x, let me write it clearly, cos n pi x by l, right? And if you evaluate it, you will get it as 0, right? It is very simple integral which you can evaluate. Okay, I don't think so that I need to tell that. Okay, it will be sine n pi x by l divided by n pi by l. You substitute the limit and you will get 0. Okay, just remember this property, that sine of n pi is equal to 0 for all n belonging to natural number or integers. But since here we are dealing with natural numbers, so that is why I'm saying over here natural number, but it is valid for all integers even. Okay, so it is orthogonal over here. Minus l to l, 1 into sine n pi x by l. Now the similar case with the sine function in the same set. it is also equal to 0. Okay, understood? It will be equal to 0. Why? Because if you integrate it, you get negative of cos n pi x by L divided by n pi by L. Well, n pi by L is a constant, so we don't need to worry about it. So we have cos of n pi x by L, and the limit goes from negative L to L, right? Is it fine? So if you substitute the limits, you will see that it is equal to 0. I don't need to tell this because it is very simple. Okay. Now next we have negative L to L of the quantity cos n pi x by L into cos n m pi x by L dx. If you evaluate it when n is equal to m, this is equal to, this is L when n is equal to m, and 0 when n is not equal to m. Well, we are now checking the orthogonality with respect to the cos functions, right? So we can see that if n is not equal to m, then in that case it is 0, which means that this is also orthogonal, right? Correct? Okay. Now let's check with sine n pi x by L into sine n m pi x by L dx. The similar case will happen over here. L when n is equal to m and 0 when n is not equal to m, right? Okay. So far so good, but still one case is left. We have checked with respect to one and the cos function, one and the sine function, the cos functions itself and sine function itself, but still we have to check for cos and sine together. Let's see that also. So integral negative L to L of the quantity cos n pi x by L into sine n pi, suppose m pi x by L, right? M pi x by L dx. So it will be 0 for all m comma n, right? So it tells that the functions orthogonal with respect to the cos and sine functions also. It tells that this set has functions which are orthogonal with each other, right? So I hope that it is clear now, and let me check if I made any mistake, and it is fine. Yeah, data is correct. Yeah. And of course you can evaluate these integrals. You have done this in your 12th grade and in 12th grade, not in 11th. So I hope that it is clear. It is simple. It is sine A into sine B. You have to just break it. You know it. Okay. The same condition will apply over here also. Okay. So you can try it if you want, but still it is not needed if you only working upon the data. Okay. But still for your curiosity you can check the data, that is it correct or not. Okay. So now let's see the Fourier expansion now, that why are we even studying this. Okay, calm down. I'm telling, let me raise this. Now assume let fx be a periodic function of period 2L, right? What do I mean by the period 2L? It means that if fx is the function, then f of x plus 2L will be equal to fx, right? For all x. Okay. Defined as, defined on x belong to negative L to L, right? Okay. Assume it can be written as a linear combination. It is linear combination of trig functions cos mx and sin nx, suppose. So basically we are assuming a function that is periodic and has the period of 2L, which is defined on x belonging to negative L to L, and we are assuming that that function can be written as a linear combination of cosine of mx and sine of nx. Okay, so it means that we have to write fx like this, some constant which we name as a naught by 2 in this case. Don't worry, I'm telling. Plus, since we are doing the linear combination, it means that it will go like this. n pi x by L. Okay, you remember the definition of linear combination? I hope so. It is that only. Okay, and n is equal to 1 to infinity bn sine n pi x by L, right? So this is a constant, and an and bn are also constant. These are the trig functions, trig sine and cosine, right? And this is your summation, you know it. Okay, and this is the function which is given. Okay, so we have written it like this. We assume that it can be written like this, but is it correct or not? We have to check first of all. How? Because so we have written fx like this, but how can we prove it? Well, this is our assumption first of all. So we have to make some adjustments using the constants to make this statement true. So it is only a fixed set of constants which will satisfy this value, and we are going to find that. Okay, so let's see. So let's solve for a naught first of all, right? Okay. So to solve for a naught, let's integrate both sides. Yeah, let's integrate from minus L to L of fx dx is equal to negative L to L of a naught by 2 dx, right? Plus summation n is equal to 1 to infinity, since an is a constant. We have this quantity negative L to L of cos of n pi x by L dx, right? I hope so it is understandable. Negative L to L of sine of n pi x by L dx. Now notice one thing, that we had proved that this integral and this integral are zero, right? If you remember that when we were checking the orthogonality with respect to 1 and the cos and sine functions, remember that? Okay, which means that this is equal to 0 and this is even 0. Since this is equal to 0, 0 into anything is 0, and summation is still again 0. So this whole expression is 0. Okay, so if you evaluate this integral, you will get a naught times 2L by 2 is equal to integral negative L to L fx dx, right? Correct? Okay, so you get a naught is equal to 1 upon L integral negative L to L fx dx. So this is the value of a naught which will satisfy this expression. Okay, so we founded the value of a naught, but still we have to find the value of a n and b n, right? And now for calculating the value of a n and b n, I will change the indices to k, that we have to find the value of a k in this summation, right? I hope you are not understanding right now. I will tell in few seconds. Let me erase this. So now let's solve for a n. So let's assume that we are solving for a value ak, right? Suppose a n is actually consisting of, since it is going from n is equal to 1 to infinity, so it is from a1 a2 till suppose ak, then again. Okay, so ak here, k is an arbitrary number. Okay, right? So now let's solve. Okay, so fx is equal to a naught by 2 plus the summation n goes from 1 to infinity. You can write it like this: a1 cos pi x by L plus a2 cos 2 pi x by L, and so on till ak into cos k pi x by L, right? And so on till infinity, plus this expression, this n is equal to 1 to infinity of the quantity b n sine n pi x by L, right? Okay, now what I'm going to do is that I will multiply both sides by cos k pi x by L. Don't worry why I'm doing it, but just believe me and let me do it, and then I will explain. Okay, so fx into cos of k pi x by L is equal to a naught by 2 cos k x pi by L, summation n is equal to 1 to infinity a1 cos pi x by L into cos k pi x by L, and I'm not writing the second term, you know it. Okay, plus so on till ak cos k pi x by L into cos k pi x by L and so on, plus n is equal to 1 to infinity of bn into sine of n pi x by L into cos k x pi by L, right? Fine, is it correct? Okay. So notice that now let's integrate both sides, negative L to L, right? Now I'm integrating the same step. Integral negative L to L of the quantity dx. Again, the integral over here, negative L to L, here dx, plus over here also integral negative L to L of the quantity over here, it will be dx and so on, right? I hope that it is clear, okay? And similarly integral over here, so negative L to L dx, okay? Now if you remember, this quantity again is 0, right? From the orthogonality, we have proved that this expression will be 0, 1 and cos, right? And this expression is also 0 and the remaining also are 0 except this, it will be ak into L. Why? Because we have proved that cos m pi x by L into cos n pi x by L integral from negative L to L dx is equal to L when n is equal to m. Over here they both are equal, they both are k, which means that their integral will be equal to L, so ak into L. And notice that sine into cos for any value of n or m, it is always 0. You remember? If you don't remember, you have to go back to the orthogonality and you have to check again that am I saying correct or wrong. Okay, if I am wrong then please tell me, and if I am correct then also. So if you don't remember, you can check it. So we have negative L to L of the quantity fx dx is equal to ak times L, which means that ak is equal to 1 upon L integral negative L to L fx into cos n pi, I mean it will be k pi x by L dx. Now if you want, you can change the indices or the index from k to n so that it is valid for all expressions, right? Okay, this is n, sorry. I did not use n over here for this term, because if I would have used n then you would have got confused with this, because it is the summation term actually n over here and k is a particular index over here. So that is why we calculated for a particular index, then we generalized it using n. Okay, so now it is valid for all indices. I hope so it is clear. So now let me raise this, and similarly if you solve for bn, what you have to do? Okay, you have to multiply both sides by sine k pi x by L and apply the same property over here. Sorry. So apply the same property over here, that you again open this. Notice that cos into sine will again become 0, right? And a naught by 2 into sine, 1 and sine are orthogonal, so in that case also the integral becomes 0. And here we will have negative L to L of fx sine of k pi x by L, right? Correct. And over here also everything will become 0 except this quantity sine k pi x by L into sine k x pi by L. Rest all becomes 0, just like over here. If you remember, you are multiplying over here, you are multiplying over here k sine into sine of k pi x by L. I hope so it is clear, right? Just like we did over here, the similar is the method over here also, right? You can try it. If you don't get the answer, you can comment me in the comment section and I will guide you there. Okay, so I hope so it is clear now. So let me write all the results over here properly. Let me erase this also. So if you solve for b, and you will get 1 by L into integral negative L to L fx sine n pi x by L dx, right? I told you the method: multiplied by sine, multiply by sine kx by L and then integrate it, just like you did for cos. You multiplied by cos term, here you will multiply by sine, just integrate, you will get the answer. It is very simple. So this expression is valid for these values of the constants, right? So it is not valid for any value of a naught, a n, b n. It is valid for these specific values, right? Okay. So let me see if anything else is left. Well, these are sometimes referred to as Euler's formula for Fourier series, right? To find Fourier series, right? Okay. So now let's see an example to understand this concept better. And yeah, let me raise this. So this is the question, and in this we are given to write, we are asked to write the Fourier series of fx. Okay. And we are given this, that the period is 2 pi, which means that L is equal to pi, right? Okay. Solution. So how we will do it? Well, we know fx is equal to a naught by 2 plus summation n is equal to 1 to infinity a n cos n pi x by L plus summation n is equal to 1 to infinity b n sine n pi x by L, right? This is correct? Okay. Now a naught is equal to negative L to L of the quantity fx dx. So it is negative pi to pi of fx dx. So now you have to break the limit, since it is the function is broken actually. So we have negative pi to 0 fx dx plus negative pi to 0, I mean 0 to pi fx dx. Notice that fx over here is 0, so this whole expression is 0. So we are left with this negative pi to 0 of fx dx, and it will be equal to, it is pi plus x. So you substitute pi plus x over here, you get negative pi to 0 of x plus pi, or pi plus x, pi plus x dx. You get pi x plus x square by 2. You substitute 0, it will be 0. You substitute negative pi, it will be negative pi square. It will be negative of negative pi square plus pi square by 2. So you will add, you will get pi square by 2. This is equal to pi square by 2, right? Okay. And an is equal to negative L to L fx cos n pi x by L dx. This is equal to negative pi 2 pi of the quantity fx cos n pi x by L dx. It is equal to negative pi to 0 of the quantity fx cos n pi x by L dx. And I won't write from 0 to pi, because I know that fx is 0 over here, right? Since fx is 0, so this whole expression becomes 0. So I just need to evaluate this. Okay. Okay. Negative pi to 0 pi plus x into cos n pi x by L dx. When you evaluate this, you will get, let me see, 1 upon n square pi into the quantity 1 minus negative 1 to the power n, right? Okay. Well, I've applied the integration by parts over here. Of course, we have to, since you can evaluate pi into cos pi x by L, right? And then you will get x into cos pi x by L, and that is simply the integration by parts. I hope so you know it. That is why I skipped the integral part. And now one question is that why it is negative 1 to the power n. So I need to tell that. So when you will evaluate this, you will get something like cos of n pi, right? And one thing I need to tell, it will be pi over here. So it will be also pi, and pi gets cancelled. So it will be equal to nx, right? Over here. Now let me tell one thing, that when you will evaluate this, you will get something like this, cos of n pi, right? So when n is equal to 1, let me write it like this. This negative 1 when n belongs to odd, and 1 when n belongs to even, right? Okay. So it means that I can write cos n pi as equal to negative 1 to the power n. Is it correct? when n belongs to odd it will be -1, and when n belongs to even then it will be -1 to the power 2k, which will equal to 1, which means that this is how we are getting here -1 to the power n. So if you don't understand that why it is over here, that is the reason that we were getting a cos n pi after evaluation of the limit of the integral. Okay. Sorry. And similarly we can apply the concept over here also to solve for bn, that bn will be equal to negative L to L of fx sine of n pi x by L dx. You substitute the values, and when you solve you will get over here as -1 upon n, right? Okay, so if you will solve you get -1 upon n. Okay, so now let's write this expression in terms of its Fourier series. Let's see. So fx is equal to, what was a naught? A naught was pi by 2, so we will get pi by 2. It was pi square by 2. 1 minute, I just did a mistake over there, that it was a naught is equal to 1 upon L into negative L by L, L to L, right? So it was fx dx. So I forgot to multiply by 1 by pi over there, so it will be pi square, it will be pi by 2, right? So just remember that you have to multiply by 1 by L also, right? That is why it will be pi by 2. And similar was the case over there also, it will be a 1 upon L into the integral 1 upon L fx cos, then that, and bn is also 1 upon L negative L to L fx sine, and then that. Okay, so remember to multiply by 1 by L and 1 by L. Sorry, I made a mistake over there, right? So just remember that in all expressions there is 1 upon L. Okay, I hope so it is clear now. So it will be this. Okay, like this. So when you are making the calculation, just see that you have written 1 upon L or not. Okay, I'm really sorry, I made over there a mistake. Actually 3 mistakes I guess, because I think in A and B also I did not wrote that 1 upon L. So kindly note that I will write it also at that point when it comes. Okay, so okay, so now let me write this expression. Okay, let me erase this. Plus summation n goes from 1 to infinity of the quantity. What was n when we calculated n? It was equal to 1 upon n square into pi of 1 minus -1 to the power n into cos of n pi x by L, plus the summation n is equal to 1 to infinity. What was bn? Bn was equal to -1 upon n. So -1 upon into sine of n pi x by L, right? And if you want, you can simplify it further by opening this summation and then writing 1, 2, and 3 like all the terms, and here also. So you will end up getting a series. Okay, but in summation form it will be like this. Okay, so you can try this problem also. I won't discuss it, but you can try it. Fx is equal to x minus x square. X belongs to negative, or let's say the period is x plus 2 pi to fx. So in this we have to write the Fourier series for this expression, and it is simply we have to use just the formulae, right? So apply the formula and you will get the answer. So the method is simply this only, nothing else. In fact, it is simple because here the function is not broken. So I hope so that it is clear. Now let's come to the convergence of a Fourier series. Let's see. So now we are going to see convergence of Fourier series for continuous function. So let's see. Well, I'm really sorry for this condition of paper because some glue had fallen on it. That is why it is in this condition. Kindly ignore this. Okay. So yeah, if a periodic function, of period 2L, I have, so you know the full form, it is period of 2L is continuous in negative L to L, and has continuous first and second derivative at each point in that interval, then the Fourier series, you know how to write Fourier series right now, okay? Fourier series of fx is convergent, okay? Okay. So basically, if a periodic function of period 2L is continuous, I mean it is continuous, it is not breaking at any point. In the interval negative L to L, of course, there is the value of the domain, and has continuous first and second derivative at each point in that interval, okay? So it means that f dash x and f double dash x has to be continuous at each point in this given interval, then the Fourier series of fx is said to be convergent. Well, if you want, I can give the proof also. Well, let's see proof also, but if you think it is not of your use, then you can skip that. But I would recommend to see the proof because it is really interesting to understand mathematics using proof, because then it will be just rote learning if you are just learning the statements, right, and solving the problems. It is better to understand it proof wise. But still, if you don't want, you can skip. Okay, let me erase this and then we'll come to the proof. So let's see the proof. We know a naught is equal to 1 upon L. Yeah, 1 upon L negative L to L fx dx. Now I will emphasis on 1 upon L again and again so that there's no mistake in your calculations too, because I also did that mistake. And an 1 upon L negative L to L fx cos n pi x by L dx, and Bn is equal to 1 upon L negative L to L fx sine n pi x by L dx, right? Okay. So I've written the constants value. So what's next? Let's. So An is equal to 1 upon L negative L to L fx cos n pi x by L dx. Okay. So now let's apply integration by parts. Okay, let's do it. So let's assume this as our first function, this as our second function, right? 1 upon L, okay, f dash x, and what is the integral of this quantity? It will be sine n pi x by L upon n pi by L, right? Limits goes from negative L to L. Notice that if you substitute L over here, it will be sine of n pi, which is equal to 0. And substitute negative L, it will be sine of negative of n pi, which again will be 0, right? For any value of n, which is an integer. Which means that this expression is 0, okay? Minus the quantity negative L to L f dash x sine n pi x by L dx, right? And n pi by L, so we get over here L by n pi, right? Correct. So L and L gets cancelled. So we have an is equal to 1 upon negative n pi integral negative L to L f dash x sine n pi x by L dx, right? Now again set it as your first function, this as your second function. You just apply the formula of integration of parts. You get f double dash x into the quantity cos of n pi x by L upon n pi by L, and of course a negative will be there over here from negative L to L, right? Now one thing to be noticed, that since fx is a periodic function, which means that f of x plus 2L is equal to fx, correct? Is it fine? Okay. So f dash of x plus 2L will be equal to f dash of x, since We have assumed that this function is continuous and periodic, right? And we are assuming now, that is why in the statement was if f dash x and f double dash x are continuous too, which means that since we assumed this as continuous and periodic, so this has to be also continuous. Why? Because we assumed it. So which means that if you substitute x as L as negative L, you get f dash of L is equal to f dash of negative L, right? Correct. So now when you substitute the limit over here, what you will get, sorry, it will be f single dash x. Sorry, since it was simply that term, okay, there, no derivative involved. Sorry, here also no derivative involved. I'm really sorry. Right, I made some minor mistakes over here which you should not make, like me. Okay, so yeah, it's correct. So so is it fine? Okay, so when you substitute over here, you get f dash of L. Well, don't worry about negative sign, we will see it. Cos of, and don't worry about this constant 2, cos of n pi minus f dash of negative L, cos of negative n pi, which is again n pi, since cos is an even function, f of negative x is equal to fx, right? Okay, so cos of n pi, right? So notice that cos of n pi into f dash L minus f dash negative L, since we assume that fx is continuous and periodic, and we assume that it would imply that over here, that since f dash of x plus L is equal to f dash x, since we assume that f dash x is also continuous, which means that this expression is 0 since they both are equal, right? Which means that this limit is again 0, right? Fine, correct. Okay, now again we have this expression negative L to L. Now the derivative of the second, I mean the first function, what is the integral of the first? Again it is cos n pi x by L divided by the quantity n pi by L. Negative negative becomes plus, right? Okay, so let me erase this and then we will see further. Okay, so we have this value of an, right? Okay, now we can further simplify it a bit and we get negative L by n square pi square negative L to L of fx cos of n pi x by L, right, dx. Now f double dash x, sorry. Now since we know that fx is continuous and periodic, which means that, and we assume that f dash x and f double dash x are continuous too, which means that since f dash x has a maximum value, so it means that f double dash x will also have some maximum value, right? Suppose f double dash x is less than some quantity m, and of course we have to take the mod over here, right? So which means that let's don't yeah, we take the mod. So let's take mod both sides. What we get? An L by n square pi square, it will all become positive now. Negative L to L f dash x cos n pi x by L dx. Bring the mod inside, and you know the property that this is this quantity, right? If you remember this property, right? Okay. So mod of n is equal to L by, is less than equal to n square pi square of the quantity into the negative L to L of f dash x into cos. What is the mod of cos? It will be equal to 1. The max value of cos is 1, right? And what is the maximum value of this function? It will be m. So m dx, right? So we have mod an is equal to the quantity m into 2l, so 2ml square by n square pi square, right? I hope so that it is clear. Okay, so now similarly, if you apply for bn also, when you apply for bn, you use the same methods and integration by parts and all. So when you evaluate it, it will be less than equal to again 2ml square by n square pi square, right? The same result which we got over here, right? Okay, so what's use of these two? Well, don't worry, we are going to see. So we have fx is equal to a naught plus summation n is equal to 1 to infinity a n cos n pi x by l plus summation n is equal to 1 to infinity of b n cos n pi sin n pi x by l, right? Okay, now just take this expression and a naught plus summation n is equal to 1 to infinity, or just why we need to write again and again. Take both sides magnitude and it will be less than equal to a naught by 2 plus summation n is equal to 1 to infinity mod an. Why mod an? Because we know that mod of cos is 1. Okay, plus summation n is equal to 1 to infinity 1 mod bn, right? Again, okay, fine, correct. Okay, so mod a naught by 2 plus summation n is equal to 1 to infinity. Since they both are equal, so we can write 2 over here, right? Since mod an and bn were 2ml square by n square pi square, right? Okay, so we are left with mod a naught square plus 4ml square by pi square into the summation n is equal to 1 to infinity of 1 upon n square. What is it? It is equal to pi square by 6, right? Okay, Euler's formula, Euler series, whatever you want to say. This and this gets cancelled, is 2 by 3. So we are left with mod a naught by 2 plus 2ml square by 3, which means that this sum will be less than this expression where m is finite, l is finite, a naught is finite, which means that this expression is converging, right? To some value less than this. It means it is converging. Okay, let me erase this. Now let's see a piecewise continuous function. Well, what is a piecewise continuous function? Well, a function which is continuous in a broken intervals. What do I mean is that? Let me write some points. A function fx is said to be piecewise continuous in negative L to L if, first point, fx is defined and continuous in continuous uh, for all x belonging to negative L to L except a few except at except at some, let me write it like this, at some finite number of points. Okay, so suppose that in the interval a to b there is a x naught, there are 3 points c, d and e where the function is broken, is discontinuous. So if the function is continuous in a to c union c to d union e to b, if the function is continuous in this interval, then it is said to be a piecewise continuous except the discontinuities at c, d and e, right? Okay, correct. Okay, so I hope so that I have written it well. Of course, if I need to write it, it shouldn't be like this. C to D, and then D to is E is left, D to E, then union E to B, right? Like this. Well, it was just an idea to tell that if there are three discontinuities in this interval at some point C, D, and E, so we will have to check that if in these intervals the function is continuous, then function is said to be a piecewise continuous function. Okay, let me erase this for now and move on to the next point. Okay, what is it? Let's see. Second point, at a point x not belonging to negative L by L, sorry, if function is not continuous, then I mean at x naught, if the function is not continuous, then limit as x naught fx and limit as x belongs to x naught, I mean x approaches x naught plus fx exist and are finite. Okay, basically if x naught is a point where the function is not continuous, then there should be the left hand and right hand limit, they should exist and should be finite, right? Okay. Sorry, at the point of interval limit x tends to negative L from this quantity fx and endpoint, and limit x tends to fx exist and are finite. Basically at the end point, right? I was thinking at why point I've written. Yeah. So at the point of interval, this I mean this is the right hand limit of the negative L, and this is the right hand, and this is the left hand limit of the upper limit, and this is the right hand limit of the lower limit, right? Of course, that after that only function is defined, and before that the function is defined, not after that and before that. Okay, that is why. So basically, these are some of the points related to piecewise continuity of a function, and now let's see convergence of a piecewise continuous function. Let's see what is it. So we are going to see convergence of piecewise continuous function. Sometimes it is referred to as Dirichlet conditions too, right? Conditions 2. Suppose a function fx can be expressed in Fourier series if provided the function should satisfy such properties if it is a piecewise continuous function. The first one, fx is periodic 2L in negative L to L, right? And is single valued, right? Means it don't take multiple values for a single input valued function, and it's finite, right? Of course it should be finite, as how will, yeah. Second, fx it should be piecewise continuous in negative L to L. Of course it should be. Third, fx has LHD and RHD at each point in interval, right? Okay, in interval, right? Okay, now there is a theorem. It is clear that the function should be periodic, it should be single valued function, and finite, it should be piecewise continuous. and it should have LHD and RHD at each point in the interval, right? Okay, you know what is left hand derivative and right hand derivative, right? Simple it is. Okay, so it is a theorem related to the Dirichlet conditions only. That suppose I'm not writing a statement or anything like that, you need to just understand. Suppose if function is continuous at x is equal to x naught, then the value of fx naught, then f at x naught, x is equal to x naught is equal to f at x naught. But if function is discontinuous at x is equal to x naught, then f at x as x is equal to x naught will be given by f at x naught negative, I mean the LHS, I mean not the LHS, it is the LHL value of the left hand limit plus the right hand limit at x naught, right? Okay, else it will be this. Of course this is general because if they both are continuous, and I mean if the function is continuous at x is equal to x naught, so in that case they both are equal, right? So it means that it will be equal to fx naught, so it is better to write like this only. Okay, so let's see this with the help of an example, right? I hope that this much is clear, right? Okay, let's see with the example. So the question states that we have to find the Fourier series of fx is equal to negative pi from negative pi x and then 0 and x 0 x and pi, right? Okay, so we are given this sorry, and now from this we have to deduce 1 upon 2 square plus 1 upon 3 square and so on is equal to pi square by 8. Well, okay, so of course you can solve for the Fourier series on your own because you know how to deduce it. You know that you will take the limit as 1 upon L. Yeah, of course you are given over here functions from negative pi to pi, right? Okay, correct. Yeah, one thing I need to tell over here, well I will tell in the later part of the video. Okay, 1 upon L into the quantity negative L to L fx dx, and simply apply for an and bn, and you will get certain result that a naught is equal to negative pi by 2 and an is equal to 1 upon n square pi negative 1 negative 1 over here, and bn is equal to 1 upon n into 1 minus 2 into negative 1 to the power n, right? Correct. Sorry, correct. So we have fx is equal to a naught by 2, so negative pi by 2 into 1 by 2, so we have negative pi by 4 plus summation n goes from 1 to infinity of the quantity 1 upon n square pi negative 1 to the power n minus 1 plus the quantity n is equal to 1 to infinity of the quantity 1 upon n into 1 minus 2 into negative 1 to the power 2 into the sine function into the this over here cos function. So this is how you will get the Fourier series. And since we need to find this expression, which means we need the square term, so notice that this don't have any square term, so we have to remove this term over here. So how will it be removed? When x is equal to 0. Why? Because sine of 0 is equal to 0, right? Okay, if you needed to eliminate cos, then you would substitute pi by 2, right? Or negative pi by 2. But over here you will substitute pi, I mean 0 over here, right? So we have f at 0 is equal to negative pi by 4 of the quantity n is equal to 1 to infinity. This will be 0 because sine of 0 is equal to 0, so whole expression will become 0, right? Correct. So n is equal to 1 to infinity of the quantity negative, not negative, n square pi negative 1 to the power of this into cos of n pi x by L. L is equal to pi, so pi and pi gets cancelled. You are left with nx, right? Nx, right? Okay. And since x is equal to 0, you get over here 0, and cos of 0 is equal to 1, right? So we are left with this expression. Okay. Sorry. Negative pi by 4 plus 1 upon pi into the quantity. Let's open this now. You get when you substitute 1, you get negative 2 by 1 square, negative 2 by 1 square plus 0. Since when n is equal to 2, it will become 1 minus 1, which is equal to 0. When you substitute n is equal to 3, you get negative 2 by 3 square, and so on till infinity. What is f at 0? Well, f at 0, over here it is 0, and over here it is equal to negative pi, which means that the LHL and RHL value are not equal. So we have to write f at 0 as f at 0 negative plus f at 0 positive, which is equal to negative pi by 2, right? Correct? Okay. So we are left with negative pi by 2 is equal to negative pi by 4 plus 1 upon pi. 1 upon pi, negative 2 is taken as common, into the required sum. This is the required sum. And if you solve it, will become negative pi by 4, and you bring it, it will be pi square by 8, right? Hence proof. So Fourier series is also used to find the series. I mean, such kind of series. It is very easy to prove it using Fourier series, right? So this is one of the biggest application also of the Fourier series. And now let's see what's next. Now let's see even and odd functions. What are these? Okay, let's see. So even and odd functions. Odd and even functions. I think you might know about it, and if you don't know, let me tell. If you have a function fx, then if f of negative x is equal to f of x for all value of x belonging to the domain, and f of negative x is equal to f of negative x for all value of x belonging to the domain, then in this case we call this kind of function as odd function, and we call such kind of function as an even function. So in the case of an even function, negative L to L fx, let me write it over there only so there is no confusion. So negative L to L fx dx, it becomes negative 2 times 0 to L fx dx, and over here if you have negative L to L fx dx, it becomes equal to 0, right? So this is the application of ordinary function in terms of integrals. So we will use this idea to solve for Fourier series in the cases of even or odd function. So suppose if fx is an even function, right, is an even function, then a naught will be negative L to L fx dx, it will be 2 times 0 to L fx dx, correct? An will be negative L to L of fx cos n pi x by L dx. Now notice one thing, that even into even is an even function, even into odd is an odd function, and odd into odd is an even function, right? Why? Because if you substitute negative x, so in this case it is negative into negative, which will become positive, which means that it will become an even. Here also it will become positive into positive and even. Here positive negative, it will become odd function, right? So notice that here this is also even, this is also even, so it means that this whole is an even function. So it is this quantity, right? Fx into cos n pi x dx. Okay, bn is negative L to L fx sin n pi x by L dx. Notice fx is an even function, sin is an odd function, right? So it means that their product will be odd function, and odd function integral from negative L to L is equal to 0, right? So remember, when you have an even function, sorry, so when you have an even function, then in that case you only need to evaluate a naught and an, because you will know that bn is already 0, right? So you don't need to evaluate for this function, for this bn, right, in the case of an even function. And in the case of odd function, a naught is equal to negative L to L fx dx, since fx is odd fx, since fx is odd, it means that this will become 0. And again, an is equal to negative L to L fx into cos of something to dx. So this is odd, this is even, odd into even is odd. So it means this limit, so it becomes 0. Bn is equal to negative L to L. Of course, 1 by L, sorry, 1 by L, 1 by L, 1 by L. So it will be 1, it will be 2 by L, 2 by L, 2 by L, right? 2 by L, right? I'm really sorry, I am making so a small mistake over here. So 1 upon L, right, over here also, and 1 upon L over here also, right? Fx sine of the angle dx. Notice that this is odd, so odd into odd is even. So it becomes 2 by L of negative of 0 to L fx sine n pi x by L dx, right? Which means that you need to only evaluate bn in case of fx being odd function, right? So there's nothing else which is required to be told in this, because when you solve numerical, you will apply the same concept as you applied over there before. But now if you see odd function, you can directly say that a naught and n is equal to 0. You will only solve for bn, right? It will save steps. Else if you apply the original method also, it is same, right? So if you want, if you see an odd function, you can directly say a naught and an is equal to 0. So you will only solve for bn. And if you see an even function, you will solve for a naught and bn, and you will say bn is equal to 0. And if you don't want to remember odd and even function anything, you just solve for a naught, an, and bn, right? Just like you were doing before. Okay. So now let's see what is Fourier half range series. Let's see what is it. So suppose Fourier series expansion of a function fx in an interval, in an interval 0 to L, where L is half of the period, right? Period, because the period is 2L, so L is 2L by 2, that is half of that period, right? Then it's possible, it's possible to extend fx, function fx, in other half, negative L to 0 of negative L to L, like this you can also write, so that function is either odd or even. Wait, now before saying anything after it, let me explain what is it, right? Because I know it is going like a bounce, so let me explain it. Okay, so suppose this is the function, right? Suppose this is like this, okay, 0 to L, right? You can assume it like this. Suppose this is a very simple example which generally given in every textbook. If you see, or if you follow any teacher, it will be, any professor, it will be the most basic example that anyone will give. Okay, so suppose this is the function from 0 to L which you are given, so you can extend it back like this also. It should be symmetric actually. Yeah, so this was original. Now you extended, this is extended even function. How? You check for any value of x, they both are equal. It means f at negative x is equal to fx, and since it is symmetric about the x-axis, sorry, about the y-axis, right? So it means that it is an it is an even function, right? So it is an extended even function, and in this case This is extended odd function 0 to negative L, right? Since it is reflected about the origin, right? Okay. So what is the use of this? Well, let me explain it. If I say in general, you won't find much use, right? But when you solve problems, it might be used somewhere or somewhere not. It will be explained in the question properly. But in general sense, it don't have much application like that as an individual, right? But let me explain it through a question also. But before that, let me see that if I need to tell anything. Yeah. Suppose if you are extending it as an even function, so if you write the Fourier series, it will be a naught is equal to 0. Sorry, a naught is equal to 2 by L negative L to I mean 0 to L fx dx, and a n is equal to 2 by L 0 to L fx cos of n pi x by L dx, and you will set bn is equal to 0, right? So when you are asked that to write the extended Fourier series for even function, it will be this. I mean the constants will be this, right? And when you are asked for this, a naught is equal to an is equal to 0 and bn is equal to 2 by L 0 to L fx sine n pi x by L dx. Just like in the case of even and odd function, there's nothing new in it, okay? So that is why I said that if you know even and odd function, you can do it very easy. So if I give you a problem, it is similar to the problems you just did before, or you can apply even or odd function also, right? That is the key. Let's see with respect to a question also. Okay. Okay, before coming to an example, let me tell you one thing. Suppose fx is given like x, and for negative pi to 0, and suppose it is 0 for like this, okay, fine. So if you are asked to write the Fourier series of it, you know how to write it. But what exactly does this statement tell? Fx plus 2 pi is equal to fx. Let me explain it graphically. Suppose this is your x-axis, this is your origin, so this is origin, and when x is negative pi, then y is also negative pi. I mean it will be somewhere over here, right? Okay. So it goes like this, okay, and then from 0 to pi it is constant, right? Till here this is negative pi and this is pi. So what will happen is that this graph will keep on repeating itself, right? This is meant by a periodic function. I hope so now you understood that what I was saying, right? That this graph will keep on oscillating like this. This is 3 pi and so on and so forth, this negative 3 pi, right? Like this. Sorry, not over here, over here. Okay, like this actually. So now I hope that you understood what is meant by fx plus 2 pi is equal to fx for a given function, right? Simple, right? Let me raise this and now we will see a problem. So question: obtain cosine and sine series for fx, Fourier series basically, Fourier series fx is equal to x in 0 to pi, I mean 0 to pi, right? So what do I mean by cosine function? Well, it is just even function, right? So we have to express it in terms of even and odd function, right? First even and then first odd. I mean first even then odd, okay? Fourier series. So it means that we first need to solve with respect to the even extension, then odd extension. This is how it will be asked, okay? So a naught will be equal to the integral 2 by pi 0 to pi x dx, right? Correct. So it is pi square by 2, pi square by 2, so it turns out to be pi, right? Correct. Am I correct? Yeah. So an is equal to 2 upon pi integral 0 to pi, and then this x cos n pi x by l dx. I won't solve this. What we'll get? We'll get 2 by pi 1 by n square negative 1 n minus 1 this. So you get fx as pi by 2 minus 2 by my 2 by pi. Let me see if I made any mistake or something like that. No, plus, sorry, of the quantity summation n is equal to 1 to infinity of 1 by n square negative 1 to the power n minus 1 into cos of, since x is since l is equal to pi, so we have cos of nx, right? Like this. Okay, so this is the even Fourier series for this, even or the even extension. Okay, this is the Fourier series for the even function or the cosine function. And similarly for the odd function bn is equal to integral 0 to pi 2 by pi of the quantity x yx, because fx is equal to x, right? Okay, of sine n pi x by l, and it is equal to, what is it equal to? I have to see, it is equal to 2 into 1 negative 1 to the power n plus 1 by n simply. So you get it as fx summation n is equal to 1 to infinity of the quantity 2 is common, so you get negative 1 to the power n plus 1 by n into sine of nx, right? Simple, right? So this is the odd extension. Fourier series for the odd extension, right? So I have that. Now you understood that what is the meant of half angle, right? Not half angle, it is the half range. Sorry, half angle. I was saying for trigonometry. Sorry. So this is for a half range. Okay. So now let's see what is Parseval's identity, and then we will see the complex form of the Fourier series, and then we will end the lecture, right? I hope that till now everything is clear. If it is clear, then please do like, subscribe my channel, and please support this video. Okay, so now let's start with the Parseval's identity, right? So let's see Parseval's identity. What is it? Well, it basically states negative L to L of the quantity fx whole square dx is equal to L times 1 by 2 a naught square plus summation n is equal to 1 to infinity a n square plus b n square, right? This is the Parseval's identity. Well, of course, now you might be thinking that how it has come, so I'm going to give the proof. Okay, let's see the proof. Okay, so fx is equal to a naught by 2 plus summation n is equal to 1 to infinity of a n cos n pi x by l plus summation n is equal to 1 to infinity bn sine n pi x by l, right? You are given this, and now what you are going to do is you will multiply both sides by fx, right? A naught by 2 into fx plus summation n is equal to 1 to infinity an into fx cos this n is equal to 1 to infinity bn times b times fx sine n pi x by l, right? Okay, now what I'm going to do is I will integrate it dx. Okay, minus L to L dx minus L to L dx minus L to L dx. Now notice that well, a naught by 2 is a constant, so I can bring it out. So notice that let me write it over here. A naught was equal to 1 upon L negative L to L fx dx. Same thing is written over here. Let me write it like this, then it will be more clear. A naught by 2 integral negative L to L, right? Same thing is over here, just we have to bring L over here. So it is L A naught. So negative L to L of fx whole square dx is equal to L times a naught into a naught by 2. It is L a naught square by 2 plus. Notice that an was equal to 1 upon L negative L to L of fx cos of n pi x by L dx. Bring it over here. So it is equal to L times an, right? Correct. So it is n is equal to 1 to infinity of L times an into an whole square. Similarly, you can solve over here also. It is same. It will be equal to 1 to infinity L b n whole square, right? Correct. You now bring L outside, you get negative L to L fx whole square dx is equal to L times a naught by 2 plus this quantity an square plus bn square, right? Okay. So hence you got this identity, right? And if functions even or odd, it don't matter. This is a general expression. You can make some adjustments to solve, else you don't need it also, right? You just apply this formula and solve. Okay. So there's no adjustment actually. You just need to just apply the properties, nothing else. So I'm not going to that. If you want, you can prove it on your own also. Else you don't need. Just you need to remember this formula if you want. Okay. Let's see an example. Yeah, and there's one more thing. RMS value of a function in a to b, right? Okay. So f rms is equal to integral a to b fx whole square dx upon b minus a, right? This is how you evaluate the RMS value, and of course you must have studied it in physics and some other subject, but since it involves fx whole square integral, so that is why I told it. Okay. Okay, so now let's see an example. Okay, here is this. Okay, question: apply Parseval's theorem. I'm not writing the full form to the function fx is equal to x negative pi to this and this. Okay, and this. Okay, f of x plus 2 pi is equal to fx, right? Okay. Now notice that when you solve for a naught, what you get? A naught is equal to integral negative L to negative pi to pi of fx x dx. It will be equal to 0, right? Correct. And an is equal to negative pi to pi and x cos n pi x by L dx. It will be also equal to 0. Why I am saying like this? Because x is an odd function. That is why. Don't worry that how am I calculating like this. And bn is equal to negative pi to pi. Now this we have to calculate. X sine n pi x by L dx. It is equal to what? Let me see. It is equal to 2 times, well, we have calculated this actually, I think, n, right? N plus 1. Okay. So this is what we need to do. What we need to do in this is that we have to prove to deduce sum 1 upon n square is equal to pi square by 6. Okay. This is the Euler series if you remember. Okay. So fx. So now we are going to apply the Parseval's identity. Now we know that negative L to L of fx dx whole square is equal to L times the summation n goes from 1 to infinity of b n square, right? So over here substitute L as pi, fx at x, this is pi, b n you know the value. Integral of x square is x cube by 3 and you integrate it from negative pi to pi, you get 2 pi by 2 pi cube by 3 pi times this summation n is equal to 1 to infinity of the quantity 2 negative 1 to the power n plus 1 by n whole square, and you solve it. What you will get is that uh, what you will get is that is it pi times, yeah, 2 pi square by 3 is equal to 4 times, since square of a negative number is now positive always, n equal to 1 to infinity of 1 by n square, you bring it over here, so it will become pi square by 6. Correct? So this is how you deduce this, okay, using the Parseval's identity. If you would have used the cos formula and all in that, you would have to use lots of adjustments. In this it is clear, right? So I hope that you understood what is Parseval's theorem. And now we are coming to the last part of this lecture, that is the complex form of the Fourier series, right? Let's see it. Now let's see the complex form of Fourier series, and it is used to make our problems simple. The name suggests it is complex, but actually it is used to make our problems simple. So let's see it, okay? So the original series looks like this. An sine cos n pi x by L plus summation n is equal to 1 to infinity bn sine n pi x by L, right? Okay. Now, if you need to convert it to complex form, you know e to the power I theta is cos theta plus I sine theta, right? E to the power negative I theta is equal to cos theta minus I sine theta, correct? Simple. Add and solve, you will get cos theta e to the power I theta plus e to the power I theta by 2. Sin theta is e to the power I theta minus e to the power negative I theta by 2i, right? Okay. Now just substitute it over here, the cos and the sine values. What you're going to get is that fx a naught by 2 plus summation n is equal to 1 to infinity. Well, you can take summation as common since they both have the same indices, right? Okay. So an times e to the power I theta plus e to the power negative I theta by 2 plus bn e to the power I theta minus e to the negative I theta by 2i. Here theta is equal to n pi x by L. Okay, so don't worry. Okay, I'm just going to substitute it back in 1 or 2 steps, but for now I was just doing like this. Notice that you have e to the power theta over here and over here also, and negative over here. So let's club them together. So you have fx is equal to a naught by 2 plus summation n is equal to 1 to infinity of the quantity an plus bn, right? This by 2i, this by 2, e to the power I into n pi x by L, right? Plus an by 2 minus bn by 2i of the quantity e to the power negative I n pi x by L. I hope that it is clear how I made this step, right? Okay. So let's write one more step over here. So a naught by 2 plus summation n goes from 1 to infinity of the quantity an plus this becomes minus I times I, it will become negative ibn by quantity 2i into e to the power I n pi x by L plus an plus ibn by 2i e to the power negative I n pi x L by n pi x by L, right? Like this. Now let me erase this and then we are going to solve further, okay? Yeah, and notice one thing, that there was no I over here because I take the conjugate and I brought that I to the numerator, so there is no I in the denominator, okay? Now let's name a naught by 2 as c naught and an minus ibn as by 2 as cn and an plus ibn by 2 as c minus n. For now just name it as negative n. I will tell why we are naming it like this in just few steps, right? So basically it is equal to c naught plus summation n is equal to 1 to infinity And notice one thing, that c of negative n is equal to the conjugate of this, right? Since I, if fx is real, right? Okay, the function is real, okay, n is equal to this cn e to the power I n pi x by l plus c negative n e to the power negative I n pi x by l, right? Okay, so now notice one thing, that if you bring the summation inside, you get c naught plus sum as n goes from 1 to infinity c n e to the power I n pi x by l plus summation n goes from 1 to infinity c of negative n e to the power negative I n pi x by l, right? Now notice one thing, if you substitute negative 1 as t, or you replace negative n with n, what you will get over here in this expression? Let's see, negative to c negative n e to the power negative I n pi x by l, you replace negative n with n, you get n goes from negative infinity to negative 1 of c n e to the power I n e to the power I n pi x by l, right? Which means that this term is from n is equal to 1 to infinity, and this one n is equal to negative infinity to negative 1. So it covers all the terms from negative infinity to negative 1, and it covers all the terms from 1 to infinity, and this covers at n is equal to 0. Which means if you combine all these three, you will end up getting fx as equal to the summation n goes from negative infinity to infinity of cn e to the power I n pi x by l, and this is the complex form, right? I'm sorry. And okay, I hope that you understood this. Now the question is that what is cn? Let's see what is it. Okay, let me raise this, then we will see further. Okay, okay. Now notice that cn is equal to a n minus I b n by 2, correct? Okay, how do you evaluate an? As 1 upon L into the integral negative L to L of fx cos n pi x by L, correct? Minus I times fx I by L, right? Okay. Fx sine n pi x by L dx, correct? Now you can take fx common, and what you will get is, of course, L is a constant, so this will come like this, and minus L to L fx times cos n pi x by L minus I sine n pi x by L dx, right? You got this? Okay. Now this will be equal to e to the power negative. So it will be equal to e to the power negative I n pi x by L. Am I correct or not? Am I? Right. It is actually. We evaluated it earlier. 2L integral negative L to L fx, right? Fx e to the negative I n pi x by L is equal to Cn, right? Correct? Okay. So this is the value of Cn, and notice if you substitute, wait, let's solve for C for negative, C of negative, and also it is equal to a, and I mean it will, when you will solve it, it will come like this, 1 upon 2L times integral negative L to L fx e to the power I n pi x by L dx, C of negative n. Just apply the same property over here. Instead of negative sign over here, you will get a positive sign, so it will become e to the power plus I n pi x by L, right? So notice that you can create C of negative n using C of n if you replace n with negative n, right? Correct? And if you replace n as 0, you get C naught, which means that this is a general expression where Cn is equal to 1 upon 2L integral negative L to L fx e to the power negative I n pi x by L dx, right? Correct? Okay. So now let's see a question on it, and then we will end this lecture. Okay. So fx is equal to e to the power negative x, and x belongs to negative pi to pi, right? Okay. So let's solve for first of all Cn. Cn is equal to 1 upon 2 pi, here L is equal to pi, negative pi to pi, e to the power negative x into e to the power negative I nx n n pi x by pi dx. And if you evaluate this integral, it will be, wait, negative pi to pi into pi and pi gets cancelled, right? So let's solve for En. What you will get is that, let me write directly the answer. So you get the value of Cn as e to the power pi minus e to the power negative pi by 2 pi into negative 1 to the power n to negative 1 minus in by 1 plus n square. And it is really simple, since it is very simple actually. If you evaluate, you will understand, right? It is simply equal to like that. Okay, you substitute the limit, and when you will solve for the limits and all, remember e to the power I n pi you will get somewhere. So e to the power I n pi is equal to sine of n pi plus e to the power sine nx n pi. Sine of n pi is equal to 0, and cos of n pi is equal to negative 1 to the power n, right? Okay, so you have to remember these things. That is why you got a negative 1 to the power n. Okay? So that is the thing which you need to remember while making calculations. And now let's see fx is equal to summation n is equal to negative infinity to infinity of the quantity negative 1 minus I n 1 plus n square negative 1 to the power n e to the power pi minus e to the power negative pi by 2 pi into e to the power I n x, right? So this is your Fourier series in terms of complex form basically. So I hope that you enjoyed this lecture, and if you did, then please do like, subscribe my channel. And I hope so that I've covered everything in this lecture, and if there's anything left, please tell me in the comment section. I will try to add in it or make a separate video on it. And please do like, subscribe my channel, and please support this video, and please support my channel. And now let's end the video, but it really takes lots of effort to make this kind of video, so please do support this video and channel. Please support my channel, and please subscribe my channel.
Hello everyone, this is Aditya, and today we're going to do Laplace transformations. But before that, please do like, subscribe my channel, and please support this video. Now let's start with the lecture. So before starting with the Laplace transformation, we need to know that why we use it. So basically it is used to solve linear or non-linear ordinary differential equations or partial differential equations, or maybe some integral equations or simultaneous differential equations, and many more things. So we will see them in the later part of the video, but now let's start. So let's see what is meant by Laplace transformations. Okay, so now let's see. So Laplace transformation of a function, suppose f of t is given as the integral 0 to infinity of e to the power negative pt f of t dt. Of course p is a constant with respect to t, right? Okay, so this is basically the definition of the Laplace transformation which you need to remember, right? Okay, so now there's something called inverse of Laplace transformation, right? Okay, inverse of Laplace transformation. Okay, so basically it is if, let me write it, if Laplace transformation of this is some capital Fp, right? Notice that this will be equal to f of p. Since after integrating and substituting the limits, t will vanish, so we will be left with a function of p, right? Okay, So it implies that f of t is equal to Laplace inverse of f of p, right? So it is very easy to compute f of p if you are given f of t, right? But it is really difficult to compute f of t when you are given capital F of p, right? And we will see it using some problems that to compute f of t you need to know the inverse functions, right? I will tell, don't worry about it, okay? But I hope so that till now everything is clear, right? Okay. Let's see a simple property of Laplace transformation before we move on to the main properties, because that property will be used again and again, so I need to tell it right now, okay? So linearity property of Laplace transforms. Okay, let's see. Suppose you have the Laplace transform of this quantity a of ft plus b of suppose gt, right? Okay, where a and b are constants. And yeah, notice one thing, that over here p can be real or complex both, right? Okay, so notice that this will be equal to Laplace of a times Laplace of f of t plus b times the Laplace of g of t, right? Okay, just simply you distributed it, okay, simply like that. Now suppose if you have suppose n terms, suppose you have a1 over here, a1 f1, where a1 is constant, f1 is function, till an fn. So it is nothing but it is equal to a1 times the Laplace of f1 plus a2 times the Laplace of f2, so on till, I need to complete over here only, till an Laplace of fn, right? Okay, so I hope so that linearity property of Laplace transforms is clear, right? So having said all this, let's move to some problems also, but before that we need to check one more thing, right? And yeah, if you want the proof of this, well, I can prove also. So proof Laplace of a f of t plus b g of t, it can be written as the integral 0 to infinity of, let me change its width, yeah, e to the power negative pt into this, right? So you will get af of t dt plus 0 to infinity negative pt b g of t dt, correct? Okay, so you simply get a over here 0 to infinity e to the power negative pt f of t dt plus b integral 0 to infinity e to the power negative pt g of t dt, correct? Okay, so it is equal to a times the Laplace of f of t plus b times the Laplace of this is Laplace, not lambda, of gt, correct? Okay, hence proved, hence whatever you want to write, okay? So similar property stands for inverse also, that Laplace inverse of a f of p plus b g, suppose capital G of p is equal to the a times the Laplace inverse of f of p plus b times the Laplace inverse of the quantity g of p. I have to check one thing, Yeah, over here I wrote Laplace inverse or not. I need to check that. Wait a minute. Yeah, I have written. Okay, I needed to check this only. Okay, so now let's see some questions to understand it better. So Laplace transforms of some functions. Okay, so let's see the first one. Suppose Laplace of 1, what is it? Well, you just simply substitute it over here, but before that remember one thing, the basic formula that you should remember, that Laplace of a function is equal to 0 to infinity e to the power negative pt f of t dt, correct? Okay, now let's see the questions. First one, suppose Laplace of 1, what is it? Well, you substitute it, negative pt 1 dt, correct? So it is 0 to infinity e to the power negative pt dt, correct? Right? And of course it is very simple integral, right? I hope so that you know it. Even if you don't, let me write it. Correct, you substitute the limits, you will get 1 upon p. Okay, so Laplace of 1 is equal to 1 upon p, correct? Okay, so you have to remember this. And what is the most important thing over here, that you have to remember that Laplace inverse of 1 upon p is equal to 1. This is really important. You can derive it, but this is very difficult to derive, so you have to remember it. Okay, that the inverse of this is equal to that. Okay, it is really important, this thing. Okay, so now let's see second one, what it states. It states that we have to find the Laplace transformation of, or transform of e to the power at, right? Okay, so this is equal to 0 to infinity e to the power negative pt e at dt, correct? Is it correct? Okay, it is equal to 0 to infinity e to the power negative of p minus a dt, correct? And yeah, one more thing, that of course p has to be greater than equal to 0, right? Since if it is less than 0, then it will become e to the power capital pt, and then this function will diverge in most of the scenarios. Okay, so when you solve it, you will get e to the power negative p minus a by negative p minus a, limit 0 to infinity. And when you solve, well, it is easy to solve also. If you want, I can do, but it is simple. It is equal to 1 upon p minus a, of course, when, what is the condition, that p is greater than a, because then only p minus a, this p minus a will be greater than 0, right? Greater than equal to 0, so you can take equal to also, no problem. Okay, so then only this function will be defined. Well, of course it can't be equal to also, because if it will be equal to, then this quantity will become 1 and then it will diverge. Okay, so you can't have equal to. Okay, so if p minus a is greater than 0, then this expression will be e to the power some negative quantity, which means that it will converge. Okay, understood? Okay, so you have to remember that Laplace of e to the power at is equal to 1 upon p minus a, right? But what is more important is that the Laplace inverse of 1 minus p minus a is e to the power at, right? Okay, this is more important, right? Because you can derive this one, but you can't derive this one. Okay, this is just the inverse. So let's see a problem, then you will understand it more. So find Laplace transformation of this function if f of t is given as t for 0, this 1, this, and 0 for t greater than 2, right? Okay, so let's find. Okay, so Laplace transformation of ft is equal to integral 0 to infinity e to the power negative pt f of t dt, correct? Okay, now you break the limit 0 to 1 e to the power negative pt f of t. Why am I breaking this limit? You will understand it in some time, right? If you can't understand right now, okay, so have patience. E to the power negative pt ft dt plus 2 to infinity e to the power negative pt f of t dt, correct? Is it fine? Okay, now notice that for 0 to 1 it is equal to t, and for 1 to 2 it is equal to 1, and for t greater than 2 it is equal to 0. So that is why I broke the limit depending upon the value of t. So it is 0 to 1 t e to the power negative pt dt plus 1 to 2 e to the power negative pt dt plus 2 to infinity 0 dt. Of course 0 into anything is 0, so this is 0 of course. Now you can solve this, right? I am leaving it to you because it is simple integral. Okay, you know how to integrate it. You will just assume it as first function, this as second function, then you will solve it, and this is also very much easy, right? Okay, so now let's see another question. Laplace inverse of p plus 2 upon p minus 1 into p plus p minus 2, right? P minus 2, right? So of course it was very easy. You can see that it was very easy to find the Laplace transformation, but to find the Laplace inverse you need to remember the original function's Laplace transformation to solve it. What I mean is that let's see the solution. It states that the Laplace inverse of p plus 2 by p minus 1 into p minus 2, right? So let's solve it. P plus 2 by p minus 1 into p minus 2 is simply equal to what? It is equal to we can write a upon p minus 1 plus b upon p minus 2, right? Of course, like this. And simply now you can this is partial fraction if you don't know it. Okay, if you don't know, you need to check it. It is equal to a times p minus 2 plus b times p minus 1. Okay, now just compare the coefficients. I hope so that you can do that, but still I will do a plus b into p minus plus minus 2a minus b, and from this if you solve you will get it as on solving you will get negative 3 by p minus 1 plus 4 by p minus 2, correct? Is it fine? You solve it is fine. Okay, so basically it's Laplace inverse of negative 3 by p minus 1, it's p minus 1 plus 4 by p minus 2, correct? Okay, so it is equal to the linearity property. If you remember, p minus 1 plus 4 times the Laplace inverse of p minus 2. And now what was Laplace inverse of p minus 1 upon p minus a? If you don't remember, let's see it. It was equal to e to the power at, right? Okay, so it is negative 3 into e to the power t plus 4 times e to the power 2t. Answer, right? Okay, so now let's see some other functions to find the Laplace transformations of. So third states Laplace of t to the power n is equal to what? Is equal to gamma n plus 1 by p to the power n plus 1. Why and what is gamma function? Well, if you don't remember, then gamma, this is gamma not f, gamma of n is equal to integral 0 to infinity of t to the power n minus 1 e to the power negative t dt, and it is equal to n minus 1 factorial. So it can be written as n factorial by p to the power n plus 1, correct? Okay, let's see this also if you want to say its proof. Okay, but it is simple if you solve it. This, it is equal to 0 to infinity e to the power negative pt t to the power n dt, right? Substitute pt as equal to x, so we have dx is equal to p dt, so you have dx by p. Okay, and notice that when t is equal to 0 then x is equal to 0, and when t is approaching towards infinity then x is also approaching towards infinity, right? E to the power negative x t, I mean x by p to the power n into dx by p, correct? Okay, so you have 0 to infinity e to the power negative x to the power n by p to the power n plus 1 dx, right? So you have 1 upon p to the power n plus 1 integral 0 to infinity x to the power n e to the power negative x dx, and notice that this is this only. Okay, here just in place of n minus 1 it's n, right? Okay, so you have gamma of n plus 1 by p to the power n plus 1, which is equal to n plus, I mean n factorial, have I written factor there? Yeah, n factorial by p to the power n plus 1, correct? Okay, so I hope so that it is clear. And the most important thing is that the Laplace of t to the power n is equal to this quantity, which implies that Laplace inverse of n factorial by p to the power n plus 1 is simply equal to what? T to the power n, or Laplace inverse of 1 upon p to the power n plus 1 is t to the power n by n factorial, right? This is more important, right? Okay, and yeah, one more thing which you need to remember, that gamma of n plus 1 is equal to n times gamma of n, right? If you don't remember the properties, you need to remember that. And 1 by 2 factorial is equal to root pi by 2, which is equal to gamma of 3 by 2, right? And gamma of 1 by 2 is equal to root pi, right? You need to remember all this, of course. Okay, if you don't remember, then you can check out my video on integral calculus, so in that I have discussed it in great detail. Okay, so you can check that out. Okay, so now let's see a question. So of course it is easy to find the Laplace transformation, so I will directly tell you all to find the inverse, right? P cube plus 2 by p to the power 5. Okay, so Laplace inverse of 1 upon p square 2 upon p to the power 5, correct? Okay, now apply the linearity property, right? This 1 upon p to the power 5. Okay, so Laplace inverse of this quantity 1 upon p 1 plus 1, and it is also 1 factorial, correct? Plus 2 times Laplace inverse of 1 upon p to the power 4 plus 1, I mean this should be in power. Okay, this will be in power, right? Okay, I hope so that you understand why am I doing this. So this is equal to t plus, and what is there, 2 times Laplace inverse of 4 factorial. So if you are multiplying by 4, you will divide by 4 factorial, p to the power 4 plus 1, right? Okay, so t plus what is 4 factorial is 24. So, and what is this? This is equal to t to the power 4 by 12, right? So this is the f of t, right? I hope so that it is clear. Now let's see another function, Laplace of sine at, right? So what is it? Well, let me tell you together. It is a upon p square plus a square, and Laplace of cos at is equal to p upon p square plus a square, correct? And I guess that hyperbolic functions are not in the syllabus, Still, if you want, I will make a different video in which I will discuss about hyperbolic functions, because I don't think so that discussing it right now will make any sense, right? So still, if you want, I can tell that what are hyperbolic functions, because then you can derive it. Okay, so this is hyperbolic sine of t. It is equal to e to the power t minus e to the power negative t by 2. This is the value. Okay, and what is hyperbolic cos of t? It is equal to e to the power t plus e to the power negative t by 2, right? Okay, and what is hyperbolic tangent? It is equal to sine by cos. Okay, and hyperbolic cosecant is equal to 1 upon hyperbolic sine of t, of course, of t, right? And sec h is equal to 1 upon cos t, and hyperbolic cotangent is equal to, of course, this there will be a t, but for now just ignore it. This okay. So if you want, you can apply Laplace transformation on these two and then apply in other cases. Okay, and you know the linearity property, so you can solve it easily. Okay, so let me discuss for sine and cos functions. Okay, so Laplace transformation of sine of at is simply equal to, well, before that we need to define sine function, right? So what is sine? Well, we know that e to the power I theta is equal to cos theta plus I sine theta, and e to the power negative I theta is equal to cos theta minus negative I sine theta, right? Just subtract them, you get e to the power I theta minus e to the power negative I theta is equal to 2I sine theta, right? So sine theta is equal to e to the power I theta minus e to the power negative I theta by 2I. So I hope so that this is clear, right? Now just apply sine, I mean the Laplace transformation both sides, but put angle as 80, correct? Okay, so sine 80 is e to the power 80 by 2I minus e to the power negative 80 by, of course, I will be there. I should write over here I80, correct? Okay, upon 2I. Now apply Laplace transformation, you will get, okay, so of course 1 upon 2I is a constant, and we are applying this I80 minus 1 upon 2I Laplace of e to the power negative I80. Now if you remember, Laplace of e to the power 80 is 1 upon p minus a, correct? If you remember it, right? So over here it is equal to IA, a is equal to IA, right? Okay, this is equal to this. I hope so that it is understandable, right? So now when you solve, you get 1 upon 2I into 1 upon p minus a, and then you are getting 1 upon negative 2I into 1 upon p minus, I mean p plus I, correct? Okay, so 1 upon 2I is taken as common, so you get 2p upon of course you are sorry, it will be, since it's negative, I forgot that it is negative, I took it as plus. So when you subtract it, you get 2ia upon p square plus a square. You cancel this, you get a by p square plus a square, hence proved, right? Similarly, when you add that, you get e to the power I theta plus e to the power negative I theta by 2 is equal to cos theta. Now simply apply to get that expression, right? Of course. Okay, is it fine? Yeah. Let's see a simple question, Laplace transformation of, and of course you have to remember the inverse also, right? That that its inverse is equal to sin 80 and its inverse is equal to cos 80, right? You have to remember that, right? That is more important. So Laplace transformation of cos of 2t minus 3, correct? Okay. Now apply cos a plus a minus b. It is equal to cos a cos b minus sin a sin b, and it will become plus, right? Okay, correct. So you are left with Laplace of cos 2 3 into cos 3 plus sin 2t into sin 3. Now just apply that. You get cos 3 is a constant, so this is equal to cos 2t plus Laplace sin 3 into Laplace of sin 2t, correct? Now just apply the property. Cos 3, I mean the formula, it is simply equal to p by p square plus 4, since a is equal to, plus sin 3 into 2 by p square plus 4, correct? Is it fine? Yeah. So let's see some more problems. Now let's see this question. Laplace inverse of p plus 2 p minus 1 p square plus 4, right? Okay, yeah, it is somewhat different questions, so let's try this. So again we will apply partial fraction p square plus 4, and of course for a quadratic there's a different method, a upon p minus 1 plus bp plus c by p square plus 4, right? This is how you will factorize it. Now I won't solve for a and b, you know how to solve it. Okay, so let me write the expression. Okay, 3 by 5 p minus 1 plus negative 3 by 5 p plus 2 by 5 upon p square plus 4, right? Okay, take 1 by 5 common, right? p minus 1 plus negative or 2 minus 3p, it looks more beautiful, so that is why I wrote that way, p square plus 4, right? This is how you write it. And now you need to find the Laplace inverse. So 1 by 5 is a constant into 3 Laplace inverse of 1 upon p minus 1 plus what you have next is, or you can write it like this, negative 3 Laplace inverse of p by p square plus 4, correct? Okay, plus 2 times Laplace inverse of p1 upon p square plus 4, right? Now notice that this, it is equal to e to the power t, right? If you remember from the previous one, 3 by 5 e to the power t minus 3 times, and this is equal to cos of 2t plus, and here it is 4, so here it should be 2 by 2, so it will become Laplace inverse, or maybe it becomes sine of 2t, right? So I hope so that this is clear, and of course by 5 will be there, right? Since it has to be multiplied all over. Okay, fine. Okay, so let's move further. So let's study something called existence theorem for Laplace transformations. Let's see. So basically before that you need to know what is meant by a piecewise continuous function. Well, I discussed it in the previous video, I guess, in the Fourier series, so you can watch that. So to understand it better, I won't discuss it right now, but of course if you want, basically a function which is continuous in a piecewise way, in interval form. For example, if the function is continuous like this, a to b it is continuous, then from b to c it is continuous, then from this to this it is continuous, right? Okay, and second thing which you need to know is exponential order, right? Now let's see, this is something new which we need to discuss. Okay, so a function ft for t greater than equal to 0 is said to be of exponential order. I am not writing the full form, alpha, if there exists a constant alpha and k greater than 0 and t greater than 0 such that modulus f of t modulus f of t is less than equal to k e to the power alpha t for t greater than capital T, right? So it means that just bring this over there since it is always positive, so you have this quantity, the negative alpha t less than k. So it means that if you take the limit as t tends towards infinity, so you have this quantity, the negative alpha t will be less than k. So it means that this will be finite, correct? Hence it would imply that the function has a Laplace transform, right? Now if you could prove that there exists some alpha like that, so then you can say that function has the Laplace transformation and this is the sufficient condition of Laplace transformations. But if it fails, then it does not guarantee us that whether the Laplace transform exists or not. There are many other things to be discussed in this, but I guess this is not that much important. If it is important, I will make it in a separate video because it requires some more sort of like bounded function or something like that. So I hope so that I should move on to properties now. But of course, if you want, I will make a small video regarding the proof and all other things regarding it, okay? So now let's see properties of Laplace transforms. The first property, shifting property, right? Okay, so basically Laplace of some function f of t is equal to, suppose, f of p, then Laplace of a to the power at f of t is equal to simply f of p minus a, right? Okay, and this is called first translation, right? First translation, okay? And the second property is that I mean not the property, the second translation, if f of t is equal to f of p and g of t is equal to, suppose is equal to f of t minus a if t greater than a and is 0 when if t less than a, right? Suppose this is the condition, then it means that then it implies L of gt is equal to e to the power negative ap times f of p, right? Okay, and this can be simply proved, so no need to worry about that, okay? So let's see also the proof. This is called the second translation, okay? I am not writing. So let's see the proof even of the first translation first of all, then the second translation. So e to the power at f of t 0 to infinity e to the power negative pt e to the power at f of t dt. So it is simply equal to 0 to infinity e to the power negative p minus a f of t dt. Now you can say p minus a as some theta, so you have 0 to infinity e to the power negative theta, where theta is a constant again, f of t dt. So notice that this is again equal to f of theta, correct? Okay, so now substitute back, it is equal to this, okay, fine, correct, because it is again equal to Laplace of ft, right? Okay, Laplace of ft, but with a different constant, with a theta over there, okay? There's no other difference. Now we have L of gt. Yeah, it is capital G or small g, whatever you want to say. Okay, let's change it to small g if you have confusion, because generally we represent this function in small letters only, so that is why. like f also we are representing small, so let's keep it small. So we have 0 to infinity of e to the power negative pt g t dt, right? So we have 0 to a e to the power negative pt into 0 dt plus a to infinity e to the power negative pt f of t minus a dt, correct? Okay, this is 0 since the function from 0 to a was 0 and from a to infinity it was t minus a, right? So a to infinity e to the power negative pt f of t minus a dt. Now substitute t minus a as equal to x, so you get t is equal to a plus x. Now you can solve it further and notice that when t is equal to a, then x is equal to 0, and when t is approaching towards infinity, then x is approaching towards infinity. So you are left with 0 to infinity of the quantity e to the power negative pt, and what is t? T is equal to a plus x. So this is equal to a plus x simply, and this is equal to f of x into dx, correct? And notice that 0 to infinity e to the power negative ap into e to the power negative tx fx dx. So e to the power negative ap integral 0 to infinity fx, or yeah, let's write it like this only, or let's keep it in the format only, minus px fx dx. Now this is again Laplace of f of t, which is equal to f of p, right? So you got negative ap into Laplace, or simply f of p, right? Hence proved. Okay, so now let's see a problem to understand it better. So question, it states that Laplace of t cube e to the power 2t 3t, suppose. This is the question. Solution: Laplace of e to the power 3t t cube, it's simply comparable to Laplace of e to the power at f of t, correct? And what is it equal to? F of p minus a, correct? Okay, so basically let's find Laplace of t cube. It is simply equal to gamma of n plus 1 by p to the power n plus 1. You remember t to the power n is equal to that, so it is equal to 3 factorial upon p to the power 4, which is equal to 6 upon p to the power 4, right? Okay, so Laplace of e to the power 3t t cube is equal to f of p minus 3, which is equal to 6 by p minus 3 to the power 6, correct? Okay, simple, very easy, right? Okay, so now let's and of course you could have done without using property, but of course if we are learning property, then we need to apply that also, right? Maybe if in your exam it is not asked, then you can do it using any method. If it is asked, then you can use the properties, because many times you can't attempt the question without properties. But if you know the proof, then you know that you can directly apply the formula of Laplace transformation. You can approach to the answer, right? So there is no harm in doing that. Okay, now suppose I give you a question, this t sine 2t, how will you solve it? Well, it's very easy. So what you will do is that you will write sine in terms of its this polar form, negative 2it by 2i. Now it's simply a cup of tea, because you know that e raised to the power something, e to the power at, you know how to solve it, t times e to the power at. So it is again of the form f of t e at, right? This, okay, Laplace of this. Okay, so you know how to solve it. Okay, I'm not solving it, you can solve it on your own. Okay, now let's see some amazing problem. Laplace of e to the power negative 2t sine of root t, right? So again you need to solve for f of p plus 2. It will be f of p plus 2, right? So now we need to find the Laplace of sine of root t, right? So how will you solve it? Well, okay, sine theta is equal to theta minus theta cube by 3 factorial plus theta to the power 5 upon 5 factorial till infinity, right? Okay, so sine of root t is equal to t to the power half minus t to the power 3 by 2. 3 factorial plus t to the power 5 by 2 by 5 factorial and so on till infinity, right? Correct. So we have Laplace transformation of sine of root t is equal to the Laplace of this whole expression. Now what is Laplace of 1 by 2, t to the power 1 by 2? It is simply equal to 1 by 2 factorial upon p to the power 1 by 2 plus 1, correct? Okay. Now what is the Laplace of t to the power 3 by 2? Well, it's simply equal to minus 1 by 3 factorial, of course, t to the power or 3 by 2 factorial upon the quantity p to the power 3 by 2 plus 1, correct? And so on till infinity, right? If you are understanding this, what am I doing, right? Is it fine? Basically, if you solve it, what you are going to get is root pi by 2 into p to the power 3 by 2 minus 1 3 by 2 into 1 by 2 root pi by p to the power 5 by 2 and so on till infinity. And if you take root pi by 2 p to the power 3 by 2 common, you get 1 minus 1 by 2 square p by 1 factorial plus 1 upon 2 square p by 2 factorial and so on till infinity, like this. Which means that what is it equal to now? It is equal to root pi by 2 to the power 2 p3 by 2, and this is equal to e to the power negative 1 by 4p, right? Why? Because e to the power theta is equal to this expression. E to the power x is equal to what? It's equal to 1 plus x square by 2 factorial, x cube by 3 factorial and so on till infinity, right? Fine. So if you substitute like that, negative 1 upon 4, you will get that expression only, right? Fine, correct? Okay. So you got root pi by 2p 3 by 2 into e to the power negative 1 upon 4p is equal to f of p, right? You got this. Now you can simply substitute p plus 2, you will get the answer. Okay. Now let's see some other problem, or let's move to the next property, right? Let's see this simple question. Let's see how will we solve this. Okay, so let's see solution. So basically you can write it like this: 3 times the inverse p by p square minus 2p plus 5 plus 2 by the Laplace inverse, even the Laplace inverse of the quantity 2 will be over here, p square minus 2p plus 5, correct? Okay, so we are left with simply 3L inverse p upon, let's make a perfect square, right? So we have p square minus 2p plus 1 plus 4 plus 2L inverse 1 upon p minus 2p plus 1 plus 4, right? Okay, so we have what we have 3 times L inverse of the quantity p upon p minus 1 whole square plus 4 plus what we have 2 times the L inverse of the quantity 1 upon p minus 1 whole square plus 4, right? Correct? Okay, is it fine? Yeah. Now notice that we have p minus 1 over here, so we will make 1 over here also. So we have simply, it is equal to that 3L inverse p minus 1 by p minus 1 whole square plus 4 plus 3 times L inverse of 1 upon p minus 1 whole square plus 4, correct? And over here we will multiply by 2 and we are going to divide it by 2, right? So we are going to do this. And why we are doing this? Because we can see that we can form a sign over there, right? So that is why. Plus this plus L inverse the quantity 1 upon p minus 1 whole square plus 4, and this 2 of course now. Okay, so you can add and of course you will make 2 over here also and over here also, because you got that. Okay, so you have 3 times L inverse of the quantity. What is this? This is equal to e to the power t into cos of 2t, right? Fine. Plus 5 by 2 sine of 2t, right? Fine. And of course into e to the power t, right? So I hope so that it is clear now. Okay, if it's not, you can watch again so that you can understand it better. All right, because notice that p minus 1 means it had something like this, because the function looked f of p minus 1, right? It means that it had 8 e to the power t times a function f of t, right? And f of t was over here cos 2t, and over here it was sin 2t, right? So this is how you solve it. Now let's see something called change of scale property, right? So suppose we have L of ft simply equal to f of p, which means that L of f at is 1 upon a f of, provided a is not equal to 0, right? Okay, let's see the proof. It is very simple. L of f of t at is equal to 0 to infinity e to the power negative p, and we have f of at dt. So now substitute at is equal to x, so we have t is equal to x by s, so we have dt is equal to x by dx by a, and when t is equal to 0 then x is equal to 0. As t is approaching towards infinity, then x is also approaching towards infinity, so we have 0 to infinity of e to the power negative p x by a into the quantity f of x dx by a. So we have 1 upon a integral 0 to infinity e to the power negative p by a x fx dx. So notice that over here the constant is not p, it is negative p by a, I mean p by a. So we have 1 upon a f of p by a, right? Correct? Fine. Did you understood it? If you did not, then watch it again, you will understand it. Okay, so let's see a question on it so you can understand it better. Okay, let's see. So the question states that and of course there is a variation over here, that it is basically, if I write it clear, it will be 1 upon mod a f of p by a, of course, which will depend upon a greater than 0 and a less than 0, right? But in most of the cases you will not need it, I think so, right? So if Laplace of f of t is this 1 upon p times p square plus 1, right? You are given this, then find Laplace of e to the power negative 2t f of 3t. This is a very simple question, so let's see. So Laplace of e to the power negative 2t f of 3t, this is the question which is given, right? So notice that Laplace of e to the power negative or maybe at ft dt, sorry, not dt, why I am writing dt, is equal to f of p minus a, correct, right? So notice that over here we have Laplace of f of 3t, right? So it is 1 upon 3 f of p by 3, right? Fine, correct. Now when you are going to solve for this one, and since we are given f of p as f of p is equal to 1 upon p into p square plus 1, so when you solve it, so we get f of p by 3 is equal to 3 by p into p square by 9 plus 1, which is equal to 27 by p into p square plus 9. And notice one thing, that we had to multiply by 1 by 3, so we have p by 3 is equal to 9 by p into p square plus 9, correct? Fine, is it fine? Is it correct? Okay, so if you do this, and yeah, Laplace of e to the power negative 2t f of 3t is simply equal to p plus 2 by p plus 2, because now we will replace p by p minus a, so a is equal to negative 2, so it will be p plus 2. right? And that you can do. Okay, that is very simple, just replacing p by p plus 2, right? Now if you want, I can tell some special types of function also, the Bessel's function and the error function, but I guess this is not a part of your syllabus, so I think that I should skip this for now. And if you want, I will make a separate small video on it so that you can understand it, right? Because if I discuss it right now, it will take lots of time, and I don't think so that it is important for first year, right? So that is why I'm skipping it right now. Now let's see Laplace transformation or transforms of derivatives. Now it's something interesting, derivatives, right? Let's see, derivatives. Okay, it's something interesting which we are going to do. So suppose ft is a continuous function for all t greater than equal to 0 and is, sorry, what is it, and is of exponential order. Suppose alpha, let f dash t be piecewise continuous on 0 to infinity, right? Basically it should be continuous. Then l f dash of t exist for p greater than alpha, and the value is, of course you don't need to remember the definition, you just need to remember this. Definition is basically when you need to prove something, right? So you need to remember those things before proving anything, that whether it is possible also or not, but in general sense it is mainly possible, right? So no need to worry about that. Okay, so it is equal to p f of p minus f at 0, correct? Okay, now notice that and the second thing, f double dash t is equal to p square l f t, right? lft, right, minus p f at 0 minus f dash of 0, correct? Fine, right? Let's check for suppose okay, let me prove it, then we will see the general form, right? So it will be better. So L of f dash of t is equal to the integral 0 to infinity e to the negative t f dash of t dt, correct? This is fine. Assume this as your second function, this as your first function, negative pt f of t 0 to infinity, derivative it will become p 0 to infinity. This is integration of parts, don't say me that why I did this, because it is something which you should know, right? So you can learn it, or maybe you can revise it, okay, if you don't remember, right? Because I can't discuss it right now, else the lecture will go like 5-6 hours then if I discuss all this. Okay, I hope that you understand it. Okay, so this, and then it will become e to the power negative pt ft dt, correct? So it is simply equal to what? When you substitute infinity, then this will become 0 since the exponential order is alpha, and when you substitute 0 you will get f of 0. So you get negative f of 0 plus p times f of p. Notice that this is equal to f of p, right? Okay, so we have f dash of p is equal to Laplace of this is equal to p fp minus f at 0, correct? Okay, now L of f double dash of p is simply equal to what? Is equal to, you substitute over here, you get p f l, this is f dash of t, correct, minus f dash of 0, fine. Is it correct? Now what is L of f dash? Well, let me explain it first of all, then only you will understand. Now you can write this as like this also, p times the Laplace of f of t minus f at 0. Now instead of f dash of t, write f double dash of t, right? You'll get Laplace of f double dash of t is equal to p times Laplace of f dash of t, right, minus f dash of 0, correct? Fine. Now what is the Laplace of f dash? It is equal to p f of p minus f of 0 minus f dash of 0. So you are left with p square f of p minus p f at 0 minus f dash at 0. I hope so that it is clear now. If you don't understand, then please watch it again, you will understand it, okay? Or comment me in the comment section, I will try to explain there also. Okay, so now suppose you have suppose nth derivative. So let's generalize it. L Laplace of this nth derivative of t is equal to p to the power n f of p minus p to the power n minus 1 f of 0 minus p to the power n minus 2 f dash of 0, and so on till f of n minus 1 at 0, right? Okay, fine, correct. Okay, so let's see some questions on it. Laplace of t e to the power 2t. Of course, this question can be solved using shifting property very easily, but right now to explain the concept, I will use the Laplace derivative, right? I mean by using derivatives, right? So let's see how will we do it, okay? So f of t is t e to the power 2t, so f dash of t is equal to e to the power 2t plus 2t e to the power 2t, right? Correct? Okay. So we have L of f dash, this is L, sorry. Okay, I hope that you understand it, that it is f dash, okay, of f dash t is equal to the p times f of p minus f at 0, correct? Fine. Now this is equal to Laplace of e to the power 2t plus 2 times e to the power 2t. What is p? Well, p will be only, okay. And this is equal to the Laplace of e to the power t 2t into t, correct? And what is 0? When you substitute t is equal to 0, you will get 0 times e to the power 0, which is equal to 0. So I'm not writing that, okay? So let's solve it. Let me choose another color. Yeah, so we have L of e to the power 2t plus 2 times L of t e to the power 2t is equal to p L t e to the power 2t, right? So this and this are same, and this is equal to what? This is very simple. This is 1 upon p minus 2 is equal to p minus 2 times the L times the required thing. So the required thing is equal to 1 upon p minus 2 whole square, right? The Laplace of the required thing, you can solve it, okay? So let's see another question. L inverse of p by p square plus 1, and of course whatever am I telling you, you should also see it in inverse form also, that suppose if this expression is equal to this, then it implies that its L inverse will look like this, okay? Fine, correct. You should see every property with respect to inverse also. Just take inverse both sides, okay? So that is why I'm not telling that. If you want, I can tell that also. Suppose over here also in the change of scale, it also means that L inverse of 1 upon a f of p by a is equal to f at 80, right? Like this, okay? Similar is the case with the shifting property also, right? Okay. So you are given this, right, this whole square, and it is given as 1 upon 2 t sine t, right? Okay, of course this is f of t. Then we have to find L inverse of p square by p square plus 1 whole square, right? Let's see how we'll solve it. Solution, I think white is better, okay? So we are given f of t is equal to 1 by 2 1 by 2 t sine t. Okay, fine. So it means that f dash of t is equal to 1 by 2 sine t plus t cos t, like this. So we have f dash of t is equal to L inverse p f of p minus f at 0, right? What I told, it is that thing only. Okay, I told that its inverse looks like this, right? Like this. Okay, so that is what am I doing over here. So it looks like this, and now you just substitute the value. What you are getting is half times sine t plus half times t cos t is p times p by p square plus 1 whole square minus what is function at 0. Well, when you substitute t is equal to 0, then it will become 0, since t into sine t, when you substitute 0, it will be 0, right? Minus 0, right? So basically p square by p square plus 1 whole square is basically equal to what? Of course, L inverse of this. So L inverse of p square by p square plus 1 whole square is equal to this. Why am I writing like this, right? This is equal to 1 by 2 t cos t plus sine t, right? And this is what we needed to prove, right? We needed to find. So this is the answer, right? Okay, so let's see the other property. So now let's see the Laplace transforms of the functions divided by t. Let's see. If L of f of t, sorry, L of t is equal to f of p, then it means Laplace of f of t by t is simply, then this is equal to p to infinity fu du, right? And of course, provided limit t tends to 0 positive or 0 plus, or the RHL, the right hand limit of f of t by t, it exists, right? Okay, now let's see its proof also, and notice that f of u is simply the Laplace of f of t, right? Okay, so notice this thing, right? Now solution, I mean the proof, not the solution. Proof, p to infinity capital fu du is equal to integral p to infinity 0 to infinity e to the power negative pt f of t dt du, correct? Now let's change the order, and of course, if you don't know how to change the order, you can check my playlist of integral calculus and multiple integrals. In that I have discussed it, so it will help you, right? I mean, they are one shots only, right? So one shot of multiple integrals, I guess you can check, right? In that I had discussed, and a bit in integral calculus too. So if you want, you can check, okay? But probably in the multiple integrals I've discussed, so you can check that out, okay? I've made the video like 2-3 months back, okay? Okay, so now let's change the order. You get 0 to infinity, what I have written, 0 to infinity, this is now t over here, and this is p to infinity e to the power negative ut f of t du, then we have dt, right? Now ft is a constant with respect to u, you just bring it out, you get 0 to infinity e to the power wait, it will be f of t, right? F of t, then you have integral p to infinity e to the power negative ut du dt, correct? Now you get this f of t, and then negative e to the power negative, so it becomes e to the power negative ut by t 0 to infinity. Of course, this suppose from p to infinity, so I remove this negative sign, so it becomes like this. So it will become infinity to p, so you get integral 0 to infinity of e to the power negative pt f of t by t dt, which is equal to the Laplace of ft by t. But don't remember just this thing, Laplace of f of t by t, right? by t is equal to integral p to infinity capital F u du, but f of t by t is the Laplace inverse of p to infinity f u du, right? Okay, remember this also. The question states the Laplace transformation of e to the power negative 2t sine 3t upon t. We need to find this, and now let's solve it. Solution. So basically we have Laplace of f of t by t, right? Basically this, okay? So this is equal to Laplace of e to the power negative 2t sine 3t, right? And now you know how to find its f of p, right? You can solve it, right? Because you know how to find for sine 3t, right? And even if you don't know, it is very simple. Let me tell you also. If you face any problem, just write sine 3t as e to the power 3 I t minus 3 negative 3 I t by 2i. Now we have this and this just exponential, and now you know that Laplace of e to the power at is equal to 1 upon p minus a. Just solve from that, okay? Very simple, very easy, right? Then you just apply the formula that it goes from p to infinity of whatever you get from this. You just substitute there from p to infinity, and then whatever you get the answer, that is the answer basically, okay? So that it is clear, right? Okay. Laplace transformation of functions multiplied by t to the power n. Let's see what is it. If Laplace of t to the power n, I mean f of t is f of p, then the Laplace of t to the power n f of t is simply equal to negative 1 to the power n dn by dpn of f of p, right? Or simply negative 1 to the power n into fn derivative of p, right? Okay, correct. So you can prove it also very easily if you want. Let's see the proof. Even proof, let's see. So we have that f of p is integral 0 to infinity to the power negative pt f of t dt. So we know that f of p is equal to this quantity, so f dash of p will be equal to 0 to infinity negative t into e to the power negative pt f of t dt, right? Because p is a constant with respect to t, and with respect to p, t is a constant, right, when you are differentiating. So that is why. So d2 f by dp square is equal to 0 to infinity t square e to the power negative pt f of t dt. It means that dnf by dpn is equal to 0 to infinity negative 1 to the power e to the power negative pt t to the power n f of t dt, which means that negative 1 to the power dnf by dpn is equal to the Laplace of f of t to the power n, right? Correct. Okay, so hence proved. Now let's see a question to understand it better, right? So question states this. Now let's see how will we solve it. Well, it's equal to negative 1 square d2 by dp square of f of p, and what is L of cos of 2t? It is simply equal to p by p square plus 4, right? So this is equal to f of p. Now it is a cup of tea to differentiate it 2 times, then you will get the answer, right? So this is how you just solve it, okay? So maybe if you have this question, Laplace of t e to the power negative 2t sine 4t, simply what you are going to do is that negative 2t. So over here this is your f of this is your ft, right? This is your ft. So it means that it will be negative df by dp, since it is only t to the power of 1. And what is f of p? It is simply equal to 0 to infinity e to the power negative pt f of t dt. And again I told you how to do it, right? It is simple. Since you will write sine of 4t as e to the power 4it minus e to the power negative 4it by 2i, then you will multiply with e to the power negative 2t, then you will solve it, right? It is very simple. Exponential, it's very easy. P1 upon p minus a, right? Like that. Okay, or you can do like that also, that Laplace of sine of 4t is equal to 4 upon p square plus 16. Then you will apply the shifting property, you will get p minus a, which means that I mean f of p minus a, so you get 4 upon p plus 2 whole square by 16, right? So basically it will become the derivative of the quantity 4 upon p plus 2 whole square plus 16. There are multiple methods to solve this problem, right? Now again, as usual, we need to find the Laplace inverse also, because if we know this, then it implies that this is equal to the Laplace inverse of this also, right? Fine, is it correct? Right. So it means that I mean, let's solve Laplace inverse of p by p square, p by p square plus 4 whole square, right? So just do what? Assume g of p is equal to 1 upon p square plus 4, right? So what is the Laplace inverse of g of p? Well, it is very simple. It is Laplace inverse of 2 by p square plus 4 1 by 2, which is equal to 1 by 2 sine of 2t, right? Correct, which is equal to g of t, right? Now notice that g dash of p is equal to negative 2p by p square plus 4 whole square, right? Since we assumed that g of p is equal to this, right? You solve it. So Laplace inverse of g dash of p is equal to simply what? Negative 2 times the Laplace inverse of p by p square plus 4 whole square, right? And what is this? This is equal to, we can write it like this: Laplace inverse of negative g dash of p is equal to this stuff, and then notice that this is negative of, simply it is equal to t. G of t is equal to 2 times the required quantity, right? So we have negative t times what is g. G is simply equal to what? It is equal to 1 by 2 sine of 2t is 2 times this quantity, so bring this over here, so we have 1 by 4 this quantity, right? I hope so that it is clear. So basically it is this, right? Okay, I hope so that it is correct. And I think there is nothing more in it. And yeah, there was a negative sign also, so this will become positive at the end. Okay, fine. Okay, so let's see further. So now let's see Laplace transform of integrals. Okay, so suppose you have Laplace transformation of f of t and it is equal to f of p. Okay, and you are asked to find the Laplace of integral 0 to t of the quantity f of u du. So this is equal to 1 upon p f of p, and of course you have to remember its inverse too, that the Laplace inverse of 1 upon p f of p is equal to integral 0 to t f of u du, right? Okay, so let's see its proof. Okay, so basically you can assume phi of t equal to 0 to t f of u du, correct? You can write it like this. So it means that d phi by dt is equal to f of t, correct? You can use the Leibniz formula if you remember, right? Leibniz rule. So what is the Laplace of this? It is equal to the Laplace of f of t, correct? And now if you remember, L of f dash of t is equal to p f of p minus f at 0, correct? If you remember this, right? Is it correct? Okay, so basically you are left with p times the Laplace of phi of t, correct, minus phi at 0 is equal to Laplace of f of t, correct? Okay, now notice that phi at 0 is simply equal to integral 0 to 0 of f of u du, which is equal to 0, of course, right, since the limits are same, right? So basically we are left with that L of ft, I mean the Laplace transform, is basically equal to what? Is equal to p Laplace transform of phi of t, correct? Okay, so now what's next? Okay, let's see. So what is it? It is equal to f of p by p is equal to the Laplace transform of phi of t. And what was phi of t? Phi of t was basically the integral 0 to t f of u du, right? Okay, understood. So now let's see a question, integral 0 to t of the quantity u e to the power u sine square u du, and you need to find the Laplace of this. Okay, and yeah, remember, if you are given 0 to t e to the power t sine square t dt, don't get afraid, because when you see t over here also and over here also as a variable, then you get confused. But don't worry, just treat t over here as u. Okay, don't worry, even if it is t, you can use it as u also, right, like this. Okay, so don't worry regarding that. Okay, so we can see it is of this form only, so let's solve it. So integral 0 to t f of u du is equal to f of p upon p, right? Now what is the Laplace transform of t e to the power t sine square t, right? Let's see it. Now let's find the Laplace transform of sine square t first. So basically you can write sine square t, if you remember this identity, that cos 2 theta is equal to 1 minus 2 sine square theta. So from this you get sine square theta is equal to 1 by 2 minus cos 2 theta by 2, right? Okay, so when you take the Laplace transformation, you get 1 upon 2p minus 1 upon 2 p by p square plus 4, correct? The Laplace transform sine is square theta, right? Or sine square x or u, whatever was the question. Okay, and now let's find e to the power t into sine square t. Well, this was your function which you got f of p in that case for sine square t. So when you apply e to the power t, so you will just have to replace p by p minus 1. So 1 upon 2 p minus 1 minus p minus 1 by 2 times p minus 1 whole square plus 4, correct? Fine. Okay, and now Laplace of t, and suppose this is equal to some g of p. Okay, t sine square t. Now multiplication by t, so it will be negative d by d p of g of p. So you basically find this and you will get the Laplace of this, right? Okay, the Laplace transform. Okay, and I think this is what it is asked. So from this you will get f of p, right? So once you get f of p, you can just substitute it over here to get the answer, right? Okay, so I think that you can solve this. You know how to find the derivative of this term. Okay, fine, understood. Okay, so this is equal to f of p. So let's do another problem, the Laplace inverse of this quantity. So basically it is of the form f of p by p, right? Where f of p is simply equal to what? It is equal to 1 upon p square plus 4, right? And now you know that it is very simple to evaluate. So it will be equal to 0 to t f of u du, correct? Right? So notice that Laplace inverse of f of p will be equal to Laplace inverse of 1 upon p square plus 4, just multiply by 2 and divide by 2. You get half sine 2t, correct? Okay, so basically you are left with integral 0 to t 1 by 2 sine 2t dt, and it is very simple to evaluate, right? So from this you will get the Laplace inverse of 1 upon p square plus 4 is basically the integral 0 to t 1 by 2 sine 2t dt, correct? Okay, so now let's see another question or maybe another concept. So this is the integral which we need to evaluate. So let's see how we can apply the Laplace transformation and solve this integral. Let's see. So integral 0 to infinity t e to the power negative t sine cube t dt, right? This is the question. So what we can do is that notice that integral 0 to infinity e to the power negative t sine cube t dt. This is the question. Notice that we can compare it with this t sine cube t dt. So just put p is equal to t. We basically need to put p is equal to 1 to get to this integral, right? It means that the integral 0 to infinity e to the power negative t sine cube t dt is basically equal to the Laplace transform of t sine cube t at p is equal to 1, right? Now you know how to evaluate this Laplace transformation. Well, basically you can either use sine cube t, you can write it as e to the power I t minus e to the power negative I t by 2i, then cube it, either do like this. So we have already practiced such kind of Laplace transformation, so I think it would be doable for you, and you can notice that it is of the format t into f of t, so you can solve it, right? I hope so it is doable, right? If you have any problem, you can tell in the comment section. I will make a video on it. Okay, so now let's move to the convolution theorem. But before that, we need to know what is meant by convolution of two functions. Let's see. So convolution of two functions. So suppose let f of t and g of t be defined for t greater than equal to 0, then the convolution of f of t and gt is denoted by convolution f and g, or you can say f star g of t is given by f star g t integral 0 to t f at u g of t minus u du. Right, I hope so that it is understandable. Okay, means this is the definition. Okay, now notice that if you use g first and then f, you will get 0 to t g of u f of t minus u du, correct? Now notice that when you substitute t minus u as z or maybe some other variable in, suppose, the first equation, in first you substitute and then solve, you will get back to this equation, right? It means that we need to know some of the properties, then I will explain that what I meant there. So the first property, first commutative, this is what I wanted to tell, that f star g of t is equal to g star t of t, right? I mean g star f of t, which means that it is commutative. That is what I meant when I said substitute this as this. Okay, so if you substitute like this, then you will end up getting these two expressions are equal, right? Same. Now let's see the second property, associativity, right? Okay, so f star g t is equal to, I mean f star g star, suppose h is equal to f star g star h, right? This is the associativity, and f star 0 is equal to 0 star f and is equal to 0 always, correct? Okay, so null element exists in this case is equal to 1 cross f but is not equal to f, right? Sometimes it may be, sometimes, or maybe not, sometimes or maybe not. Okay, or maybe it exist or maybe don't exist. For example, you take f of t as t, suppose, and g of t as 1, you solve with them, you will end up getting that they are not yielding t, right? How? Let's see. 0 to t, t into 1 dt is basically u into du is basically equal to 0 to t u du is equal to t square by 2. So it is not equal to t, of course, right? Understood? Okay. Now let's see the convolution theorem for Laplace transformation. Okay, let's see. Laplace of f of t is given as f of p, and Laplace of g of t is suppose capital G of p, right? Then we have, wait a minute, yeah, Laplace of f, let me write properly, f star g of t is equal to the Laplace of 0 to t f of u g of t minus u, this is basically the definition, and is equal to f of p times g of p, right? Okay, it's inverse, that the inverse of the quantity f of p into g of p is basically the integral 0 to t of the quantity f of u into g of t minus u du, correct? Okay, so you should remember the Laplace inverse very thoroughly, right? Because it is very much important, because you can find the Laplace transformation but you can't find the inverse easily, so that is why. Okay, let's move to the next question or maybe concept. Let's see, but before that let's see its proof, right? So Laplace transformation of 0 to t f of u g of t minus u du, right? Okay, this is equal to 0 to infinity e to the power negative pt 0 to t f of u g of t minus u du dt. It can be written as 0 to infinity integral 0 to t e to the power negative pt f of u g of t minus u du dt, correct? Okay, now I'm going to use change of order. If you don't know, you can check out my video of multiple integrals. It is in my channel only, so you can go and check it out if you don't know, else you can continue with the video. So notice that this limit is of u and this is of t, right? So we will interchange the limits, right? Not the limits, the variables, this du and dt, and we will change the limits accordingly. So it becomes 0 to infinity u to infinity of e to the power negative pt f of u g of t minus u dt du, right? So now what you can do is that substitute t minus u as z, right? So you basically end up getting integral 0 to infinity of e to the power negative p u plus z, because t was u plus z, and notice that when u is equal to when t is equal to u, then this is equal to 0, and when t is approaching infinity, then this is also approaching, then z is also approaching infinity, right? Of the quantity f of u times g of z dz du, correct? So integral 0 to infinity e to the power negative p u f of u du, of course they both were different, so that is why I brought it like this, and I hope so this is clear, right? Dz, and this is simply equal to f of p and this is g of p, right? Hence proved. Now let's see a problem and then we will move further. Okay, so let's find the Laplace inverse of this quantity. So Laplace inverse of p upon p square plus 4 whole square. So we can clearly see two functions over here. Laplace inverse of p by p square plus 4 into p square plus 4, right? Suppose this is your f of p and this is your g of p. So what is the Laplace inverse of f of p? It is the inverse of p upon p square plus 4, which is equal to simply cos 2t, correct? Is it fine? Yeah. And Laplace inverse of g of p is simply equal to Laplace inverse of 1 upon p square plus 4. So multiply by 2 and divide by 2. get 1 by 2 sine of 2t, correct? Okay, so Laplace inverse of p by p square plus 4 whole square is Laplace inverse of the quantity integral 0 to t f of u g of t minus u du, correct? Okay, which means it's equal to Laplace inverse of the quantity infinity to t, sorry 0 to t of cos of 2t or 2u into sine of 2t minus 2u du. And of course now it is very simple, this is sine a minus b, you can open it and then integrate it. Okay, so it is something which is doable, right? Okay, and I am really sorry, there will be no Laplace inverse over here, sorry, we are evaluating the function. This is f of t, means this is the required function, this is the this is the required L inverse of f of p, whatever f of p or maybe some q of p, right? Okay, which was given. Now let's see something called initial value theorem. Let the Laplace transformation of f of t is f of p and f dash t be piecewise continuous, right? And is of exponential order for alpha, suppose alpha for t greater than equal to 0 if limit p tends to infinity p f at p exist, then limit p tends to infinity p f of p is equal to limit t tends to 0 of f of t, right? Okay, well, let's see its proof also, we have sufficient space over here. So Laplace transform of f dash t is equal to p f of p minus f at 0, correct? Fine. Okay, now since we know that Laplace transform, I mean the mod of f of t is less than m times e to the power alpha t, because we had said its exponential order as alpha, right? If you remember, for the condition of existence of Laplace transformation, right? If you remember that. So now remember one property, that the this integral e to the power negative pt f dash t dt, of course this is the Laplace transformation of f dash t, it's always less than the integral 0 to infinity e to the power negative pt mod f dash t. If you remember this property, that mod of an integral is less than equal to the integral mod of that thing, right? Okay, understood? So basically this is less than, maybe I should erase this. Yeah, now remember that 0 to infinity e to the power negative pt, now f dash t was less than equal to m e to the power alpha t, m e to the power alpha t dt, correct? Fine, is it understandable? Yeah, so this will be like this negative p minus alpha some m dt, right? So this is m by p minus alpha, and of course p is greater than alpha, right? Okay, for p greater than alpha it can't be equal also. So this is the integral e to the power negative pt f dash t dt limit. Okay, modulus, of course. So just use limit p tends to infinity both sides this, and limit p tends to infinity of m by p minus alpha. Understood why it is 0? Because it is m by infinity, which is equal to 0. Of course I can't write infinity directly, it should be in the limiting case, but to explain I'm writing like that. So it is tending towards 0, so mod of something is less than equal to 0, which means that that thing is equal to 0, which means that the integral 0 to infinity e to the power negative pt f dash t dt is equal to 0 when p tends towards infinity, right? Okay, now why am I calculating this? Well, let's see. You remember this? Okay, now here apply limit as p tends towards infinity of integral 0 to infinity e to the power negative pt of the quantity f dash t dt. This Laplace inverse, I mean Laplace transformation, is limit p tends to infinity p f of p, right, minus f0. Okay, so basically we proved that that is equal to 0, which means that the limit 0 is equal to limit p tends to infinity of p f of p minus f at 0. So limit p tends to infinity of p f of p is equal to f at 0 for the function defined at 0. But suppose if it is not defined at 0, then we will have the limiting case. So that is why there was a limit. That limit as t tends towards 0, of course 0 positive, this will be equal to this. Okay, and I hope so that you understood this proof. Okay, we will see its application, but before that let's see the final value theorem. It is sometimes called IVT also. Okay, IVT, initial value theorem. Okay, ninth final value theorem or FVT. So similar condition as in the case of IVT, like L of ft is equal to f of p, f dash t be piecewise continuous for t greater than equal to 0, and limit t tends to infinity f of t exist. Then we have this expression that limit t tends to 0 p f of p is equal to the limit t tends to infinity f of t, right? Let's see its proof also. Notice that Laplace transform of f dash t is equal to p f p minus f at 0, simple, 0 to infinity e to the power negative pt f dash of 0, I mean f dash of t dt is equal to p f of p d, why am I writing dt, minus f at 0, right? Now you just substitute over here p, you just apply the limiting case that p approaches to limit p tends to 0 of the quantity 0 to infinity e to the power negative pt f dash t dt is basically equal to the limit p tends towards infinity p f p minus f at 0, correct? Okay, now when you substitute p as 0, this will become 1 and this will be left. So because 0 to infinity f dash of t dt is simply equal to the limit p tends towards 0, why I wrote infinity there, it will be 0 p f of p minus f of 0, right? Now integral of anything f dash of x dx is equal to fx, right? You remember that the integral is basically antiderivative, right? So that is why. So this is equal to f of t 0 to infinity is equal to limit p tends towards 0 p f p minus f at 0, correct? So we have limit as t tends towards infinity f of infinity, I mean f of t minus f at 0 is equal to limit p tends to 0 of p f of p minus f at 0. This and this gets cancelled, so we are left with limit p tends towards 0 p f of p is limit t tends towards infinity of f of t, correct? Fine. So now let's see a problem, then we will understand it better. So the question states that verify IVT and FVT for f of t is equal to e minus 60, right? Solution. So what is the Laplace transform of f of this f of t? It's very simple, 1 upon p plus 6, of course multiplied by 2, right? It is very easy. By now you should be knowing that why it is this, right? It is very simple. So now apply for IVT. It should be limit p tends towards infinity, p f of p, which is basically limit p tends towards infinity. It is equal to p upon p plus 6 2, and of course this is equal to what? 2, right? Correct. Fine. Now limit t tends towards 0 of f of t, it is equal to the limit t tends towards 0 of 2 e to the power negative 60, which is equal to, so hence 2 is equal to, hence IVT is true, right? Okay. Now for FVT, what is the limit as p tends towards 0, p f of p, of course 2p by p plus 6, it will be equal to 0, right? And what is limit t tends towards infinity of f of t, you evaluate this is equal to 0, so 0 is equal to 0, hence FVT verified. Okay, fine, correct. Okay, so now let's see a problem which could be very difficult if we solve it using the traditional method, but if we apply IVT and FVT it becomes super easy. Let's see it. So this is the problem. We are given f of p and we are asked f at 0 and the limit of the function as t tends towards infinity. So of course if you apply like the inverse Laplace transformations, you will get the function, then you can easily substitute and check. But I'm not interested in that. I'm rather interested in using IVT and FVT to solve it. Of course you can easily find its, not easily, but with some manipulations you can find its original function. From this you can find f of t, then you can substitute the values to check the answer. That can be approached, but right now we are learning IVT and FVT, so that is why I'm telling right now how to evaluate it using that. Okay, so let me move to another slide. Solution. So basically we have limit p tends towards infinity. We know this p f p is basically equal to the limit t tends towards 0 f of t, right? And this is f of 0 which we are asked. So limit p tends towards infinity, what is this? This is p square plus 3p. P multiplied by p plus 3 is p square plus 3p upon p plus in the question it was p plus 2. Well, it does not matter much. P plus 2 whole square plus 9 p plus 2 whole square is f at 0. You can evaluate this limit. This is very simple limit, right? This is from the IVT. Now apply FVT. So limit as t tends towards infinity, f of t is equal to the limit as p tends towards 0 of p times f of p, and of course this is very easy, you can evaluate, right? I don't think so I need to waste that much time in this. Okay, so let's move to the next concepts. In fact you can do this kind of problem also using IVT and FVT. Let's see how. Well, let's see. So you can assume 0 to t is sine u by u du as suppose some f of t. Okay, so let me change the slide. Understood by the Leibniz rule, right? Okay, so you have t times f dash t is equal to sine t, correct? Okay, fine. Okay, now what we are going to do is that Laplace of t f dash t, it will be equal to minus d by dp of the quantity Laplace of f dash t, right? If you remember the formula, t times f of t is equal to negative d by dp of the Laplace transform of f of t, right? So over here in place of f of t it's f dash of t, right? Okay, now it is negative d by dp of the quantity p f of p minus f at 0. Now notice that f at 0 over here, if you substitute 0, f of 0 will be equal to 0 since the limit will become 0 to 0, right? So it becomes 0. So basically you are left with just what? You are left with negative d by dp of the quantity p f of p, right? Is it fine? Okay. And one more thing, it was equal to what? This was equal to the Laplace transform of sine of t, right? Which is equal to 1 upon p square plus 1, right? So basically you get negative pf of p is equal to the integral of 1 upon p square plus 1 dp, right? Correct? Is it fine? So you have negative pf of p is equal to tan inverse of p plus some arbitrary constant. Now to evaluate the constant, just apply the IVT, limit as p tends towards infinity of pf of p is simply equal to the limit as t tends towards 0 f of t, which is equal to f of 0, which is equal to 0. So we have 0 is equal to the limit p tends towards infinity of tan inverse p plus c. So c is equal to negative pi by 2, since tan inverse of infinity is equal to pi by 2, right? Okay, it's already going to be 50 slides, I guess. Okay, so we are left with p f of p negative, of course, is equal to tan inverse of p minus pi by 2, right? So f of p is equal to basically pi by 2 minus tan inverse of p by p, right? This is the required function. Okay, and one more thing I need to tell way back. Yeah, Laplace transform of integrals over here. So in this I need to tell, if you had Laplace inverse of some f of p by p square, then in that case you needed to integrate it twice. Okay, I need to tell this, right? Like you did normally, for one time for one p and second time for the another p, right? So let's see the application of Laplace transforms in ODE and integral equations. And with respect to ODE, in this we will be discussing it with respect to the electrical engineering too, and the general cases of like initial value problems, right? Like that. Okay, so we'll cover everything, right? So don't worry. So let's start with the first question. The differential equation for current I with respect to time in an electric circuit containing an inductance. Don't go by my writing, right? Since I am recording it since long time, so that is why my writing may fluctuate. Okay, like the current. So don't worry about that. Inductance L and a resistance R, right? in series and acted by an EMF E sin omega t satisfying di by dt plus Ri is equal to E sin omega t. Let me correct it. Satisfying. Okay, so this, and find value of current at t is equal to t, means time is equal to t, if initially I at 0 is equal to 0, right? Okay, solution. L di by dt plus Ri is equal to E sin omega t. Well, there are many methods to solve this, but we are going to apply Laplace transformations. So take both sides Laplace transformations. Don't get confused by this L and this L. This is the Laplace transformation, this is an operator, and this is a constant. L di by dt plus Ri is equal to the Laplace transform E sin omega t, right? So this L, this is the inductance, this is the Laplace transformation di by dt plus R Li is equal to E Laplace of sin omega t, right? Okay, Now over here we will assume Laplace transform of I as f of p. So basically we are assuming that L of I is equal to f of p, right? Okay. Now what's the next thing over here is that Laplace of, I mean, this is the inductance, and this is L I dash, right? So p f of p I at 0 is equal to e omega by p square by omega. This is what is the Laplace transform of sine omega t, right? Okay. Now what we are getting next is that since we know that this is equal to 0, so we have inductance LP fp, right, plus L R f of p is e omega by p square plus omega. Why I wrote L over there? For no reason. So we have f of p into LP plus R is equal to e omega by omega square plus this. Okay, so f of p is equal to e omega by p square plus omega square times LP plus R. Now either you apply convolution theorem, in that case you can assume omega by p square plus omega square as f of p. So in this you can apply convolution theorem also, like you can assume that omega by p square plus omega square as f of p and this as g of p. Then you can apply the convolution theorem and then integrate. That is also an approach. Or you can do is that you can write it in terms of partial fractions, that e omega by p square plus omega square LP plus R is equal to, e can be taken as common, AP plus B by this plus C by LP plus R, right? Okay. So from this you can solve for A, B and C, and whatever you get you just substitute there. So basically you will get AP plus B. I am not writing it right now, okay? P square plus omega square plus, what is the next expression? C by LP plus R, right? Okay, yeah, this was it. Okay, so notice that it will be A P upon P square plus omega square plus B by P square plus omega square plus C by LP plus R. When you take the Laplace inverse on both sides, you will get it as A cos omega t B sin omega t by omega plus C by L e to the power negative R by L into t, right? This will be the expression you need to just solve for A, B and C. Okay, now let's move to second problem. Y double dash minus 6y dash plus 5y is equal to e to the power 2t, given that y at 0 is equal to 1 and y dash at 0 is equal to negative, and this is also called initial value problems. Of course this is a part of ODE, but still I did not discuss there because it required the knowledge of Laplace transformations. So now you know that why I had left this topic that time. Okay, in my old lecture you can watch my lecture on ODE also. I have already made it, right? You can check it. I'll provide all the links in the description. Okay, so let's solve it. Y dash minus 6y dash plus 5y is equal to e to the power 2t, right? This is the question. Just take the Laplace on both sides. Whatever you see, just take Laplace both sides. Okay, is Laplace of e to the power 2t. It's simple Laplace of y double dash minus 6 Laplace of y dash plus 5 times Laplace of y. This is equal to 1 upon p minus 2, correct? Now what is y double dash? It is equal to p square f of p minus p y at 0 minus y dash at 0, correct? Minus 6 of p f of p minus y at 0, correct? Fine. Here I'm assuming that Laplace of y is equal to f of p, correct? Okay. Plus 5 f of p is equal to 1 upon p minus 2, right? So whatever you get when you rearrange it, right, you just rearrange this, you will solve it on your own. Of course I won't show the calculation, that is your work. Okay, I will tell you the concepts. So it will be f of p, p square minus 6p plus 5 minus 6 plus 7 is equal to 1 upon p minus p, sorry, p minus 2. So you get f of p times this is p minus what it will be, it will be minus 1 into p plus p minus 5, right? Yeah, this is the thing, 1 upon p minus 2 plus p minus 7. So you get f of p is equal to 1 upon p minus 1 p minus 2 p minus 5 p minus 7 p minus 1 p minus 5. Now just use the property of partial fractions and then solve it. It is very easy, right? Okay, just take L inverse both sides, whatever you get f of t or y, right? Okay, now such kind of equation is called an integral equation, right? Okay, no need to worry much about it. Let's see, I just told the concept that take both sides Laplace transformation and your job will be done, right? When you take Laplace transformation of y dash, what you will get? P f of p minus y at 0, what is it? It is 1, right? Okay, now minus 4 f of p, right? Now what is the Laplace transform of 0 to t of f of u into du or y of x into dx? I just now discussed Laplace transform for integrals, right? If you remember, so that is what I'm going to apply, plus 3 f of p by p, simple, right? Okay, it is equal to, what is it, what is the Laplace of t? It is equal to 1 upon p square. If you don't remember, just watch the video from the end. Okay, so of course Laplace of y of t, I assumed it as f of p. Okay, so when you solve it, you will get something like this, that let me simplify it. It will be f of p into p minus 4 plus 3 by p is equal to 1 by p square plus 1, right? So on solving, you get f of p into p minus 4p plus 3 by p is 1 plus p square by p square. So this and this gets cancelled. So f of p is equal to 1 upon p square upon p minus 1 into p minus 3. And of course this is very easy now, right? You know how to solve it, right? It is simply the partial fraction, nothing else. Okay, you can do it. So just use partial fraction, right? Take the L inverse and you will get y of t, right? Like this you solve. Now let's see a question of simultaneous differential equation, and it is like this. Okay, so let's see how we will solve it. Dx by dt is equal to x minus 2y, right? So just take the Laplace transformation, you get p x of p minus small x at 0 is equal to 2 capital XP minus 3 capital YP, right? Okay, and for the second equation, when you, this is for the first equation, now let's see for the second, that dy by dt is equal to simply what? It is equal to y minus 2x. Let me see if I have written correct. Yeah, so Laplace of dy by dt is simply equal to what? I took the Laplace both sides. Okay, Laplace transformation. Here also I'm going to do the Laplace transformation. So I get p times capital Y of p minus y at 0 is equal to capital Y at capital YP minus 2 capital XP, right? Now we know the value of small y 0 and small x 0, it is equal to 3 and 8. So basically the whole equation is now dependent upon x of p and y of p. So we have two equations and these two variables. So from this we can solve for x of p and y of p. So x is basically equal to the Laplace inverse of x of p, and y, small y, is equal to Laplace inverse of y of p, right? Simple. So this is how you can solve, right? So I hope that you understood whole lecture, and by this of course we came to an end to this lecture. There are certain things which I could not discuss because I don't think so that that is required for BTech first year, but of course I will make separate video on it if you want, and of course I will make soon. It's not something that I will skip, but for this one shot this much is enough, right? So I hope so that you enjoyed this lecture. If you did, then please do like, share, subscribe my channel, and please support my video, and please watch my other lectures too, and please subscribe and support my channel. Bye bye, take
Hello
care.
everyone, this is Aditya and today we study numerical methods in a one go. So let's start with the lecture, but for that please do like, share, subscribe my channel and please support studio. Now let's start. And I have made many one shots for engineering mathematics. Please do check it out. I will give the link in description. So now let's discuss something called interpolation. Let's define it first of all. It is the method of estimating an unknown value or values from a given set of observation. So basically if you are given different observations, then from that if I ask you to find any random unknown value, then finding of that value is called interpolation. Now it can be found using several methods. Let's discuss that. So let's discuss interpolation for equal intervals. What do I mean by equal intervals? For example, if x is equal to 5, x is equal to 10, then x is equal to 15, x is equal to 20, and so on. So there is a constant difference of 5. So it is called an equal interval, and in this the difference is 5. Okay. So to find interpolation in this, what we do is we use two methods. The first one, Newton's forward method, and second, Newton's backward method. So let's discuss both of them using an example. So let's discuss the question. This is the year, that is X, and it is 1891. And these are very common questions. If you see anyone's lecture, you will see that these questions are very common because they are very basic ones, and in your exam also you can find such kind of problems. Okay, so they are very common ones. Okay, so 1891, 1901, 1911, 1921, and 1931, right? And this is population, yeah, fx. It is 46 in 1891, and it is 66 in 1901, and it is 81 in 1911, and it is 93 in 1921, and it is 101 in 1931. Okay, so we have to estimate population in 1895 and 1925. Okay, so how do we estimate it? Well, 1895 and 1925, so we are given 2 years. So first of all, let's solve for 1895, then we'll solve for 1925. Okay, so first of all, let's draw it in a table. So it will be like this. This is x, this is fx, right? So corresponding to 1891, the population is 46. Corresponding to, I should draw it small, 1901, it is 66, and in 1911 it is 81, 1921 it is 93, and in 1931 it is, that's the end, it is 101. Okay, so if you have to estimate for 1895, what we do? Well, 1895 is lying between these two values, right? So to understand the trend, we need to see the forward values, the values which are coming after 1895, right? So because it is lying over here 1895, so you have to see the successive years for its value. That is why that is why we will use Newton's forward method in this, right? And for 1925 it is lying between 1921 and 1931, hence this is 1925, right? Because of which we will use Newton's backward method. Why? Because in this we have to see the previous trend, what was that how the population was increasing, right? So that is why we will be using Newton's backward method over here and Newton's forward method over here, right? Okay, so now let's discuss Newton's forward method. So first of all, let's complete this table. Okay, so now let's define something called delta x, I mean delta fx. Well, delta fx is equal to f of x plus h minus fx. Basically the successive value minus the value at x. Okay, it means that delta fx is equal to, for example, delta 1891 is equal to f at 1901 minus f at 1891, right? So it is equal to what? 66 minus 46, which is equal to 20, right? Okay, so over here we can write over here 20, right, for 1891, and for 1901 what will be its value? It will be equal to 15, right? 81 minus 66, right? Okay, and similarly for 1911 it will be 93 minus 81, which is equal to 12, and for 1921 it will be 101 minus 93, which is equal to 8, right? So this is delta fx over here. And now let's define another term called delta 2fx. Now how we find it? Well, we find the difference between these two values and these two values and these two values, right? So delta 2fx is basically the difference of these terms. So it will be equal to 15 minus 20, which is equal to minus 5, right? So it is basically minus 5. Okay, and what is 12 minus 15? It is negative 3, and 8 minus this quantity, it will be equal to negative 4, right? So the corresponding value to this is I should write over here negative 3 and negative 4, right, in the middle, so it is more understandable, right? Okay, so we can basically say over here that delta 2fx is basically delta f of x plus h minus delta f of x, right? And now delta, this value we all know that it is equal to f of x plus 2h minus f at x plus h minus the quantity f at x plus h minus the quantity f at x, right? Okay, so it is equal to f of x plus 2h minus 2f of x plus h minus plus f at x, right? So if you want, you can just substitute the value. So f at x plus 2h, its value is 81, so it is 81 minus the quantity, here x is equal to 1891, right? So corresponding to 1891 we are calculating delta 2fx. Okay, so 81 minus the quantity 2 times this value 66 plus f at 1891 is equal to 46, so it is equal to, let's add, we will get 127 minus this quantity, it will be equal to what? 132, right? So it is equal to negative 5, right? Similarly we can solve for these values also, correct? Okay, understood. Now let's define delta 3 fx. So it will be equal to delta 2 f of x plus h minus delta 2 f at x, right? So let's solve it also, right? So let's see how we'll find it. So it will be delta 2 f at x, right? Delta 2 f at x, sorry, delta 3. So it will be their difference. So negative 3 minus this quantity, it will be plus 2, right? And this, the difference will be negative 1, correct? Okay, and yeah, that's it. So now let's see the formula of Newton's forward method, right? So f at a plus h u is basically equal to f at a plus u times delta f at a divided by 1 factorial plus u times u minus 1 divided by 2 factorial times delta 2 f at a plus u into u minus 1 into u minus 2 divided by 3 factorial into delta 3 f at a, and so on and so forth, right? So now let's solve. Where a is equal to 1891 and u is equal to well, just a minute, and h is equal to what? H is equal to the difference. So the difference is equal to what? 10, right? Where 1981 to 1901, it is, the difference is 10, and since it is for equal intervals, so the difference will be same. So h is equal to 10, right? And we have to calculate for a plus hu. We want it equal to what? 1895, right? 1895. Okay. So from this we can solve for u now. What we'll get? U is equal to 1895 minus, what is the value of a? It is equal to 1891. 1891 divided by 10, which is equal to 0.4. Correct? So we have all the values just substituted over here. So we have f at 1895 is equal to f at 1891 plus the quantity 0.4 into the quantity delta f at a. What is its value? 20, right? 20 divided by 1 factorial plus the quantity 0.4 times 0.4 minus 1 divided by 2 factorial delta 2 f at a. What is delta 2 f at a? It is equal to negative 5, right? Negative 5 plus 0.4 into 0.4 minus 1 into 0.4 minus 2 divided by 3 factorial times 2, right? Okay. And since we can calculate delta 4 also if you want, so delta 4 will be equal to this minus this will be equal to negative 3. Okay, so it will be 0.4 into 0.4 minus 1, 0.4 minus 2, 0.4 minus 3 times the quantity negative 3 divided by 4 factorial. And of course I am not solving it, and of course you will be also having a calculator while solving all these kinds of problems. So I am directly writing the answer. It is equal to 54.852. It's around this. Okay, so after that you understood Newton's forward method, right? So this is how basically what you do is that you apply this formula, you find you assume a base value over here, that base value is 1895. Okay, and then you apply this formula, you calculate the value of u, and you know the value of h from the differences in the values of the values of x, right? So from that you know the value of u and you substitute the value over here, and consequently you get the answer. Okay, when you substitute all the values. So let's move to another not another problem. We are still left with the Newton's backward formula. Let's discuss that also. Now let's discuss for Newton's backward method. Well, f at a plus hu is equal to the quantity f at a plus u times nabla of f at a divided by 1 factorial plus u times u plus 1 divided by 2 factorial. There it was negative u minus 1. Here it will be u plus 1. Okay, 2 factorial times nabla 2 of f at a, and again it will be u plus 1 times the quantity u plus 2 divided by 3 factorial nabla 3 of f at a, and so on and so forth. Okay, so what is nabla of f at a? Well, nabla of f at x is equal to f at x minus f at x plus h, right? Sorry, x minus h. So over here the base value is 1931, right? So corresponding to this we will be having these values. Okay, correct. So it means that the nabla, what is the nabla of f at 1931? So 1931, it is equal to f at 1931 minus f at 1921. What is it? It is 1921. So it is equal to 101 minus the quantity 93. It is equal to 8, right? Correct? Correct or not? It is correct or not? It is correct. Okay. So 8 and corresponding to delta 2f, the similar formula will be there, right? So negative 4 is the nabla 2 of f at 1931, and this is the value, this is nabla 3 at of f at 1931, and nabla 4 of nabla 4f at 1931 will be equal to negative 3 again. You just calculate nabla 4 on yourself. Okay, so basically this is how you calculate the nabla function. Okay, and this is not related to something which you study in calculus and all. No, it is a different one. Okay, so yeah, this is it. So now let's solve for this 1925. What will be the population? So f at 1925, it is equal to f. Well, first of all we need to find the value of u, right? So again, a plus hu must be equal to 1925, correct? What is the value of a? It is equal to 1931. Okay, so 1931 plus 10u is equal to 1925. So u is equal to negative 6 by 10. It is equal to negative 0.6, correct? C, right? Okay, so it is equal to f at 1931 plus the quantity. Well, I should substitute the value directly. What is f at a? F at 1931, it is equal to 101. So 101 plus the quantity negative 0.6 divided by 1 factorial into nabla of f at 1931, it is equal to 8, right? 8 plus the quantity negative 0.6 into negative 0.6 plus 1, it is equal to positive 0.4. Okay, so it is positive 0.4 divided by 2 factorial times the quantity, the nabla 2 of f at 1931, it is equal to negative 4, right? So negative 4 over here plus negative 0.6 into 0.4, and negative 0.6 plus 2 is equal to 1.4 divided by 3 factorial times the quantity negative 1, right? Plus negative 0.6 into 0.4 into 1.4 into 2.4 divided by the quantity 4 factorial times negative 3, and of course you can calculate it on yourself. Of course you can't define nabla 5 over here because there will be no value then. Okay, so over here we'll be getting 96 point the 96 point what 8368, so somewhat like this approximate value. Okay, so this is Newton's forward method and this is Newton's backward method. Okay, understood? So when you have to find the value of a function by observing the successive values, the successive results, then in that case you use forward method, and when you have to observe the preceding observations, in that you use Newton's backward method. Okay, so this is it. Now let's move to interpolation for unequal intervals, right? Let's erase this. So let's study interpolation for unequal intervals. Like let me give you an example. Let's solve the question directly. So in this we'll be discussing Lagrange's method. Okay, so let's discuss that. So question, so find value of y at x is equal to 10 by Lagrange's interpolation formula. Okay, so we are given x and y, that is f at x only. Okay, so it is 5 and fx is given 12, 6, 13, and then 9, 14, 11, and then 16. Okay, so that is it. Now we have to find a function at 10. So basically f at 10 we have to find. Okay, so now we can clearly see that 6 minus 5 is equal to 1, but 9 minus 6 is equal to 3, and 11 minus 9 is equal to 2. Hence the difference is not constant, hence it is an uneven or unequal interval, right? So what we do in this is that solution, this is Lagrange's interpolation formula. F at x is equal to, so what you have to do is that you have to just write it like this. x minus 6 times x minus 9 x minus 11 divided by 5 minus 6 5 minus 9 5 minus 11 times function at 5 plus x minus 5. Wait, I'm just telling, let me write the formula first of all. Into x minus 9 x minus 11 divided by 6 minus 5 6 minus 9 6 minus 11 function at 6 plus the quantity x minus 6 x minus 6 sorry x minus 5 x minus 11 divided by 9 minus 5 9 minus 6 9 minus 11 into function at 11 sorry function at 9 plus the quantity x minus 5 x minus 6 x minus 9 divided by 11 minus 5 11 minus 6 11 minus 9 times the quantity function at 11. Did you observe any pattern? Did you? Well, what I've done is that I first of all I saw this column, okay, corresponding to x there was the value f, the f at 5 was 12, okay. So first of all I considered this column and I did not wrote 5 over here, right? I just hided this column, so I got 6 values in x. 3 values in x, 6, 9 and 11, right? Okay. So in the first value, what is it? X minus 6. So I taken x and I wrote it x minus 6, x minus 6, x minus 9, x minus 11, right? Now I wrote the same expression x minus 6, x minus 9, x minus 11, but in this I substituted the value of x in the denominator. So x is 5. Whichever term we have missed over here, we have written over here. I mean, I've taken the value which I have not written in this expression in the numerator. There should have been 4 numbers, 4 terms, not terms, 4 terms to be multiplied over basically. But I did not taken this one, so that is why this term x is equal to 5, sorry, due to which I wrote it in denominator, okay, and I took the value of function at 5 and substituted over here, okay. Now similarly I went to the next column, so I hided this column, so I could see 5, 9 and 11, so 5, 9 and 11, and since 6 was hidden, hence I substituted over here. So 6 minus 5, 6 minus 9, 6 minus 11, function at 6. So basically it is x minus, suppose if x is like this, alpha 1, alpha 2 and so on till alpha n, right? And in the middle there lies some alpha k, then any term in this will be given as x minus alpha 1, x minus alpha 2 and so on till x minus alpha k minus 1 times the quantity x minus alpha k plus 1 till x minus alpha n divided by alpha k minus alpha 1 till alpha k minus 1 times alpha k minus 1, sorry, plus 1 till alpha k minus alpha n, okay. So we can clearly see that this is the first term, this is the second term, this is the third term, and this is the fourth term, right? So we can clearly see that there are 4 values of alpha. I mean, alpha 1 is equal to 5, alpha 2 is equal to 6, alpha 3 is equal to 9, alpha 4 is equal to 11. So if I take t2, what will I get? I mean t1, then what I will get? I will get over here x minus 6, x minus 9, x minus 11, divide this and of course multiply it by a term over here, f at alpha k, right? F at alpha k, right? So this is the basic, this is the general form, okay. And if you want to write it general, to obtain this expression, just do the summation, right? Okay. So this is the general method, how we write a Lagrange's interpolation formula. So basically I hope so that now you understood that whichever column we are choosing, we are not selecting it, and we are just writing different the rest of the numbers like this, and in denominator we are doing this. We are substituting the value of that number which we neglected, right? And then we are calculating the value of that function at that particular value, right? So now let's solve it at 10, right? So let's see that. So when you substitute the value as 10, you will get 10 minus 6 times the quantity 10 minus 9, 10 minus 11 divided by this quantity. It will be negative 1, negative 4, negative 6. So 24 into 12, right? Okay, negative. And so on for these terms also. Plus, now you can calculate, it is just mathematics. And on solving, you will get 14.66. 14.66, okay? Just substitute the value as 10 over here and you will get your answer. So this is Lagrange's interpolation formula. Now let's move to next topic. So now let's study something called bisection formula or method. So basically it is used to find the solution of an algebraic or a transcendental function, right? What is an algebraic function? For example, x square plus 2x and so on, x cube, 4x square, 4x cube, x to the power 10 and so on. And what is a transcendental function? For example, log x and all, right? So let's see a question to understand this question. Find the real root of x to the power 3 minus 2x minus 5 is equal to 0, right? So we have to find a real root of this this function, right? So it is an algebraic function, right? Function, I mean. So let's see it. So let's define fx as x cube minus 2x minus 5, right? Okay. So now I need to tell you one thing. For example, if there is a function like this, any function, this is the solution when fx is equal to 0, right? Okay, and it is y is equal to fx. So what's the one thing which you can notice? Well, over here the value of function, suppose some a, is negative, right? Okay, and over here the value of function is positive. So we can easily find the solution of a function when it goes from a negative value to a positive value, because it is obvious that in this process it will pass through 0, right? It will, I mean, its value will become 0 at some point, right? Because then it can go from a negative to a positive value, right? It means that to find a solution, f at a it should be less than 0 and f at b it should be greater than 0. And one more thing, if both are positive, I mean, for example, here it is f of b, suppose here it is f of c, right? So in between it is never possible to find a solution, because of course if it in that case the function is like positive only, it hasn't changed its sign, I mean. And if it is negative, in for example here we choose a d over here, right? So in that region also it won't give any solution because it has the same parity, right? So basically f at a is less than 0 and f at b is greater than 0. So we have to choose such kind of a and b. So for example, let's take f at suppose 2. What we will get? 8 minus 6 minus 5, which is equal to what? It is equal to 2 negative 7, right? It is equal to negative 7, right? And let's take function at b as f at 3. So it is equal to 27 minus 2 times 3 minus 5. It is 27 minus 6 minus 5, which is equal to 27 minus 11, which is equal to 16. So function at 13, function at 3 is positive and function at 2 is negative, right? Now you could have also taken f at 0, there was no harm. F at 0 is equal to negative 5, right? But in the solution I have taken x is equal to 2, a is equal to 2. So that is why I am sticking to taking a as 2 and b as 3, right? So it is obvious it is going from negative to a positive value, so it is obvious to find the solution, right? In between this region, right? So now let's erase this and let's draw a chart, I mean table over here, right? So this is the number of iterations, and this is a, f at a is negative, and this is B. F at B is positive, and this is X is equal to A plus B divided by 2, and this is F at X, this value. Now notice one thing, that over here we have B and over here we have A, right? So if I take its average, I will come somewhere over here, right? A plus B by 2, right? Okay, I will come closer to this value, right? But I haven't achieved that value. So again I have A plus B by 2 as the next B over here. This is B dash, okay? This is B dash. And which value should I take A? Should I change the value of A or should I keep it same? Well, if I take A as B, is it making a sense? No, because it will again be positive and positive, means the parity will become same. But if I take A as the previous one, that is A only, then it is going from again negative to positive one, right? So again we will take the average. We will get A plus 2, A plus A plus B by 2 whole divided by 2, right? We will get that expression, and we will get closer to this value, right? And like this we will be going. Okay, so now let's see. And yeah, there might come a point when we come over here, suppose at some value a n, right? Suppose at some beta, right? Okay, suppose we come over here. So in this now we won't take this value. Why? We won't take A over here. Why? Because then they have the same parity, so we can't take that. Because if we take average, we will be ending over here, not near there, not near this point, right? So we have to again take the previous region, the previous value. Don't worry, I will be telling telling you using question, right? So don't worry. So let's see. Let me draw this. So this is it, right? Let me draw this. So this is first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th and 12th. So probably it takes around 11 to 12 iterations to solve. Okay, so A is equal to it, we had taken 2, right? And B we had taken 3. So what is its average? It is 2.5, right? 2.5. Okay, so let me erase this and I will explain you properly over here, right? Okay, so what is the value of function at 2.5? It is 5.625, right? Fx is equal to x cube minus 2x minus 5. You can check these values whatever I am going to write, because I don't know, maybe there might be any calculation error. So if there's any error, so let me know in the comment section, and you should check on yourself also the values. You know the value of function, you know the function basically, right? Now notice that the function is a positive value. So just a minute. So I don't need to draw the y-axis over here. Okay, so suppose this was the original function. Let's assume it. Okay, so suppose here exists the 0. Now this is the value of function at suppose we don't suppose this is the value of function at 2, right? Okay, and suppose this is the value of function at 3, right? Now when I taken its average, I ended over here. Wait a minute. Suppose f at 3 is over here, this value, and suppose this is 3 and this is f at 2, right? This is 2, right? Okay. So now we can see that suppose that f at 2.5 is a positive value, so it should be lying somewhere over here, right? So f at 2.5, whatever be its value, we have calculated it. So it means that 2.5. So it means that now we have to shift from 3 to 2.5 now. So when we take the average, we'll get more close to this value, right? So now should I change the value of A? No, I won't change, because the parity is still opposite. So 2 and over here 2.5. Now what is its average? It is 2.25. So its value is 1.8906, right? So again it's a positive value. It means that 2.25, it is lying somewhere over here, right? So it is still so it is still positive. Hence we won't change the value of a, but we'll change the value of b. We'll take it as 2.25 now, right? So we'll have 2 and over here 2.25. Okay, we'll be having this, correct? Now when we will take its average, we will get 2.125 and the value is 0.3457, right? So it is over here. Let me raise these values. It is 2.125, so it is over here somewhere. Okay, now again it is a positive value. The value of function is positive over here, and the value of function is negative at 2. Hence we will take again this value as 2, and it has 2. It will be 2.125. The average will be 2.0625, and when you solve it, you will get negative 0.3513. Okay, now it has come a negative value. Okay, hence what is its value at 2.0625, right? So somewhere over here 2.0625, the value of function is a negative value. Now should I change a or b? Well, now if I don't change a and I change the b to 2.0625, then the parity is same, and we can clearly see that there is no solution in this region. So it means that we have to change a to 2.0625 and b will remain 2.125, right? So we will have 2.0625 and here it will be 2.125, right? And the value will be 2.09375, and what is its value? It is equal to negative 0.0089, right? Okay, so now this value is again a negative value, right? So it means it will be somewhat over here, right? Okay, so hence we have to again change the value of a to 2.09375, and it will remain same 2.125, and what we'll get the sixth one, so it will be 2.10938, and its value will be 0.1668, right? So now it is a positive value again, right? So it will be over here. Now the value of a will be same 2.09375, and the value of b will be changed now, right? So basically if the value of function at the average value is positive, then change b because f at b is positive. Okay, and if the value of function at this average is negative, then change the value of a, right? Replace the value of a with the average, and if function value is greater than 0, then replace b with this average value. That's it. Okay, so 2.0937, 2.10938, what is its average? It is 2.10156, and its value is 0.07856, right? And now just keep on doing this process. Let me write down the chart completely now. Table. So after completing this table, you will get this result, this table I mean. So finally you can do it on your own because I have told the concept. After that you can fill on yourself. Now how to know when to terminate? Well, now after this point, when we wrote the value of the average value, we can clearly see that after this when we got 2.097 2.09, this value is constant, right? And in the last three value it is like very much constant. So x is approximately 2.09. That is the answer. Okay, so it is a very lengthy method, of course, and yeah, it takes time, but it's really an amazing method. Now let's discuss another method to do the same problem, right? Now let's study Newton-Raphson method. Newton-Raphson method. Okay, so first of all, let me write its formula. It is xn plus 1 is equal to xn minus function at xn divided by f dash at xn, right? Okay, wait, I'm telling its proof also. So suppose this is I don't need to draw the y-axis. Suppose this is the function, okay, This is a suppose function. Okay, so suppose this is a point, okay, and I draw a tangent to this point. So it will go like this. Wait a minute. Yeah, it will go like this, right? Okay, so what is the equation of tangent? Well, you all must be knowing. Suppose this point is x naught comma y naught, right? So the equation of tangent is y minus y naught is equal to dy by dx at x naught comma y naught into the quantity x minus x naught, right? This is the equation of tangent, and it is not any new equation. It is just equation of a line, of a straight line. The slope is like the derivative at this point, that is dy by dx at x naught comma y naught. This is the slope of this tangent, and this is just this is the point. This is the point form, right? That's it. Okay, so we have y. Now what is it? It is 0. It is, sorry, suppose this value is x1 comma 0, right? So we have negative f at x naught is f dash of x naught is x1, sorry, times x1 minus x naught, right? Okay, hence x1 is equal to x naught minus f at x naught divided by f dash at x naught. Okay, so we got an expression for this point, right? So we are moving close to this point actually, right? So now what is the value of function over here? So it is x1 comma y1, correct? So now we will draw another tangent, right? So suppose it intersect the x-axis at the point x2 comma 0, right? So similarly over here it is x1 comma y1, so we have x2 is x1 minus f at x1 divided by f dash at x1, right? Correct? Hence, for a general point xn plus 1, it will be this expression. Okay, so now let's see it using an example, right? So let's see the same question. F at x is equal to x cube minus 2x minus 5, right? The same question. X cube minus 2x minus 5 is equal to 0, that one. So we are solving it using now Newton-Raphson method, right? So let's see that. So we are given fx is equal to x cube minus 2x minus 5, right? Okay, now the question is that how we choose x naught. Well, just a minute. So f dash x is equal to 3x square minus 2, right? So how we choose x naught over here? Well, suppose f at 0, what is the value of function at 0? It is negative 5. What is the value of function at 1? It is equal to 1 minus 2 minus 5, which is equal to negative 6, correct? What is the value of function in negative 1? It is equal to negative 1 plus 2 minus 5, which is equal to negative 4, correct? What is the value of function at 2? It is equal to 8 minus 4 minus 5, it is equal to negative 1, right? Okay, and so on. So we choose the value of function. We choose the value of function, I mean we choose the value of x naught such that the value of function is closest to 0. So in all these values, I can see that x is equal to 2 is giving the closest value to 0, right? Hence we will choose x naught is equal to negative 1. You can take any number if you want, but it is recommended to choose a number which is which gives the value of function close to 0, right? So that you approach to that value like pretty easily, right? Else it will take more number of iterations, right? So we have x naught is equal to negative 1, right? Okay, so now let's see. The formula is xn plus 1 is equal to xn minus f of xn divided by f dash of xn, correct? Now if n is equal to 0, so we have x1 is x0 minus f at x0 divided by f dash at x0, right? So it is equal to and we can write xn minus xn cube minus 2xn minus 5 divided by 3xn minus 2, right? Okay, so we have what is x naught? It is equal to negative 1. Sorry, it is equal to 2 minus the quantity
when we substitute over here, we have 2 cube minus 2 times 2 minus 5 divided by 3 times 4 minus 2. So it is equal to 2 minus the quantity. What we will get? We will have 4. This is negative 1. Of course, I had calculated over here. Negative 1 divided by the quantity 10, it is equal to 2.1, right? So this is x1, right? Now we will use, you will find x2, it is equal to what? It is x1 minus f at x1 divided by f dash of x1. So just substitute the value. In place of 2, just substitute 2.1 over here in these two, in this and this. So it is equal to 2.1 minus the quantity. When you solve for f at x1, it will be equal to 0.061 11.23, which is equal to 2.094, right? So now let's solve x3. So when n is equal to 2, this was n is equal to 1, right? So when n is equal to this, x3 is equal to x2 minus f at x2 divided by f dash of x2. So if you will solve, it's on you now. You can easily solve, you know the value of x2, just substitute it over here. You will get 2.0945. And when you substitute n is equal to 3, you get x3 is equal to, x4 is equal to x3 minus f at x3, f dash at x3, which is equal to 2.0945. Now this value is your answer. Why? Because when you again substitute it in x4, I mean when you solve for x5, you will have to substitute this value only, right? So again you will be getting 2.094 only, because you had already substituted 2.0945 over here, and you end up getting this. So when you will again substitute, you will get again the same value, because the function is when you substitute the same value in this function, you will get same output only, right? Okay, that is why. So this is the answer. X is equal to 2.0945, right? So it is the same answer as we got in bisection method also. So it is like it is a better method because it is more efficient, and that method is like lengthy, but that is also interesting. So now let's move to numerical integration, right? Trapezoidal rule and Simpson's 1/3 rule. Let's see that. Now let's study numerical integration. Numerical integration, right? Okay, so let's first of all study trapezoidal rule, right? So if you studied integration, of course you must have studied, so in that you must have studied its proof, that suppose this is a curve, suppose not like this, suppose this is a curve, okay? So suppose this is this is the abscissa value, this is A and this is B, and you draw rectangles, right, like this. This is x1, this A is equal to x0, this is x2, this is x3, and this is equal to xn, correct? Right? Okay, so you make the partitions like this, x0 to x1, x1 to x2, and so on and so forth, right? You break it in different arcs, right? This is your first arc, this is your second arc, this is your third arc, and so on and so forth, right? And you calculate the area of each arc and then you sum up, right? And you tend n towards infinity, right? Okay, so similarly, integral a to b f of x dx, right? So what is the value of this width? Well, this width is equal to b minus a divided by n, correct? So it is equal to h times y naught plus yn, the number of intervals which you have taken over here. The number of intervals is equal to n, right? N divided by 2 plus y1, y2 till yn minus 1, okay? So this is the trapezoidal rule, okay? And now what is Simpson's 1/3 rule? It is valid for, and yeah, it is valid for every interval, right? Be it odd interval, be it even interval, right? And on the other hand, Simpson's 1/3 rule, right? So it is valid only for even intervals, right? If n is even, right?
So it is given as integral a to b f at x dx is equal to the quantity h by 3 times the quantity, since we have Simpson's 1/3, so that is why we have h by 3, correct? Okay, so it is equal to what? It is equal to y1 plus yn plus the quantity, sorry, y0 plus the quantity 4 times y1 y3 y5 and so on, the odd terms over here, plus 2 times the even terms y2 y4 and so on, right? So we have to basically divide it like this. So basically there must be even number of intervals in this case, right? So now let's see a question to understand this, right? So let's see a question. We have to do it using trapezoidal rule also and Simpson's 1/3 rule also. So integral 0 to 1 1 upon 1 plus x square dx. Yeah, I know that it is very simple integral. It is tan inverse of 1, which is equal to pi by 4. We all know this. Okay, we have to solve it using numerical method, numerical integration, right? So it is, so first of all let's find h. So we all know that we have to use the same set of values in Simpson's 1/3 rule also. So that is why I will choose n as an even number, n as an even interval, right? Because it will be then very much easy. Else if I take odd number intervals for trapezoidal rule and even for this, then it will be like too much calculations, right? So that is why I will take n as even. So problem will be solved, because trapezoidal method is valid for even and odd both, but Simpson's 1/3 rule is only valid for even number of intervals, right? So that is why I will take n suppose as 6, right? In the question also it is given 6. If it is not given the question, then choose according to yourself. Just remember that in Simpson's 1/3 rule you have to take the interval even. So if it is not given the question, just take n as any even number which you want, right? And in the question it is given 6, but still I told that if it is not given, still you can take 2 4 6 whatever you want, just an even number, right? And if it is like just for trapezoidal method, you can take 5 also, 7 also, 6 also, whatever you want. But for Simpsons you have to only take even number of intervals. Okay, so now let's solve it. So n is equal to 6. So what is b? B is equal to 1 and a is equal to 0, right? Okay, hence what is h? Well, h is equal to b minus a divided by 6, sorry, n. So it is 1 minus 0 divided by 6, which is equal to 1 by 6. Hence what we have? We have x0 is equal to what? It is 0, this value. X1 is equal to 1 by 6, x0 plus h. X2 is equal to 2 by 6, correct? Are you understanding or not? Xn is equal to x0 plus n minus 1 h, correct or not? Correct or not? Sorry, xnh, right? Nh, right? So when n is equal to 1, then we have 1 by 6. When n is equal to 2, we have 2 by h, right? I mean 2 times h. So x3 is equal to 3 by h, sorry, 3h. So x4 is equal to 4h, 4 by 6. X5 is equal to 5 by 6 and x6 is equal to 6 by 6, correct? Now corresponding to this function value, we have y0 is equal to, when you substitute over here, y is equal to 1 upon 1 plus x square. So when you substitute over here 0, you will get 1. When you substitute over here 6, you will get 36 by 37, right? 36 by 37. And when you substitute over here y2, you will get 9 by 10, and over here you will get y3 as 4 by 5. Okay, 4 by 5. And over here we will get y4 is equal to 9 by 13, and over here y5 is equal to 36 divided 61, and y6 is equal to 1 by 2, right? So this is the value. These are the values. Now we will apply the integral formula for trapezoidal rule. So what is trapezoidal rule? 0 to 1, 1 upon 1 plus x square dx, right? This is the function, and we all know that integral a to b fx dx is equal to h times the quantity y naught plus y n divided by 2 plus summation I is equal to 1 to n minus 1 y I, right? This is the formula we all know, right? So we have to just apply it over here. What is h? H is 1 by 6 times the quantity. What is y0? Y0 is equal to 1 by 6 and sorry, y0 is equal to 1, and y6 is equal to 1 by 2. So we have 1 plus 1 by 2 divided by 2 plus the quantity 36 by 37, 36 by 37 plus the quantity 9 by 10, this 10, 9 by 10 plus 4 by 5 plus 9 by 13 plus 36 by 61 plus 1 by 2, right? And just add this, you will get the answer as 0.78423, right? This is the final result using this, and pi by 4 is also 0.785, I guess, 7529, I guess, right? Pi by 4, I don't have exact value, it is something like that only. Okay, now using Simpson's one third rule, 1 upon 1 plus x square dx, it will be equal to, remember, integral a to b fx dx. It is an even interval, hence we can apply Simpson's one third rule. So it is equal to h by 3 times the quantity y naught plus y n plus the quantity 4 times the quantity y1 plus y3 and so on, plus 2 times y2 plus y4 and so on, right? Okay, so now we have to just substitute the value. We will have 1 by 6 into 3, it is 18, 1 plus 1 by 2 plus 4 times 36 by 37, y1 is 36 by 37, y3 is 4 by 5, 4 by 5 plus y5 is 36 by 61. What is y2? It is equal to 9 by 10, right? 9 by 10 plus what is y4? It is equal to 9 by 13, right? So 9 by 13 plus the quantity y6, it is equal to 1 by 2, right? So 1 by 2. And when you solve this, you will get 0.785396. So they both are almost same, but still I guess this one is more accurate in comparison to this one. Okay, so now let's move to next topic. Now let's study something called Euler and Euler's modified formula. Let's study that. So first of all, let's start with Euler's method, right? So it is basically used to solve the values of ordinary differential equation at particular points. Let me discuss them. So its formula is y of n plus 1 is equal to yn plus h times the quantity, the function at xn comma yn, right? And yeah, let's see it using a question, and h we all know how to find. We will see it. Okay, don't worry. Solution. Sorry, let's see the question first of all. The question is, solve dy by dx is equal to x plus y, and this x plus y is called x n comma yn, right? Okay, this is called fx comma y basically. Okay, so with boundary condition as function at 0 is equal to 1. So basically it is 0 comma 1. So we have to find the approx value for y approx value at for x is equal to 0.1. okay, for x is equal to 0.1. so now we have to notice one thing, that h is also called step size and n is also referred as number of steps. Okay, so if you are not given the number of steps in the question, you can take on your own, and if you are given, then you have to take that only, of course. Okay, so in the question it is given take number of steps as 5, so I will take 5. Okay, so we are given n is equal to 5 in the question. So what is the final value of x? It is equal to 0.1, and what is the initial value of x? It is 0. Hence b is equal to 0.1 and a is equal to 0, right? Hence we have h is equal to b minus a divided by n, so it is equal to 0.1 divided by 5, which is equal to 0.02. h is equal to 0.02, correct? Okay, so x0 is 0, x1 is equal to 0.02, because we all know that n is equal to x naught plus nh, right? Okay. Hence, we have this. So x2 is equal to 0.04, x3 is equal to 0.06, x4 is equal to 0.08, x5 is equal to 0.1. So we have come to 0.1, right? Now we all know that x is equal to 0. We have the value as y0 is equal to 1, correct? y1 is equal to what? It is equal to, from this formula, we know y n plus 1 is equal to y n plus h times f at x n comma y n, correct? You have this value, right? So when so let's substitute n as 0. So we have y of 1 is equal to y at 0 plus h times f at x naught comma y naught, right? So what is the value of function at x naught comma y naught x naught comma y naught? Well, we all know that it is equal to what is y naught? Well, y naught we calculate as 1, right? 1 plus 0.02. Now fx is equal to x plus y. fx comma y is equal to x plus y, correct? So when you substitute x naught comma y naught, we will have x naught comma x naught plus y naught. What is the value of x naught? X naught is equal to 0 and y naught is equal to 1. So we have 0 plus 1, it is equal to 1.02, right? So it is 1.02. Similarly, y2 is equal to, just substitute over here, n as 1. So it will be 2, it will be 1, and it will be 1, it will be 1. So it will be, what is y1? y1 is equal to 1.02 plus 0.02. What is f at x1 comma y1? x1 is equal to 0.02 and y1 is equal to 1.02. So we have 0.02 plus 1.02. It is 1.04. Correct? Okay. So this is equal to what? This is equal to 1.0408. So it is 1.0408, right? Now similarly you can solve for these values also. I am writing just the result. So I have written the result. So basically y3 is equal to this. Well, y3 will be equal to y2 plus h times f at x2 comma y2 and so on and so forth. So we have got the value as 1.1081, right? This is the answer. So function at 0 comma 1, sorry, 0.1 is equal to 1.1081, right? Euler's modified method. Okay, so in this we define two equations. Y star n plus 1 is yn, this is yn, not yn star, okay, plus h times f at xn comma yn, and yn plus 1 is defined as yn, not yn star, okay, plus h by 2 times the quantity f at xn comma yn plus f at xn plus 1 comma yn plus 1 star. Okay, this is the equation. Okay, so now let's see the question. Let's see that. So we are given dy by dx is equal to x square plus y and f at 0 is equal to 1. So we have to find f at 0 comma 0 point, sorry, f at 0.04. okay, so now we are not given the number of steps over here, so we can take any number of steps. So probably I can see over here 0.04, so I can take the number of steps as 2 because already the value, the difference is very small, so I can take the number of steps as low. So let's take n as 2. So x final is equal to b is equal to 0.04, x initial is equal to a is equal to 0, hence we have h is equal to b minus a divided by n. So it is equal to 0.04 divided by 2, which is equal to 0.02. This is the step size. Step size is equal to 0.02. Okay, so we have got the value of h as 2, right? As h is equal to 0.02. Correct. Now let's calculate x0 and x1, and so x0 is 2, sorry, is 0, x1 is 0.02 and x2 is equal to 0.04, right? 0.04. So probably we'll be getting the answer when we will solve for this, right? Of course we'll get answer then. So x0, y0 is equal to what? It is equal to 1. Now y1, well, y1 is equal to y0 from this one plus 0.02 divided by the quantity 2 times the quantity f at x0 n is equal to 0, right? F at x0 comma y0. So what is fx comma y? It is equal to x square plus y, right? Okay. So 0 square plus 1. So it is 1 plus function at 1 comma x 1 comma y1 star, right? Now what is y1 star? Well, let's calculate this now. So now here it will be f at what is x1? X1 we have got 0.02. 0.02 comma y1 star, right? Now we don't know the value of y1 star. Well, now over here we know this equation. Now let's substitute 0 over here. So we have y1 star is equal to y0 plus h times function at x0 comma y0. Correct? We will get this. Okay. So what is y at 0? Well, y at 0 is equal to 1. Y at 0 is equal to 1, right? Okay. Plus 0.02 times the quantity f at x naught comma y naught, it will be equal to x naught square plus y naught. What is the x naught? It is equal to 0. What is y naught? Is equal to 1. So we have 1 over here. So we have this as 1.02. So this is 1.02. 1.02. Correct? Understood? Okay. So now let's solve for this. So we have 1 plus 0.01 times the quantity 1 plus 0.02 whole square 0.02 whole square plus 1.02. So we will get over here what is the value of y1? Let me see it. Well, the value of y1 is equal to, when we solve it, we will get 1.0202, right? So this is the value of y1. Okay. Now let's solve for y2, and that is what we need to find, y2, right? So it is equal to 1.020, right? Now what is y2? Well, y2 is equal to y1, we know the value of y1, plus 0.02 divided by 2, which is equal to 0.01 times what is over here? It is I have written over here f of x1 comma y1, right? So it is equal to x1 square plus y1. What is value of x1? Well, x1 is equal to 0.02, and what is y1? Y1 is equal to 1.0202, right? So I can write over here it as 0.02 square plus 1.0202 plus function at x2 comma y2 star, x2 comma y2 star, right? Now how we find y2? Well, y2 star, we know this expression. So now we have y2 star is equal to what? Y1 plus h times function at x1 comma y1. So it is equal to this value is 1.0202 plus 0.02 times the quantity x1 square. What is x1? x1 is equal to 0.02. 0.02 whole square plus the quantity 1.020, this 1.0202. So on solving, what we'll get y2 star is equal to what? It is equal to 1.0406, right? So we got the value of y2 star from here, right? So it is 1.0406, correct? Okay. So now let's solve for y2. So what is y1? It is equal to 1.0202, right? Plus this quantity. So on solving this, it will be 0.04 whole square plus 1.0406, correct? And on solving, we'll get 1.0408. This is the answer. So function at 0.04 is equal to 1.0408, right? Correct? Not function over here, the value of y, right? I should write over here y, or I should change the function. Okay, I should write over here some y at 0. Why? Why? Because I've already used the function f. Sorry, I forgot that I had used it already. So it will be y at 0. Wherever I've written like this, please note that. Okay, so y at 0.04 is equal to this expression. Okay. So this is the end of this lecture, and I hope that you enjoyed this video. And yeah, I have already made many one shots on engineering mathematics, so you should check out those one shots. And I probably have completed the whole engineering mathematics. Whatever is required for your university or college level, I've completed everything in that. So it is like 25 hours playlist or 26 hours playlist. In that, I have covered everything from first year to second year, whatever is required. I mean, whatever is required in engineering mathematics, I have covered it. Okay, in those playlists for your first semester, second semester, third semester, and whatever maths. If there's some higher level mathematics required, I will make some topic wise videos then. And rest everything I've covered, the overall portion I've covered of engineering mathematics. So from now I'll make topic wise videos for engineering mathematics or bachelor or BSc mathematics. And I'll now start with masters mathematics, and of course I have to cover many topics of physics also, so I will cover that also. So till then, bye bye, take care, and all the best.